and further we can more effectively. To realize all these applications, we need to invest in R&D as well as in development of this robust and reliable infrastructure that can support quantum communication in satellite systems. As discussed, some projects are going on in collaboration with ISRO on space-based QKD systems to develop indigenous technologies. We need to work towards standardization also so as to ensure interoperability and widespread adoption of the technology. Application of quantum communication in satellite are vast and promising. It is up to us to harness the potential of this technology for a greater good. I believe this conclave would work as a trigger in accelerating the research, development and deployment of quantum communication in satellite system. The knowledge and expertise of all the participants in this conclave will undoubtedly contribute to identify the opportunities and challenges in the field and finding solutions to them. Let us take this opportunity to collaborate and share our ideas, experience and best practices to pave way for the widespread adoption of the quantum communication in satellite system. With our collective efforts, we can create more secure, efficient and sustainable future for satellite communication and leverage its potential to address most of the pressing global challenges. Thank you very much.
Thank you, Honorable Chair. And now I request Professor Joy Ghosh to present her keynote address. She is an associate professor in IIT Delhi and heads the Quantum Photonics Research Group in IIT Delhi. She's playing active role in quantum technologies projects sponsored by DRDO and Department of Science and Technology, and is also a distinguished expert member of National Mission for Quantum Technologies and Applications and the Joint Quantum Communication Working Group. I would humbly request all the esteemed panel to kindly adhere to the timings as we are very tightly packed today. So it's 10 to 15 minutes for each panelist. Thank you so much.
So a very good morning to the audience here. It's a pleasure and honor to be here in Vigyan Bhavan. It's my heartfelt thanks to the organizers here for inviting me. Thanks a lot. So today I'm going to speak about entangled photon sources, quantum photonic sources that we are building in our group in IIT Delhi. And we have projects both in free space as well as fiber-based quantum communication. So just before I go on to those projects and the results from our group, here in a nutshell, I just wanted to highlight the kind of things that we do in our group. So the broad-based research interests are quantum and nonlinear photonics. We also explore atomic physics, light-matter interaction, and basically we are interested and our challenging projects are all based on quantum technologies with single and entangled photons. Now there are different endeavors in which we work on. So these are the two blocks that I'm going to detail on today as far as allowed the time. So one is a fiber-based quantum communication project funded by DST Quest, and the other one is a free space quantum communication project funded by DRDO. We have other interests, so these are based on entangled photons, single and entangled photons. We also have interest in quantum detection via squeeze light. So we are cranking up our experiments for the generation of squeeze light. We are also interested in silicon nano waveguides, again for the generation of correlated photons, and we explore silicon nano waveguides for the same. A little different from all these aspects are coherent light-matter interaction, where we explore atomic vapors at room temperature, and we wish to see experiments that can be applied towards quantum storage, quantum memories, but there's a way to go in that direction. So here's the group and few pictures from the lab.
It's the other one. It's not
The red one. Sorry for this. Yeah, so it consists of PhD students and a couple of postdocs. We also heavily collaborate and share the group with Professor Vivek Venkatraman. So coming to the main aspect of the talk, so as we all know, quantum photonic technologies are very much interesting, particularly for their applications in quantum communication that require, and that's due to their speed, robustness, and ease of implementation. Now there are and in this regard, single and entangled photon sources are very lucrative. Particularly, it's important to develop efficient sources of such photons. Now there are two directions to explore this. One is fiber-based quantum communication that utilizes photonic qubits and sends information from one location to another through optical fiber links. And these are particularly preferable when you're looking for high bandwidth, long distance communication, as well as experiments where which is shielded from the external environment in order to minimize electromagnetic interference. The other, so this one, these are based on detectors and sources which are pretty well developed. The detectors which are solid state like in-gas SPAT, they are not as efficient, but today we have SNSPD detectors, as we all know, which are pretty much efficient as well as expensive. On the other hand, free space optical communication relies on the optical band of 700 to 850 nanometers. This is the near IR band, and here again sources and detectors are well developed. Single portable single photon detectors are more efficient than what we get in the telecommunication band. And we also have SNSPD detectors, which are definitely expensive, but they are also very, very efficient. So we have projects in both these regimes. And before that, I would just like quickly to focus on this slide. There were many speakers yesterday, so I am not elaborating on any introduction here, but just want to focus on one small thing, that there are several QKD protocols, quantum communication protocols, that can be broadly classified under two umbrellas. One is the prepare and measure based protocols, which are single photon based protocols, and in particular BB84 is very popular there, as we all know. Many of the experiments have been utilized using attenuated laser pulses, but these are prone to attacks like photon number splitting or intercept and resend attacks. In order to circumvent that and in order to make your communication link more secure, it's important to reap the benefits of entanglement. So you have entanglement-based protocols. There are two kinds, the Eckert 91 and the BBM 92. There might be other versions of that. And these are particularly lucrative. Why? Because these actually utilize true single entangled photon sources, which are quantum sources. These are resilient to eavesdropping attacks. They are inherently random. They offer long transmission paths, and they also inherent source independent security. They offer, so in this direction we like to explore entanglement based quantum communication, and there are, so these are details, because the source, the entangled photon source, could be in the middle between the sender and the receiver, or it could be on either side of it. Now, the first project, which is our project funded by DRDO, this explores free space quantum communication. So the task is to set up free space optical link, and the initial task is to develop an efficient source of entangled photons for the same. So this is particularly important for areas or locations where fiber installation cannot happen, or it's difficult to install fibers, let's say, and therefore have fiber communication, and particularly interesting for moving terminals, including the important aspect of satellite-based links. Now, some important, so this is the task, but the problem is, especially when you're doing, even for the simplest of quantum transmission, you would need some kind of a shared reference frame between the sender and the receiver. Now, in standard quantum communication, utilizing photons, the popular idea is to utilize polarization qubits. Now, polarization is about, so the sender and the receiver on each end, they need to align or orient their axis very carefully with with respect to the H and the V, because polarization information is about H and V, so that axis orientation is very important, and also to have a relative orientation between the sender and the receiver. This is all fine, but if the two parties are moving with respect to each other, or there is some rotation or some misalignment, then this kind of an information might get distorted when it is being transferred from the sender to the receiver. In order to circumvent that problem, it's important to encode your qubits in rotationally invariant hybrid photons. And with that aspect, we have this project where we actually explore an alignment-free QKD, or a quantum communication protocol. We are in the middle of our experiments. We have achieved polarization entanglement in this, but it needs the results need to be improved. And the next steps are hybrid entanglement based on multiple degrees of freedom of the photons, such as orbital angular momentum and polarization. And then once that setup is ready, we are going to explore it for entanglement-based QKD. So these are our recent results for polarization entanglement. The other project, which is funded by DST Quest, actually explores fiber-based, all fiber-integrated, fiber-based, WDM-based source, a waveguide-based source. And these are important, particularly if because these systems, any kind of quantum communication or any of these quantum technological experiments are becoming more and more complex. So it's important to have stability and high efficiency in the source. And in this regard, integrated systems, as there are other speakers who talked about it yesterday, integrated systems utilizing fiber-based or waveguide-based systems, they have demonstrated a huge potential. And in this regard is our second project, which is totally fiber-based, and it motivates, or it wants to explore a multi-user QKD kind of a protocol. So recently we have built our source. It also got highlighted, and so it's not only important to have an entangled photon source, but it's also important to have a source which competes with other similar sources internationally. So that depends on the characterization of spectral brightness, the coincidences to accidental ratio, and all of that. And we are proud to demonstrate that we have such kind of a source which is very compact in our lab. We want to put it in a box and then explore it towards multi-user QKD. So we have so this is highlight, and recently we have also actually seen polarization entanglement with this source, both in broadband as well as the individual channel entanglement. This has been achieved, and the next steps is to explore entanglement-based QKD in the same setup. This is a very compact tabletop setup, and such sources can be taken outside the lab and soon explored. So I would just like to, so those are the experimental endeavors, and we also actually explore a lot of designs on integrated architecture that, for example, generates all optical Bell states through a multipole integrated waveguide device. So these designs are all in popular nonlinear materials of KTP and lithium niobate, and as you all know, if we can have such architectures, if we can fabricate them, we can actually generate all the 4 Bell states through such an architecture, or we can also generate post-selection free hyperentangled photon pairs utilizing such an architecture. Hyperentanglement is again utilizing different degrees of freedom, and I will not go and get into the detail, but I would just like to highlight here, we are not fabrication experts, but if such fabrication of such devices are possible, keeping in mind all the practical aspects, then we can have these sources very compact, almost on chip, and we can take it out to space as well. So this is one direction, and just 2 more slides here. So I would just like to highlight, because the group also explores silicon nano waveguides, because we want to also explore correlated photon emission through silicon nano waveguides. Silicon is very hot, very easy to implement, also because of the CMOS architecture that is very compatible with silicon, and we are developing such sources as well, and we are trying to crank up our experiments on this. And so this is a slide that we have where our recent paper in PR Applied was actually selected as the editor suggestion, which talks about broadband silicon photon wires for broadband polarization entanglement at telecommunication wavelengths. So yeah, those are the experiments, and yeah. Thank you.
Thank you, Professor Ghosh. Our next keynote speaker, Dr. Ravindra Pratap Singh, is the chairperson of Atomic, Molecular and Optical Physics Division at Physical Research Laboratory, Ahmedabad. He built experimental program in laser physics and quantum optics from scratch at RPRL, Ahmedabad, that houses three 10,000 class clean labs with equipment and accessories of more than $5 million. He is presently involved in free space quantum communication projects from Department of Science and Technology and Department of Space as part of Quantum Science and Technology program at PRL. Dr. Ravindra Pratap Singh, please.
Thank you for the introduction. It was very generous introduction. I think that I didn't give. Maybe you might have taken from LinkedIn. I gave only one line introduction. That was good enough. Anyway, thank you for inviting me to be here, giving this chance. Department of Telecom, Mr. Abdul Qayyum, Mr. Venkatraju. So, I am here talking to you because of my students and younger faculty colleagues. You can see them, they are good numbers, and there are many more. So I have given names who are directly contributing to this work. So Ayan is now in UK, working in University of York, postdoc, and India is in NUS, Singapore, and Rupesh is again, he's from lab, he has become faculty at University of York. And Pooja is electronics and communication engineer, so they equally contribute, and they contribute heavily to the quantum communication program, electronics and communication engineers. Jabir and Nizil, they are at NIST, and Ali is in Fraunhofer Institute, and Ali is in UK, Fraunhofer Institute, Sarika is in Germany, Fraunhofer Institute. Anju is doing PhD, she is working on CVQKD. Okay, already we have some results on CVQKD. And Samantha, Sasi, they are my younger faculty colleagues. So, in PRL, many people don't know, that's why I put PRL, this t-shirt today. So, it needs a little bit of advertisement. People think PRL is in Delhi, many people get confused. Everybody knows ISRO, but they don't know ISRO came out of PRL. Okay, PRL is 75-year-old institute. And whole space program started from PRL. They don't recognize PRL, many people. They don't take even name of PRL, but it's all because of PRL. You see this, all the satellites and all. Even first satellite, Aryabhatta, was assembled in PRL. It started from PRL only. So at PRL, we have started this quantum science and technology program. We have like covering all the stacks of quantum technology, starting from communication, computing, sensing. So we are covering all the technology verticals in quantum. This moving is taking.
The big green one. Yeah.
Okay. That side or this side I have to do?
No, the big green, this one.
This
Yeah,
one?
you don't-
Oh.
That's, I had the same problem.
There's so many greens, there are 3 greens. So, as you see this QKD, we are going to talk about QKD. So, it is like discrete variable, continuous variable, and we are covering whole reason. So, you can have prepare and measure, already Joey has talked about B84 and B92, prepare and measure. You prepare in a particular polarization state or even phase, particular, and then you measure. And then entanglement based protocols, BBM 92 and Eckert 91, and then accordingly in continuous variable you have again prepare and measure and entanglement based. You can have Gaussian modulation or discrete modulation, so all the things you can cover. It's going, no?
The big green one.
Yeah, big. Oh. So this you can have, as I told, entangled photons as well as prepare and measure weak coherent pulses. Joey has told that you attenuate the laser so that per pulse you use pulse laser so that per pulse you have less than 1 photon. So it's not single photon source. Many engineers get confused. They say single photon source, single photon source. When you say weak coherent pulse, it's not a single photon source. Single photon source has very peculiar characteristics, which is not possessed by this weak coherent pulse. So it's attenuated laser, pulse laser, so that on average per pulse is having less than 1 photon. So both are different things, single photon source and weak coherent pulses. So you can use weak coherent pulses as well as this entangled photons. So this is when you are using entangled photon. This is there are two ways. One can do satellite-based quantum communication. When you are using entangled photon, this is pair. You can use it as trusted node. Satellite can be used as trusted node. And when you are, because you are not keeping the key in the satellite, that's why it's trusted node. You are not keeping the key is here only. And when you are using weak coherent pulses, you generate key with one station, then you generate key with another station. So both keys are you can see that both are there. So now this is K and KP, both keys are there. Then you XOR and then you send and then again another XOR, and both the stations having same key, symmetric key distribution you can do, and that's how you encrypt the message and you can have secure communication. So you can have both trusted. Here it is trusted because satellite is having key. Anybody can hack, but you have to trust that nobody is hacking. So that's why it's called trusted. Okay, you are trusting that nobody is going to hack. This is called untrusted. So both ways you can have, and my heart goes for this entanglement based. Okay, because it's untrusted, and if you want to develop quantum communication network or QKD network or internet, quantum internet, it has to be based on entangled photons only. So that's why one should have this one. So we proposed, like in 2015 it all started, we proposed for satellite based quantum communication to the principal scientific advisor with all the budget, timeline, everything, but it was not moving. Then Quest started, DST in 19. So we thought, let's go for this free space quantum communication, because this is the stepping stone for satellite based communication, is a longer free space quantum communication. So we thought we should go for free space quantum communication, and that will lead to satellite communication later. So that's how it started in 2019. So under this project, we have done quite a bit of work related to QKD. We have generated, like we have used BB84 for 200 meters free space channel, then entangled photons, and most of the results are published now. And we have studied like what could be the information leakage also, which kind of attacks are possible when your source or detector is not perfect. Okay, in theory you assume that everything is perfect, okay, and it's theoretically secure everything, but it's not always true, because your instrument, your equipment is having some imperfections, so it can't be secure like theory. So that we have done anyway. So this is the entangled photon source. It's very compact. It's like 15, 20 by 25 centimeter, very compact. It is in the box, and it uses like periodically poled crystal, nonlinear crystal. And here you get two entangled photons. This is the pump laser 405, and it's degenerate. Degenerate means both the pair having same wavelength, 810 nanometer. And then you measure polarization correlation. So these are the like analyzer and lambda by 2 plate and PBS you use. So you analyze the polarization. You are looking for polarization correlation. Here we are generating polarization entangled photons. That's why you are looking for polarization correlation. You fix polarizer of one, polarization of one beam, one arm, and then you keep on rotating. So that's what this correlation curve comes. It's like interference, this correlation curve. Like interference also, it's field correlation. So now you are looking polarization correlation. So that's what you get. And so you can see that's this is the measurement of Bell inequality measurement. So 2.63 is a very good source of entangled photons and very robust also. So this is the schematic where we have done this free space quantum key distribution using entangled photons. We have done for 35 meter and 200 meters both. This is here entangled photon source sitting here. Then you send to Alice and Bob, and these are the cabins, and this is the where we send from meddles and get it bound. So that's what. So this is the similar curve which I was showing earlier. These are the 98% confidence interval lines, inner and outer. Middle one is theoretical fit, and then even after distributing at 200 meters, you can measure the Bell parameter is 2.54, and we collect the photons for 1 nanosecond. So that's what timing is very important. If it is 200 meters, around 200 meters, the photons which are coming, it is like you have to collect around this 648 nanosecond, even 0.5 nanosecond if you are, so you will not get the key. And because we are having HS plus VV polarization entangled state, so when you are sending H, it has to be measured in H, both has to be in H. And what is the beauty of entangled photons when you are using for QKD? You don't have to use random numbers. That's the very good advantage. Because entangled photons, they take care of the randomness, so quantum mechanical randomness. So that's the very good advantage when you are using entangled photons. So that's the key basically. Anyway, so what is going? So we have to go back. How to? Yeah. Okay. So that's what you HHVV, you count this thing, a diagonal thing that will form the key. So that's the key rate. You can have this Cuber also 4%, and these are the parameters, the channel transmittivity and all those things. So then we have studied the atmospheric effect also. We have space and atmospheric sciences program in PRL. So we could find out the extinction coefficient, megameter inverse, and scattering coefficient. For PM, means particulates who are less than 2.5 per micrometer, so their concentration also we could find out. And what we observed that our key rate depends on these atmospheric parameters, and it follows like key rate follows atmospheric conditions. So what we say, if you are studying quantum key distribution, at the same time you can have atmospheric parameters, aerosols and other. So it's very great advantage. Same time you are having atmospheric parameters along with quantum key distribution. Nowadays climate studies are becoming very important. Atmospheric studies are very pollution is a big problem. So along with that you get as byproduct. In fact, when I was presenting this work in Israel in a conference, in a meeting, they said, have you patented this idea? I told no, we have not patented. They were very impressed. That's really very good. You can, along with QKD, you can have like atmospheric data also. So this is the CVQKD result we have got already. We are having some results. This is, so we are getting around this one, secure key rate 0.30 bit per pulse. So we are using this 80 megahertz laser, so quite a high key rate. And why we use CVQKD? Because it's easy to integrate with existing communication network. You get you don't have to use single photon detectors, which are very costly, very bulky. You can use standard photo detectors, homodyne detectors. You get higher key rate. Okay, so there are many advantages when you are going for CVQKD. So that's what it is, and ongoing work. So this is the discrete modulation, and that's what result was shown. And this is the setup, and this is in-house developed QRNG. We have entangled photon based QRNG. We are making random numbers using entangled photons. So this is, we are using that only for this work, because it's prepare and measure this discrete modulation. We are modulating, we are preparing in particular state. So you have to use random numbers. If you are using entanglement, you don't have to use random numbers. So that's why QRNG was used there. So this is the Gaussian modulation thing also we are doing. Okay. So this is the setup, and the let us come to the international scenario. So Chinese, basically they are the leaders in quantum communication, and all the major investment by countries, different countries, European Union, USA, and everybody started putting heavily into this quantum technology because of misuse, and we should be thankful to the Chinese for this big boom in quantum technology investment. Okay, we are here talking maybe because of this misuse 2016 launch. Okay, so and they have planned to have worldwide quantum key distribution network by 2030, and I am pretty sure they will have by that time, because already they have developed this network in China using 5-6 stations. They have 3 satellites already. MISES is one, they have already 2 more satellites, and they are having QKD network over China using satellites. Then China was not the first one. Basically, this free space thing and long distance, it started in Germany, and they did it in, you can see that, in 13 itself, okay, using flight, 20 kilometers. They could do the key distribution, Herald Wine Further group. Then Japan, you will see that in May 14 itself, they launched this satellite. Although they published quite late, it didn't work for a very long time. That's why they were hesitant to publish the data. They published in 17 only, and they did B92. They got the key, okay, and published later. So they were the first one, rather, through satellite getting the quantum key distribution. It was very compact, entangled photon source. This is very compact satellite, okay, macro satellite, and very compact ground station. Their ground station is the most compact one. And then Italy was the first one to show that it's feasible to use satellites for quantum key distribution, and they published in 2015, much before the Chinese launch. Yeah. And this is the future plan at Quantum Science and Technology program. So we have turbulence, how it is going to affect, how to mitigate the effect of turbulence. We can simulate uplink and downlink using calibrated turbulence cells that we have with astronomy and astrophysics division of PRL, and development of device independent QKD. That's what we are doing after this BBM 92. Then entanglement swapping and quantum teleportation. It has already been talked yesterday. We are doing that also. And then finally, using structured light, we can have like more robust and secure key distribution. And a new lab has started working to develop photonic quantum computing, because it is the best bet for quantum internet, worldwide quantum web. Okay, and with that, thanks.
Thank you, Professor Singh. Well, Dr. Bruno Hartner yesterday enumerated on the future of quantum communications. So we request him now to share his inputs in this session. We all know him as the Director of Strategic Quantum Initiatives in ID Quantique, Geneva, Switzerland. He has extensive experience in the field of quantum technologies, particularly in the areas of quantum cryptography and quantum key distribution. He is also the co-chairman of the Quantum Safe Working Group organized by the Cloud Security Alliance. Dr. Bruno Hartner.
Okay. Right, so it's good to be back. Today I'm going to talk to you about basically randomness, and especially randomness in space, because that's the topic of the session. So, as usual, I like to go back first to basics, and let's think a little bit about randomness. And randomness is really the basis of all cryptography. If you want to exchange a secret or to do something which nobody else can know, obviously you have to surprise him. You have to do something which is not expected. And that's why you really read randomness. So any good cryptography, it can be quantum, it can be standard modern cryptography like RSA, it can be post-quantum cryptography. Every single cryptography starts with random keys. Somehow you need to start with randomness. And then, of course, afterwards, you can have mathematics, physics, whatever, QKD, but you still start with randomness. And here I have to disagree slightly with my esteemed colleague. Even with entanglement, you need randomness, not on the value of the bits, but on the choice of the basis. So if you do a Bell experiment, you should still need some randomness to start with in order to make sure that the two bases you're going to use to measure are not the same. I mean, to make sure that they are random, basically. So whatever you do, you start with randomness. Now, what is randomness? I mean, it's actually very hard to know exactly what is randomness. You can basically test randomness, but it's much harder to really define it. And this was started, well, more than 100 years ago, 200 years ago, yeah, something like that, by Kerckhoff. And he said that in cryptography, in order to have security, what you need is a key which is, first of all, unique. So you need to make sure that nobody else knows the key. So you can have something perfectly random. If it's known by somebody else, obviously you cannot use it for cryptography. Then it has to be really truly random. That's the main thing, unpredictable. If somebody can know what will be the next bit of your key, obviously you cannot use it. And last but not least, you need to store, distribute, and manage securely. So if you got a best key, which was basically generated with random, distributed with random, but you store it badly, obviously you cannot use it anymore. So basically, cryptographic randomness has really to be private, so it has to be yours, and that's why we believe it's much better to generate it as close as possible to the place you're going to use it, basically locally. So it's not such a good idea to ask for a randomness source to be away and to send it to you in some way, because somebody can intercept it, find out what it is, and then of course it's still random, but it cannot be used for cryptography. So how do you build a random number generator? There are several steps, and I think here it's the easiest way, the best way is to go back to NIST, okay? And when you look at NIST, there are three different steps, basically. The first one is the entropy source, and this has to be a physical process in order to be secure. You need to have something which generates bits in a way which cannot be predicted in any way. Of course, being a physical process, it cannot be perfect. Therefore, you need to process it in order to make the bits as perfect as possible. And this is really the goal of the random bit generator, which you use to basically improve the randomness of your system. Once you have these two things, then you have a random source you can use. And of course, before you use it, you test it. And many people think that randomness is something that is only tested by all the NIST recommendations. That's not truly the case. You need to start from the beginning, generate random bits, process them to make sure they're as perfect as you can, and then test them. If you got a string of bits and you only test the randomness through the NIST process, from the NIST test, it's not enough because you don't know if somebody else can know it or not. You really need the whole process. And actually, the hardest part is the entropy generation. The rest is more or less well known. You can easily make a random bit generator. You can easily test strings of bits. I mean, you have ways to do that. To generate the entropy is what is actually the critical path. And here, how to generate this entropy, we can go back to John Neumann, who said that basically you cannot do it with deterministic systems. Okay, if you start with something deterministic, it will remain deterministic. There is nothing you can do about it. So never start with a pseudo-random number generator. You can use this pseudo-random number generator as long as you started with good entropy seed. Okay, so that's really the main thing you need to remember. You need a good seed to do that. How do you get this seed? Well, you can start with classical systems. And then if you work with classical systems, there are two ways. First of all, you try and get something with external noise. So some noise coming into your system, and you say, okay, this noise has to be random, and I can use it. That's possible. However, you need to make sure there are no hidden regularities. And basically, if you look at this graph, it looks random, but if you look at the frequency distribution, you will find out that it's not at all, for example. The second thing is that this random thing can be manipulated. Somebody can give you this. It looks very random, but the guy who is giving it to you knows exactly what it is. It can also be duplicated. It means that somebody else can be next to you, find exactly the same randomness. And of course, if you are in a remote location, for example, somewhere in a telecom house or something like that, you may not have access to external fluctuations. And therefore, it's not a really good idea to rely on external noise. So let's try and see if there is another way you can generate randomness from classical system. And there is a way which is quite used and probably not bad at all. It's from chaos. If you take a chaotic system, of course, it's very sensitive to initial conditions. So any very, very tiny change of the initial condition will change completely the output. And therefore, very quickly, the output will be random. So that's not too bad. You can use it. But there are still some issues with that. First of all, a system which is chaotic is only chaotic within a given range of parameters. The same system can suddenly become deterministic if you move a little bit the parameters. So somebody who is clever enough to tune the parameters of your system by, for example, an external influence, changing the temperature, putting some radiation or something, could actually manipulate your chaotic system and make it deterministic, and he could know what's going on. Another thing which is actually very important is, especially in the context of the quantum computer, is that once a chaotic system is still something deterministic. So if you have good mathematical techniques, you might be able to predict the behavior much better than you can do today. And this, of course, could be done with machine learning and artificial intelligence. As we know, they can find the needle in the haystack. They can look at this very large data and find out some kind of repetitiveness or something like that, which would lead to breaking the randomness you wanted to have. Therefore, using chaotic system is again a possible idea, but probably not the best one. Quantum is great, and I explained very briefly yesterday, because whenever you do a measurement, quantum mechanics is telling you, you cannot predict the result. There is absolutely no way, if I prepare a qubit in a coherent superposition between 0 and 1, and then try to measure if it's 0 or 1, the result is random. And we now know that there is no hidden variable which can tell you what it is. There is no way you can predict the result of a measurement which is starting from quantum. At ID Quantique, we use the one particular way, which is really looking at the photon distribution of a laser light impinging upon detectors. And that's the basic idea behind our random number generator. And if you haven't done so, I encourage you to visit us on our booth and see how small you can make the system using this kind of idea. So you can today make a very, very small system which generates randomness from quantum principle and have a very, very good entropy. Applications, as I said, are many, many. Basically, anytime you need cryptography, you should use randomness, and it can be used in all these kinds of applications I mentioned here. Now I want to focus briefly on, of course, I cannot not mention the fact that our quantum randomness source is small enough to be in a telephone. And again, if you want to see for yourself, come to visit us on our booth. It can also be used in connected vehicles, for example. And actually, it's interesting to realize that the demands on standardization and testing for this kind of application are actually very, very stringent. We passed the test for environment test for vehicle, which are actually harder than the space one I will mention in a moment. But the focus of the talk really is in space. So in space, as we all know, the main requirement is swap, size, weight, and power. Because the satellite is restricted in all of these, you need to make it as small as possible, as light as possible, and it shouldn't use any power if possible. So that's the first thing. Second thing, which obviously is a big difference between space and ground, is radiation hardened, because in space you have a lot of radiation and you need to test your system in order to make sure that it will work even when you have a lot of radiation. And the last one, which is a little bit the same, is harsh environment, which means that you need to work at very low, very high temperature, zero pressure, so on and so forth. There are many, many tests you need to do in order to be able to space qualify a chip like that. And that's basically what we did with our system. So we didn't do the chip only, because actually it's not really possible, but we put the chip on the board, and we tested the whole board for space, and we passed basically everything that was needed. Again, to make a space-qualified electronic board is not totally obvious. I mean, you need to follow some very strict regulations. Once you do that, you have a board which you can test. And of course, we went through all the tests in order to space-qualify this little board. And now with this board, you can safely take it, put it into a satellite, have a totally standard communication between the board and your computer or whatever you're using, and you can make sure that you have good randomness there. And again, it can be used for QKD, because you need randomness for QKD. It can be used for any kind of communication with satellite, and we have a major satellite builder, manufacturer, who is going to use this kind of system in his satellites. I just show here a little bit, but probably not too much, the test we were doing. So we took space qualification is a rather long and expensive process, and this is the reason why any space qualified board is rather expensive. I mean, something which you can sell for a few dollars in the ground will go to thousands of dollars, simply because you spend so much time and money doing all the tests to make sure that it will work. And our system obviously passed all that. So a summary, I think the most important thing is really to remember that whenever you do cryptography, classical, quantum, post-quantum, whatever it is, make sure you start with good randomness. Otherwise, your keys are worth nothing. In the quantum era, it's even more important, because we believe that the power of the quantum computer may actually be strong enough to destroy any kind of pseudo-randomness you have. If your randomness is not good enough, a quantum computer, machine learning, and artificial intelligence may actually be able to find in some way what's behind and actually extract then the keys, or at least get an idea of the key. Remember, if you have a key and somebody can get the first bit of your key, doing the same process over and over again, it will then get the second bit and the third bit. So even if you have a 256-bit key and you leak one bit, you basically leak the whole key. Okay, so that's very important to remember, that you really need something very good to start with. That's why we believe that quantum technology is really the best way to generate randomness. And with respect to this session, if you need randomness in space, you can already have space-qualified QRNGs now. They're available as I speak now. And this will improve security in your satellite by making sure the key you start with is good. Of course, it's up to you afterwards to make sure that all the rest of the chain is good enough. At this point, we are only talking of key generation. All the rest have to be done, and in order to get real security, you start with a good key and you need to make sure that all the rest follows. Thank you very much.
Pleasure to introduce the last speaker of the session, Professor Urbasi Sinha. She is a professor at the Raman Research Institute, Bangalore, and heading the Quantum Information and Computing Laboratory at RRI. She completed her PhD at Cambridge University, UK, on experiments in high-temperature superconductivity. Her scientific recognitions include the Homi Bhabha Fellowship in the year 2017, as well as 2018 ICTP-ICO Galliano DiNardo Award in Optics. She was recognized as one of Asia's top 100 scientists by the Asian Scientist for the year 2019, and has also been awarded the Simons Emmy Noether Fellowship at the Perimeter Institute, Canada. She also led the 2-member winning team as a mentor at the World Skills International Competition in Quantum Technology at the BRICS Future Skills Challenge organized by the Russian Quantum Center in Moscow. She also won the ASSOCHAM Women in Cyber Making a Difference Award. Professor Urbasi Sinha, please.
Thank you very much. So green button, yeah, to go forward. Red button to go backward. Doesn't work. Okay, so thank you very much for the kind introduction, and of course thanks to TEC, CDOT, and TSDSI for inviting me to present this talk here today. As was mentioned, I am at the Raman Research Institute in Bangalore, and I'm also an affiliate faculty at IQC and CQIQC and a Simon Seminoider Fellow, all in Canada. So I would like to thank my previous speakers for doing almost every introduction that I may have needed for my talk. So I can jump straight to telling you what we have been doing, over the last few years. So with that, this is what we work on. We work with photons. We work on quantum computing, quantum sensing, QIP, fundamentals of quantum mechanics, but today's focus is, of course, quantum communications. In a nutshell, this is what we represent. So here you can see our projects in quantum communication. So we are working on satellite-based QKD. This is India's first funded satellite-based QKD project, and I'll tell you over the next 13 or 14 minutes on this project. Having said that, we are also working under the DST Quest project on quantum relays and repeater technologies, DST ITPAR on integrated photonics-based quantum key distribution, as well as long-distance quantum teleportation and device-independent random number generation from a project funded through MIT. We are India's first lab dedicated to photonic quantum science and technologies, and we have many interests, including higher dimensional quantum computing and quantum information. So this is some of the snapshots. And this is essentially the main highlight results. The back button doesn't work as well as the front one, which wasn't going to be my... Madam Chairperson, please note that I've spent a bit of time going back and forth, okay? So these are the highlight results from the lab over the last couple of years, and of course I won't be telling you much about them. So having said that, this is how our journey began in December 2012 with various people who came and graced the occasion of inaugurating our lab. These are the people who are, of course, making things happen in the quantum communication space, and there are several more in other domains in the lab. Quantum experiments using satellite technology. So it is a collaboration between RRI and Indian Space Research Organization, particularly UR Rao Satellite Center and LEOS, which are both based in Bangalore. Our aim is rather simple. We want to establish information theoretically secure quantum communication over large distances using a satellite as a trusted node, and essentially perform entanglement-based quantum key distribution between two Indian ground stations using an Indian satellite as the trusted node. Now, why is this experiment exceptional? I mean, this is a rather objective view. Quest is India's first project on satellite-based quantum communications. As RP mentioned earlier, we didn't have a lot of traction to get funding for these projects till our neighbors actually flew a satellite. And so we benefited from that. And we started at a time when the field was not that popular. And its achievements, we believe, humbly, have played a major role towards putting India on the global quantum communications research. So I think, that makes it already exceptional. Having said that, it works on security in communications, which I need not introduce, and satellite is a good means. I think by now we all have an understanding of that. Having said that, this is the picture of two different possibilities towards satellite-based QKD. The left one is what our friends in China have done. They have demonstrated downlink-based QKD, and these are some publications from the group for that. So downlink means that the entangled photon source is in the satellite. Okay, so you fly it away. What we are aiming to achieve is uplink-based QKD, and having said that, this has never been shown before globally. So naturally, we are aiming to achieve that because really we like to stress ourselves out at RRI. So we want to do something which hasn't been done. So not repeat and so on and so forth, all those crazy things. And so, but what are the scientific aims of this? One, uplink allows for photon source to be at the ground-based lab. We don't need to fly it. So this means that we have more flexibility with changing the source even after the satellite has been launched. So Joey comes up with a better source 1 year after the satellite is launched. We can in fact integrate that without having to fly another satellite. We can include quantum memory components after the satellite launch. And so essentially it gives us a tremendous scope for novel first-in-the-world science, but then it's also very challenging. Many challenges, like Bruno mentioned, many things have to be space compatible and some of them don't exist. But then we are very happy to take up this challenge, and we are sincerely hopeful that we will get there in real time. So this is, these are the things we have achieved. Development of a QKD experimenter simulation software. We discussed this in the panel discussion. We have done the performance analysis with an in-lab protocol. We have developed, of course, several entangled photon sources. We have also done free space atmospheric channel characterization, we were told. That is important, of course. So prototype for entanglement-based QKD, both in lab as well as atmospheric channel. And currently, we are very excited on our progress with the moving receiver platform for QKD. So, okay, this is, of course, the big picture. We'll skip that. The milestones achieved so far. So this is, of course, one of our very, important milestones. This was an in-lab experimental demonstration of the B92 protocol. And so this is India's first reported end-to-end free space QKD experiment, which has been published in an internationally peer-reviewed journal. And so we had competitive key rate and QBA, which were better than the previous ones. Then we went on to do the first demonstration of QKD between two buildings using an atmospheric free space channel. This was done in February 2021. We have heard of other demonstrations. Some of them also call themselves first, but that's not right. Ours was definitely the first in terms of the chronology. So, and we achieved this very beautifully. We are very proud of this. Very recently, we have done something which I'll talk about for a couple of minutes, which both RP and Joey alluded to. We need to correct the polarization if we want polarization degree of freedom, and we've come up with a very interesting method to obviate that. And then we are also now becoming software developers. So we are developing software for simulating QKD with device and process imperfections, and so on. So this is the B92. I'll skip the details. It involves two measurement bases, but the idea is this is on Heisenberg's uncertainty principle. These are our, basically the components used. And having said that, at the Alice side, we used a heralded single photon source using continuous pumping, which kind of was an answer to the PNS type attack, which we could avoid to a large extent. Then we used passive quantum randomness. Within the setup, we used quantum random number generator so that we could obviate attacks based on active random basis selection. This is our Bob module. And here also passive quantum randomness, no gated detection required, and continuous record of timestamps. So these were some of the novelties we introduced, which made us achieve this higher key rate and lower QBA than all previous demonstrations. So there's the snapshots of the actual setup, of course. And going on to the next thing. So with QKD becoming commercially viable, advanced engineering techniques are being proposed. So direct testing is not always very cost effective. You don't want to build an optics setup and then realize you want to build it better. So a simulator can accurately pre-evaluate the performance of these setups and designs. So the competing QKD simulation toolkits in literature are these, and maybe you will find more if you search. But having said that, missing requirements in this are quick and precise simulation of physical processes and consideration of experimental non-idealities. So we are developing software as experimentalists. So we know what problems we face, so we include that. So our results obviously will match better than the commercially available ones right now. And so this is what we call QKD Sim, QKD Experimentals Toolkit. We have created a logo with a lot of hope for the future. So these are the various details. So we are following the AGIFOL model of software development. And so we have also come up with a lot of nice post-processing algorithms as a part of this software development, which you can all, you can see the details in the publication that is listed below. You can see the beautiful match between theory and experiment here. And this is something you wouldn't get if you just used an off-the-shelf simulator. This was the previous result, and this was in fact held by a group from NASA. And so you can see that our key rate is much higher and QBA is much lower. In fact, ours is information theoretically secure and theirs wasn't. So this is our achievement. So it matches very well. Salient features, as I mentioned, different types of attacks could be mitigated. We also got a lot of appreciation for this. This is popular media. This is Nature India, which is a science forum. This is IBM blog, I would say an industry recognition. And this, the biggest one, Government of India recognizing us for our small efforts. So this is what resulted from this development. We have done in-lab quantum key distribution, of course, using entanglement-based QKD. And these results are actually going to appear. So this was accepted a couple of days ago, very much in time for the conference, in Communications Physics, which is a very important journal from the Nature Publishing Group. And so we're very happy with these results. So this is our performance analysis. As you can see, this is our in-lab prepare and measure based protocol, and this is our BBM92 protocol. So clearly, we have achieved very competitive numbers in all these protocols. Having said that,
As I said, I'll talk to you about this very recent result, which will be appearing shortly, about how we can obviate the polarization correction. So long distance QKD, polarization of light, is a commonly used degree of freedom, and it's becoming increasingly important. So significant challenge is, as was mentioned, that polarization gets affected due to birefringence in fiber-based as well as free space communications. So variation of reference frames due to satellite movement in long haul demonstrations. So conventionally what we do is active feedback based mechanism in real time polarization tracking, right? So what we employ is a polarization basis compensation method that obviates the need for active polarization tracking in satellite QKD. So we replace the active with a passive feedback mechanism, which works very, very well. And in fact, we are very happy, that it is independent of any local polarization rotation. So these are, this is the concept. So active feedback. So essentially you have to dynamically compensate for any polarization fluctuation. Robotized polarization correction has also been seen by many groups on active control system, but our approach is without active feedback. We perform a quantum state tomography, obtain the density matrix, evaluate the optimal measurement basis choice that leads to high anti-correlation, and then achieve the best trade-off between key rate, Q-bar, and symmetry. So this, I want to show you the results. So this is the one I really like. So you can see the blue dots. Those actually are measured in conventional measurement basis. So you can see as the fidelity drops with your state, this just shoots up, right? So it just goes really, really haywire. But then now if we use our method, you can see the orange dots. These are actually a flat line. So these orange dots are measured in our new technique of the optimized measurement basis. And we, have many more results in the paper, which you're happy to look at. I mean, if you are happy to look at them, I can discuss them later. So these are all the optimizations which have been done. But the main idea is that it works very well. It converts a really exploding graph into a straight line. Okay, and so usefulness is obvious. So we can correct this without having active feedback, no control systems required. It's also cost effective, because, these usual ones are resource intensive and result in additional maintenance cost. Ours, will of course serve as an important tool in both fiber-based and free space communications. So having said that, I wanted to show you the, is this possible that I'm going back again? Yeah, so I think this is working. Yeah, so you can see this is our free space demonstration. So from within the lab, we are actually projecting the photons from the ALICE side out through our telescope arrangement. This is the ALICE module, just to give you a bit of a lab tour. And so this is the ALICE module. So we come out of this window, and then we go straight across to our other lab, which is, situated some distance away, and we have our Bob module. And this distance is 50-meter distance, because RRI is full of trees. And we cannot really have a free space link without cutting down one. And that we cannot do. Our project will stop, institute will stop. So 50 meters is what we were limited to because of where we are. And of course, that is not an issue. So this was the atmospheric channel. And so these are our parameters. So you can see when we first achieved this in February 2021, we of course had lower key rate and higher Q-bar, but then we have done a lot of optimization after that, and now we have much better numbers and much more stability. But having said that, we did achieve this first in our country. And and then we went on to do something, partly inspired by all this discussion about 200 meter, 300 meter that followed, and partly also inspired by science. So we said that, let us actually simulate the effect of atmosphere over this channel and see if, even if we can't cut down trees, can we predict what would happen if we keep increasing the distance by taking the atmosphere into account. RP talked about atmosphere, he talked about, we have also not patented anything in this, but then we went on to do the simulation to see what would happen if we actually did that. And so this is, the kind of difference you would see, 200, 300, 500 even. It's not a very large drop in our atmospheric scenario. And so this is what we went on to do. We put filters at our source to induce attenuation in the photons and see how the key rate would drop as a function of distance. So as you can see, this is what we already had at 50 meters, but then with all those simulations, we calculated the attenuation required to simulate higher distances. So at this very important number now of 300 meters, which you keep hearing about, our drop is essentially 10.2 to 9.5. So it's hardly a drop. So whether you do this demonstration across 50, 200, 300, or even 500, basically you're not achieving anything new. If you go to several kilometers, tens of kilometers, then yes, of course, it will drop and you need to do a lot more to get that back. But these numbers are just numbers. So achieving it in 200, 300 is not a bigger achievement than 50. And so we prove that now through what we do know best, which is science. And so this, of course, is there. So having said that, now what we are very excited by, the last 2 slides, is the next step that we are working on for the last 1 year. So we have done free space communication between 2 buildings, but my satellite is not going to stare at me from the orbit. It's going to move. I mean, of course, that's what we want it to do. So if it moves, I need to keep pointing at it and tracking it, right? That is a very important step. How do you keep that line of sight and you keep maintaining the QKD link? And so that is what is called, the pointing acquisition and tracking system which you need to develop, so that that works in conjunction with quantum key distribution. So without that, of course, none of this is really going to be useful for satellite QKD. So we went about it in several steps. As you can see here, we have the, first thing, we use the 2 gimbal mirrors on a translational stage and a single beacon in a closed loop setup. So this is what you can see. This is the transmitter gimbal, which is stationed here, and the receiver one is moving. And I think, if you can look very carefully, and if my friends there are cooperating, you can actually see that this is a video where you can see things move, hopefully. We have been working on it since yesterday to get this video to actually work. Do you actually see movement there, my friends behind? Yeah, okay. So you can see that, this is my beacon. So we have to center it on the, photodiode. And then we have to keep doing this, back and forth feedback so that it remains centered. So this centering of this circle that you see is your indicator that you are in line of sight. And of course, a lot goes into this feedback mechanism, which we have painstakingly developed. But this is just to give you an overview from Delhi while we are in Bangalore. And so this was our first such attempt, where we did a linear feedback. Then, we went on to this beautiful demonstration, where actually we have a circular motorized arm. Okay, this is my last slide. Circular motorized arm. So essentially on the left you can see this was done completely in-house. We have a great workshop. So they came up with, basically mimicking a satellite. So a satellite is not going to move linearly either. It's going to have a circular motion. So how do we correct for circular motion? And so that is the next challenge which we took up. And so this is what you see. Now you have to really pay your attention to this big thing here, which is actually moving, and it is not moving very fast, obviously, it's moving at a certain distance. And if you keep your eye on this little circle here, then you will see that, this guy, it's the same arrangement of trying to, get the beam back to the center of your camera. But then now this is actually moving in a circular track. You can see that, I think I can see it, I hope you also see it. So this is actually, so these are all things, of course, steps which lead towards the ultimate thing. It's not doesn't happen in a day. And so with the circularized, motorized thing was very much appreciated by our colleagues at ISRO as well, because this is basically like a little demo sitting within the lab. And so now I want to leave you with this very interesting slide here, and you should hear back from us in a day or two. And so with that, I would like to also say that we are a member. So we have done a lot of things in order to make this quantum useful. And so we are a member of, we are the founding partners of the JESDA Open Quantum Institute, which is in Geneva. And so I am a member of the Incubation Advisory Board and a task force member. Whole idea is to see if we can make quantum computing useful for, things that we may care about, like food, health, and so on. So these are the Sustainable Development Goals of the United Nations. So I'm personally actually overseeing this particular aspect, and I'm learning a lot. That what we do is not all useless, in some sense. So, so this is one of my little explorations which I wanted to share with you. So with that, this is what we all look forward to. So thank you very much.
Thank you, Professor Sinha. With that, we'd like to express our gratitude to all our distinguished panel for bringing to the table their knowledge, experience, and expertise. And may I request Mr. Shashi Mohan, DDG TEC, to kindly present a memento to the chair. A memento for our chair, Shri Sanjeev Agrawal, Member Technology, Department of Telecommunications. And now I request Honorable Chair to kindly present mementos to all our panelists. Professor Joy Ghosh, Professor R.P. Singh, Dr. Bruno Hatna, is it with your name?
I don't know. You're giving me every time I talk.
Professor Urbasi Sinha.
I had enough. One is good.
Let's have a quick group photograph before we disperse for tea. You're all invited for high tea. Again, the same venues on the ground floor in the lounge for our guests and speakers, and for all the delegates on the first floor in the foyer lounge. Thank you. Kindly be back after 20 minutes. We begin our second session at 11:15. 2 minutes. Request you to kindly put your mobiles on silent mode. So in this post-tea session, we welcome you all once again. The topic of this session is security in the quantum era. This session will discuss the potential threats posed by quantum computers to traditional cryptographic methods and the need for a robust security framework in the quantum era. We will explore quantum key distribution and post-quantum cryptography as potential solutions for secure communication in a quantum world. The session will cover the current state of QKD and PQC research, as well as their practical implementation and integration into existing systems. Chairing this session is Srimati Pamela Kumar, Director General, TSDSI. I request her to kindly be present on the dais with us. Let's welcome her on stage, Srimati Pamela Kumar. I would also like to call upon all the other panelists of this session. Shri Narendranath, Joint Secretary at NSCS, National Security Council Secretariat. Shri Atul Kumar Gupta, Group Leader and Head Optical Technologies at CDOT. Shri Prashant Chugh, Group Leader at CDOT. Professor Prabhakar Krishnan, Scientist at Amrita Center for Cybersecurity Systems and Networks. Shri Swami Saran, Technical Lead at Thales. And joining us online in this session will be Tommy Lampila, Director of Business Development, Zifera from Finland. I have the pleasure of introducing the chair to you. Srimati Pamela Kumar is Director General of Telecom Standards Development Society of India and President and Founder Chair of CCICI, that is the Cloud Computing Innovation Council of India. Pamela ji was the first ever appointee from India in the IEEE Standards Association Board of Governors. I request her to kindly set the ball rolling. Srimati Pamela Kumar ji.
Speak. Okay. So now I'm audible? Yeah, okay. Okay, so welcome back after the tea session. I think we had quite an amazing and eye-opening session in the morning today. But I think all of yesterday is a testimony to the excitement around quantum in India. It's quite an eye-opener for all of us. I thought quantum was still a niche area. I think a few years back it was said that it's at least 20 to 30 years away from seeing reality. But what we've been experiencing that in India it is pretty much a reality. And amongst all the sessions, I think that reality on how we're going to, how the rubber is meeting the road is going to be discussed in this session. Because in quantum security is what is leading, and both the post-quantum cryptography and QKD are the two key areas, and we have real live examples of people who are working on this and are actually doing some trials, as well as the view from national cybersecurity on what their expectations are, and the global view on what are the kind of threats that are happening. So with that, I want to kick off the session but I would, I'm not using my 10 minutes. I'm reserving some time because I want to listen, I want to understand, and then I want to conclude with some concluding remarks. So thank you very much.
So virtually present with us here is Tommy Lampila. Can we have him on screen? He's a partner and director of business development at Zifera Limited, a Finnish company implementing cryptographic solutions for FPGA and ASIC circuits. He has more than 20 years of experience in cybersecurity industry, including SSH, communication security, and in leading technical security services at KPMG, Finland. Mr. Tommy Lampila, can you hear us?
To everyone. So I will be discussing today the imminent quantum threat and the implementation of post-quantum cryptography on hardware. The quantum threat refers to the fact that in due time, as quantum computers become powerful enough, they will be able to break public key cryptography, which is the foundation of our entire information security infrastructures at the moment. So Shor's algorithm will be able to break discrete logarithms as well as factoring, which are the mathematical problems that are the foundation for public key cryptography, the elliptic curves and the RSA algorithm. Luckily, Shor's algorithm does not apply to symmetric cryptography, although Grover's algorithm can be applied. Doubling the key size to 256 bits is enough of a protection for the time being. So that's, of course, the recommendation to use AES 256 for the time being. So what can we do about the quantum threat, and why is it a concern today? Well, as far as we know, quantum computers today are not yet cryptographically relevant, meaning that they're not able to break current public key cryptography with the current key sizes. However, the equipment that we design and deploy to the field today will need to stay operational for long life cycles, maybe even decades. So they need to be secure throughout the life cycle. Also, the concern is that malicious actors, such as nation states, maybe likely are targeting already today interesting internet traffic and data and storing it, capturing it and storing it, with the intention of breaking it when they have powerful enough quantum computers in their possession. This being the record today, break tomorrow threat model. So we should be already protecting the data of today that we want to keep confidential and private for the next years to come, decades to come, or through our lifetimes. And what are we doing about it? So post-quantum cryptography refers to cryptography that cannot be broken with quantum computers, asymmetric cryptography that cannot be broken with quantum computers, but that is implementable on traditional computers of today, like the laptop that I'm using to present here today. It is based on mathematical problems that are difficult, luckily not only for myself and traditional computers to solve, but also for quantum computers. These different types of post-quantum cryptography and mathematical problems are grouped into lattice, multivariate, hash-based, code-based, and elliptic curve isogenies, which I will not be going into detail in today's session. NIST, the National Institute of Standards and Technologies in the US, has been running a competition-style process for standardization of post-quantum cryptography. The competition has now reached into its fourth round. The winners of the round 3 have been announced this past summer in July. 4 algorithms were added into round 4, and the call has gone out for further new signature algorithms to be entered into the competition. The expectation being that the first standards will start to take shape at the end of this year, 2024, and from 2024 onwards, the standards will be evolving and additional standards will be created. What this means for us, seeing as we are already being told that we should be implementing post-quantum cryptography to protect the data of today and tomorrow, especially when considering hardware implementations, is that crypto agility, being the ability to upgrade and update your cryptographic implementation, is a must. And when it comes to hardware solutions, FPGAs, field programmable gate arrays, do have an advantage in that they are indeed programmable. They can be updated in the field, and you can update and upgrade your cryptographic implementation should new algorithms need to be added, or the existing algorithms be tweaked, or even deprecated as time goes by. So the winners of the this round 3 were the Crystal's fiber algorithm for key encapsulation, and the Crystal's Lithium Falcon's Finch algorithms for digital signatures. The round 4 candidates were quite classic meddles and H2C, and unfortunately for this site, it was broken quite late in the game and had to be dropped out. Now, when considering implementation of post-quantum cryptography on hardware, we can take a look at the key sizes and ciphertext sizes for the key encapsulation algorithms and compare them to elliptic curves, the traditional and current public key cryptography for that purpose. And what we can see when examining the key sizes and the ciphertext sizes, that in the various algorithms, they do indeed grow quite considerably. And in terms of hardware implementation, this implies that there will be a larger communication and storage overhead that has to be taken into account when designing the hardware. On the other hand, as a piece of good news, latencies will likely stay similar or even become slightly faster than when compared to traditional algorithms. So we don't have to worry about speed as such. Looking at the signature algorithms, while the key sizes do grow, especially for some algorithms quite considerably, for others a little more moderately or even staying the same, again the signature sizes will grow quite considerably when compared to traditional elliptic curves. Again, it means that there is a communication and storage overhead to be taken into account when doing digital design for hardware. But also we do expect that the signature landscape for PQC will change when the algorithms enter the competition in round 4. So on the one hand, we are being told that we should already be protecting our data today with post-quantum cryptography. On the other hand, the standards are still taking shape and taking form. And also the post-quantum crypto algorithms haven't seen the same amounts of mileage and scrutiny that traditional public key cryptography, which has been around for decades, has. So we need to take into account the risk that something will be, unidentified, vulnerabilities or weaknesses will be identified late in the game in some algorithms that maybe even have even been selected for the standards. And for this purpose, many entities, for example, ANSSI in France, recommend using a hybrid crypto system for a time being, meaning that you combine both traditional public key elliptic curves with post-quantum cryptography into a hybrid crypto system, using them in conjunction with each other. Meaning that if one of them fails, for example, traditional elliptic curves are being broken by quantum computers, or the new PQC, one of the new PQC algorithms is found to be vulnerable late in the game and broken by quantum, and vulnerable, then you will still have the other to fall back curves will not be going away for a long time. And honestly, for example, recommends using this hybrid cryptography until 2030, at which point in time we will perhaps start to be able to consider the PQC algorithms as being having the same level of trust as traditional public key cryptography. So Sarkera, our company, which is based in Finland, specializes in implementation of cryptographic algorithms and protocols on hardware, being FPGA and ASIC circuits, which we deliver in the form of cryptographic IP cores. We launched our Conclave family of PQC IP cores in December with the first product and implementation of the Crystal Skyler algorithm being released in January. And we will be expanding the family with Crystal's Lithium in the upcoming months, as well as other expansions to the solutions. And all of our implementations are based on the latest standards, or what is the latest draft of an emerging standard. So the takeaways from my session today is that elliptic curves will live alongside post-quantum cryptography for years to come. In terms of designing hardware solutions, crypto agility is something that we do need to take into account, and this is where FPGAs do have an advantage in the design and implementation of a solution, which is something that crypto agility is something that fixed solutions, ASICs, and trusted platform modules lack in the same form. We can expect that the algorithms will be, or the standards will be, or the first versions will be finalized in maybe 2 or 3 years. Quantum cryptography, on the other hand, which refers to cryptography performed on actual quantum computers, for a time being is likely to stay a niche application for research and, for example, point-to-point connections on dedicated links. That concludes my session today. If you have any questions, you can send them to us an email. And thank you, and hope you all have an interesting conference.
Thank you, Mr. Lampila, from joining us from Finland. Well, our distinguished panel here has Shri Narendranath Gangavarapu, an officer of the Indian Telecommunications Service, is working as Joint Secretary, National Security Council Secretariat, with responsibilities for coordination in matters of cybersecurity activities by different entities of India in the government, public and private sectors. He's also driving the initiative on the trusted telecom supply chain. He's the coordinating chair for India for the Quad Critical and Emerging Technologies Working Group, focused on diversifying 5G supply chains and obtaining leadership positions in emerging technologies of biotechnology, AI, and quantum technologies. He drives the cybersecurity R&D fund and has over 30 years of telecom experience, including 20 years of senior management experience in the areas of telecom security, network planning, installation, operation, and maintenance. He was associated with TSDSI as a member of the GC and was also director on the board of Tata Communications Limited and is currently on board of NIXI. I request him for his keynote address.
Thank you, ma'am. A very good afternoon or good morning. You know, we've had a whole day yesterday and nearly half of today on quantum technologies. I'm no expert on quantum technologies. As I was saying, I was just talking to one person there, that, you know, we deal with all critical emerging technologies. I talked of biotechnology, artificial intelligence. You can't be an expert in all of them. From our office, what we look at is, you know, the implications of all these technologies, especially with respect to national security. And in the current scenario, we find that advanced technologies have a bearing on national security. You know, getting leadership positions in advanced technologies is very important. And you would find that those countries which have obtained leadership position in advanced technologies are the ones that are actually, I wouldn't say ruling the world, but having the say in the matters that matter in the world. So with that perspective in mind, quantum technology is one important technology where we have to have a leadership position. And that's where we also work with industry. We work with different wings of the government and the private sector to see how is it that India also develops, the complete hinterland of India also develops in terms of developing the core competency for understanding those technologies and also having the products and services that are riding on those technologies coming forward. So one important part that we're concerned about, especially regarding technology, is the technology supply chains. And when we look at the technology supply chains, we look at the technology per se, that how do we have access to those technologies, where it is at much more advanced stage than where we are currently. And if we do not, then how do we get access to those technologies? How do you work with like-minded countries to see that, we work with them to see that there's a transfer of technology, or combinedly we develop together in those technologies. That's one area that we look at. The other is the materials that go into these technologies. So one is, of course, a lot of raw materials, equipment, all of that. So the access to that, how are the export controls working in those areas, and then again working with like-minded countries to see that we have access to those materials in that one. And the final, of course, piece in the puzzle is the manpower, the skill sets that are required. And especially when, I know many of us, some of you are experts in quantum technologies, many of us are in this room to understand what is quantum technology. And you would have found that it is not a simple subject to understand. Classical technologies are quite simple. You can make an image of what it is. But quantum technologies, we must have done engineering, a lot of physics and all of that. We must have read Schrodinger equation at a particular point of time. But still, it's difficult to visualize that. And after such a lot of period of time, when we have not worked in those areas, to understand it's very complex. So getting the level of manpower, that is the tipping point for things to happen in a country, is very important. It's not that we have isolated one or two people or experts. It's that we have to have a tipping point that, and especially for a country our size, we should have spread across the country in multiple institutions, not in single isolated institutions that this manpower is resident. So how do we, have this manpower development across all of the institutions? How do we, enable collaboration amongst them that the development of manpower happens? So there are many, one is within the country there's some effort that's happening. And bilaterally and multilateral also we work. And in the Quad, for example, that we have this Quad Fellowship program that we have started for critical emerging technologies, where around 100 people are being sponsored to, get trained over a 2-year period in postgraduate, level in the critical technologies. So this is one area. The quantum communication interministerial report that's been prepared is one very good exercise that's happened in this regard. One, because it has given us a good visibility into what is of the current situation. We know, who are the people who are there. We know that which are the companies that are working in their area and what are the products that are available. And that is something that was not, if you look before the report and after the report, it's like pre-COVID and post-COVID we talk about. We could talk in terms of pre that report and post that report. We currently have a good understanding of current scenario. And we were discussing about that in some of the context in, for example, PSS office. And we were thinking that similar type of report is required for in the computing space also, in the compute space also, where currently we don't have that much of visibility about where we are. I think that's one area I think we have to really work about and get, so that we have the complete canvas of all the quantum technologies that are there, and we have then you will find that we could have targeted interventions in terms of where is the intervention that's required for actually to have the maturity in these technologies. So that is one part. From the NSCS, it's around the last 3 years or something, we've been in discussions on quantum technologies, and we've been talking to various institutions. CROT is one institution we talk about, and certain other institutions also, like ISC Bangalore is one. So we've been talking about working in these areas, and then asking them to identify. The process that we follow in the R&D is that we get the user agencies together and try to ask them what are the problem statements that you have, and then try to identify the institutions with whom we can work to solve those problems. So quantum was one area that was identified as a problem statement because of the various things that have been talked about. That post-quantum, the data encryption, that it will be broken, and the problems that will be there, key exchange problems which are there, and all of those things are there. So looking at that, I'll say that initial part there was some issues in getting those projects through, because we were having this graduation of having that quantum mission and all of that. So we were trying to dovetail everything into that. But later on, then we decided that there should be some amount of delinking that should happen, because two things can happen parallelly. We can have a grand vision and then have a big program. But simultaneously, as you identify the problems where the work has to happen, we could start working on the smaller things, so that we have people getting together and that capacity also developing. And then you will find that the ecosystem will develop, and when you have the mission statement, you will find that you will have the people there to work on those mission statements and quick delivery happening. So that way, from our office, we have worked in various areas. We have worked with QNU Labs also. As Hub and Spoke, which you see there, is one that we have worked with them. The voice, quantum secure voice video phone is another inline encryptor, and key distribution. So various areas we have actually sponsored. One, Mr. Sai is sitting here. So one is on messaging applications and using quantum technologies in that messaging application also. So these are areas that we have tried to seed, some areas where people start working on these technologies. One of the concerns that is expressed is regarding that harvest now and decrypt later. That's one of the biggest concerns that's been expressed. And for us, it's a big concern, because data could be harvested today and then somebody could decrypt it later. How do you prevent that? So how do you prevent is, the only way you can prevent is that forget quantum. We have to use classical techniques that we have today to see that unauthorized access to data doesn't happen, whether it's encrypted or not encrypted. Because even if it's encrypted, because one of the things that we really talk about is encrypt your data and store it. And we ask everybody in the data centers, kindly encrypt and store it. But what you say is, if you are going to harvest today and decrypt later, then encryption is not going to work. So it means you have to think beyond that and say that, okay, how do I prevent unauthorized access to data? And that is one thing we have to really take it serious and to the next higher level, and to see that how do I have my access mechanisms of authorization and access to see that the access doesn't happen to unauthorized entities. And that is one, I think, as a community, we should ensure that we design and build our systems to prevent unauthorized access to data, because of what are the consequences of the decryption that will happen later. So that is one point I just wanted to make, and this is something that we are stressing with the people we are working on that. The other point that comes is regarding the security of the quantum products and the deployments that happen. So we are talking of key exchange, and that the key exchange is such a way that you will not be able to detect the key. But if I'm not going to go to that channel and then try to detect it. I'll go to the end places where the key is getting generated, and I compromise that end system, and I have access to the key there. So how is that end system where the key generation is happening? How is it secure? Because any system that you are generating, you are having, the complete key life cycle management is there. You are going to generate the key, you are going to store the key somewhere. You have the user and object management, user of those systems who are there, then management will be there, the monitoring and configuration systems that would be there. So how are they all secure? So is it possible for me to access those systems where the key generation happens and then get access to the keys? So that is something I think people who are talking about quantum, developing quantum systems should also get into this area of trying to ensure that the end systems where the key generation is happening and the key lifecycle management is happening, where the user management, the monitoring systems are there, the centralized monitoring systems, how are they secure? So that is one aspect I think that is a work in progress, and people have to look at it. The other is, dwelling further on the topic, is in this security requirements. Based on this, that is understanding that you have to secure these systems also. Your understanding of coming of the security requirements for these systems based on the use cases, the different deployment scenarios that happen, then you'll have to have a security analysis for the key distillation methods, the PQC algorithms that are there, the key storage and distribution, then the API support that will be required for the random data that gets generated before it gets into key generation and all of that. Then the web and command line interfaces that you would put in place for HTTPS and or SSH for doing that. So, and then finally, how do you integrate with the legacy systems? So where all of these which are there, how do I have security requirements for all of this? So that is one body of work I think as an industry or the academic community should start working on those requirements, so that then the products get designed as per that and we have a certification mechanism to say that yes, they are certified as secure products. Okay. And finally, of course, the verification and claims, standards and certification. I think the last slide that was put after what he was talking of standard certification and standardization. Now that we have identified people who are there in this room, I think one is working in aware areas is very important. But I think you should also start participating in the standards activity. So, and identify the standards bodies which are there, and then so that our own requirements and our own understanding of how the systems are to be developed are incorporated in those standards bodies. So with these words, I thank the organization for the opportunity. And from our perspective, these are some issues that we hope the academy and the industry will address. Thank you.
Thank you, sir. Our next keynote speaker is Shri Atul Kumar Gupta. He's the head of Optical Technologies Division at CDOT and has experience of more than 30 years in design and development of optical communication-based products and has worked in design of SDH-based systems, fiber access systems, GPON, and DWDM. He is leading the development of quantum key distribution systems at CDOT. Shri Atul Kumar Gupta, please.
Very good morning to everyone. Yeah, so much of what I'm going to talk now is already covered, so I will be very brief. This is the basically this is the agenda, a bit of introduction and what are the challenges. These are already covered, so I will cover it very quickly. This will be followed by QKD protocols, the ITU standards, what are the QKD related activities at CDOT, applications, future scope of development. So just to briefly revise, the cryptography can be divided into two verticals, symmetric key and asymmetric key. And symmetric key cryptography actually uses asymmetric key for the purpose of distribution of key. And the asymmetric key cryptography, which uses public key and private key, two different keys for encryption and decryption, that is at risk because of the advancement in quantum computing. And because of this risk, the risk gets transferred to the symmetric key cryptography as well. And that remains no longer secure in case there is a compromise of the key distribution. Keeping that in mind, QKD is fast evolving, quantum key distribution, and we saw this earlier also. QKD is a mechanism to provide information theoretic security to the keys. It is not based on any assumption or any belief. It is mathematically secure, and it is not dependent on the computational power at the hands of the eavesdropper as well. So these are the present day challenges. The most important challenge is that the intrusions, they remain undetectable. So if somebody is tapping on the channel, there is no way to know whether the tapping is actually taking place or it's secure. So what quantum mechanics brings in is that the intrusions, as and when happen, they gets detected, anomalies created which can be measured, and then alert can be issued to reroute the traffic or to stop the traffic from before it gets compromised. So with this, this is typically a point-to-point configuration on the left side and a network view on the right side taken from ITU. So point-to-point is pretty simple. There are two nodes at each end which are connected through some channel, which can be free space or fiber optics constituting quantum channel as well as classical channel, and the purpose is to provide identical secure random keys to the application entity, which can be an encryptor or a router, and that key is used for encrypting the traffic which flows on the network. So if there is any eavesdropping attempt on the data on the channel which is carrying data, that's not going to succeed, primarily because the key is not known. And if an eavesdropping attempt is made on the channels, be it the classical channel or the quantum channel of the QKD, that will also not lead to any information regarding the key. If the quantum channel is tampered with, then that anomaly will get detected. But point-to-point configuration is not enough for the purpose of network. So it has to actually cater to a telecom network which will be existing in multiple topologies, whether it is a ring or a star or mesh topology, and the QKD has to support it. It has to overlay over the existing telecom network. The telecom network itself cannot be changed because of QKD, but the QKD has to support all the topologies which are there, and that is what is the intent with which ITU is coming up with all the recommendations. So just very briefly, the QKD can be divided or can be differentiated based on two possibilities. One is how the quantum states are generated and decoded. So there can be a continuous variable QKD or discrete variable QKD. In case of discrete variable QKD, we can have distributed phase reference as the mechanism where the information is encoded in the time or the phase of the weak coherent pulses. In case we can also differentiate QKD based on the architecture of protocols, which can be prepare and measure, measurement assisted, and entanglement based. These all were discussed earlier. So in case of measurement assisted, basically the objective is to further strengthen the security that is provided by the keys which are generated using QKD. So this is what we are working currently on the measurement device independent QKD. The traditional QKD implementation, which is point-to-point or even when scaled to a network, has certain issues as far as side channel attacks are concerned, which can be exploited by any eavesdropper to get some information regarding the keys which are being generated by QKD. So those can be actually addressed by using something known as a measurement device independent QKD that will take care of the imperfections in the measurement device. Imperfections can be there on the transmitter side also, but that are easy to address. But addressing imperfections in the measurement device is a little bit tricky, which requires a different implementation. So we have started work on the measurement device independent implementation of measurement device independent QKD, and the difference it brings in from the technical complexity point of view is to ensure that from two different locations the signal reaches the common node precisely at the same time with the same wavelength and with the same polarization. So if that can be addressed, then measurement device independent QKD is a better way of generating keys, secure keys, instead of a typical point-to-point implementation. Now, another aspect is the continuous variable QKD, which is supposed to be better in terms of cost effectiveness from the purpose of large scale proliferation in the network. So as it doesn't use a single photon detector, so it uses more of telecom grade components which are already there, being produced in large numbers at a reasonable cost. So for smaller distances, for a metro network, probably CV QKD might be a better solution. Keeping that in mind, CDOT is requesting applications from experts for a collaborative development of CV QKD. More details are available on CDOT website. So for all the experts who are interested, I think CV QKD, indigenous development of CV QKD can be done through a collaborative effort with CDOT under its recently released CDOT's collaborative research program. These are just an summary of ITU standards for QKD. The basic intent of showing is the ITU has not very long back started work on standardizing QKD, but even in a short time it has come up with number of standards, and more standards are getting generated. It is covering all aspects of QKD from the perspective of large scale proliferation in the network, keeping so that dependence on individual vendors can be removed, and to the extent possible interoperability can be ensured. This is our solution. I will request for a visit in the exhibition area where this live demonstration of the solution is taking place. So what we recently did is also to address the issue of non-availability of dark fiber for QKD implementation. Since we already have a solution which generates 100 gig of data, multiplexing multiple lower rate signals like 10 gig and 1 gig. So we came up with a solution where a complete dark fiber free implementation of QKD is possible through a totally indigenous solution with 100 gig of traffic carrying on the same fiber. So it won't require any special third fiber for the implementation of quantum channel. One pair of fiber is sufficient for data, quantum channel as well as classical channel. Of course, there is a limitation in terms of the number of distance, the amount of distance it can cover. So, but for greenfield application, this is going to be a better solution. For existing network where the fiber is already lit with some data, be it at C band or S band, a customized solution can be given where the QKD can coexist with the existing traffic carried on the fiber. So these are some applications. I think these have been already discussed in detail earlier. So the existing network, it can be upgraded with quantum security by putting the quantum nodes at each egress and ingress points, where the traffic will get encrypted with the keys which are generated by the quantum nodes, and then it can be upgraded to provide quantum security. So this is sort of an overlay which can take place on the existing network. So some of the things to ponder upon. QKD solutions are proprietary because it is not possible to interconnect one node from one vendor to another node from a different vendor. Of course, key relay can be implemented, but there is no interoperability as far as Alice to Bob sort of a connectivity is there. So this is one issue which probably will get addressed as we move along and more standards gets formulated. And so, keeping in view certain side channel attacks, measurement device independent QKD is getting popular. Further down the line is twin field QKD, which can provide better key rates at much higher distances. And then finally, chip-based implementation is certainly necessary. We saw some of that yesterday also, to bring down the cost, power consumption, operating temperature range, etc., and to ensure that more deployments can take place at a faster pace. So this is just to summarize that the threat is posed by advancement in quantum computing to the data, and large-scale deployment of 5G will further complicate the situation as far as security is concerned. So QKD addresses this by information theoretic security, and there is plenty of scope for novel algorithms as well as multi-vendor interoperability. C-DOT is actively pursuing the development of field deployable solutions in this area, and it intends to play a leading role in the national mission. Thank you very much.
Thank you, Mr. Gupta. Well, our next keynote speaker, Shri Prashant Chugh, is also from C-DOT. He has more than 26 years of work experience in telecommunications R&D and is currently leading the development of post-quantum cryptography-based encryption products in C-DOT. Shri Prashant Chugh.
Thank you, ma'am, for the introduction. So, good afternoon, everyone. So, the topic is post-quantum cryptography systems. So, there are a number of sessions on post-quantum cryptography, a number of talks in this session, and after this session also we have on the ETSI and the NIST standardization. So there will be some repeat, but I think that repeat would be good, in fact, because quantum is a difficult topic. So post-quantum cryptography systems. So as you have been, we have been listening in the whole seminar since yesterday that there is a quantum threat to the cryptographic systems. All the current cryptographic systems are under threat from the quantum computers and the quantum algorithms running on quantum computers. And this impacts the communication systems as well as the storage systems which are using cryptography. And this is the threat is because of the fact that certain classical cryptographic problems which are difficult or impossible to solve using conventional computing are expected to be solved trivially using quantum algorithms. And this situation can lead to a crypto apocalypse type situation if mitigation actions are not planned and executed. So that's why in the news you have so much about the quantum threat to cryptographic system, and that's why this conference and all these things are happening now, so that we suddenly do not land into a crypto apocalypse type situation. And as previous speakers, Atul has also mentioned about public key cryptography and the symmetric cryptography. And so both are under threat, but the experts are saying that the symmetric cryptography, the strength will become half. So if you can double the key size, it might be okay. But the asymmetric cryptography will be completely broken, and so definitely complete solutions are required for new algorithms in asymmetric cryptography. So RSA, ECC, and these experts are saying will be completely broken. So now the communication protocols which are under quantum threat, they include IPsec, SSH, TLS, VPN, HTTPS. So this practically includes all the protocols over which secure communication is happening currently. And as Mr. Narendranath also mentioned, and the previous speakers mentioned about harvest now and decrypt later attack. That is, you save the data now, even the encrypted data you can save now and you can decrypt later, because the data which is encrypted using current encryption algorithms will be broken when stronger quantum computers are available. So definitely, as Mr. Narendranath mentioned, that preventing unauthorized access is required. Also, another thing which is suggested is encrypted using hybrid cryptography, which I am coming to the next line. So this harvest now and decrypt later and these all attacks, what it means that all your previously encrypted information, banking information, identity information, and important sensitive information whose shelf life is long, that can be saved now and decrypted later. Of course, there is a lot of information whose shelf life is not long, where this will not matter. So now coming to what are post-quantum cryptography systems. So the security systems that use a new class of cryptography algorithm solutions which are based on different hard to compute problems. So all cryptography algorithms are based on hard to compute mathematical algorithms. So when we are saying the classical cryptography, those which are based on the current mathematical problems, they are going to be broken. So the research is happening, the competition is having is to have new mathematical problems, and all the algorithms are based on new mathematical problems which will be hard to compute. And these algorithms, post-quantum cryptographic systems, they are implemented on today's classical computers. They are not implemented on quantum computers as some of people misunderstand. So they are implemented on classical computers, but it will be resistant to attack from tomorrow's quantum computers. So NIST is having a PQC algorithm, the post-quantum cryptography algorithm competition for a number of years, in the sense that the standardization of cryptographic algorithms generally takes a number of years. Algorithms like AES have been standardized over a number of years, and there are a number of rounds in that competition, and in each round certain candidates are eliminated and certain candidates they move to the next round. So in the end of third round, lattice based, which is again, lattice is a class of mathematics problems. A lattice based crystal Kyber algorithm has been chosen for standardization for key encapsulation mechanism, and 3 algorithms, crystal dilithium, which is a lattice based, Falcon, which is a lattice based, and Sphinx plus hash based, have been chosen for standardization for signature algorithms. When we mention that they have been chosen for standardization, means currently they are not standardized. So certain improvements, and specifically in terms of certain parameter tuning and all, will take place, and then these standards will be published on these. And many algorithms have been eliminated, and certain 3 algorithms like BIKE, which is code based, and classic mechalis, which is code based, and HQC, which is again code based, have been moved to the next round. That means for further analysis in the next round. So the first column are the algorithms which have been chosen for standardization, while in the second column are a few algorithms which have not been rejected, but which have been chosen for further consideration, further cryptanalysis to happen on them. So in the next session we have a talk by Dustin Moody, so I think a lot more clarity will be there. Now for post-quantum cryptographic systems, where I'm talking about the systems, so post-quantum cryptography, we have understood the mathematics behind it. So when the systems are there, so what are the use cases for these systems? So the obvious use cases are, we want to secure our critical voice, video and data communications and storage, and we want to do this in our legacy networks as well as the greenfield networks. And some of the implementation guidelines which I advise for the potential developers of such systems is that such systems should be having driven by standards, and the PQC standards are being driven by NIST. So NIST PQC standards driven systems should be there. And then the most important is that the systems should support hybrid approach of quantum safe migration. So what is this hybrid approach? Hybrid approach is that you combine the key which has been generated through key exchange algorithms of under standardization NIST algorithms with the key exchange, with the key which has been derived from a key exchange algorithm, which is a classical algorithm like ECC. So this hybrid algorithm has been suggested by NIST as well as by ETSI, Quantum Safe Cryptography Working Group. And we, in fact, in the next session, we have a talk from ETSI speaker as well. So we would be coming to know more about the hybrid approach. So it is important that when the new standards are not final, so in the phase of migration to post-quantum cryptography, we need to follow a hybrid approach, where one of the algorithm which has been used for key generation is a standardized algorithm, which has got standardized over a number of years, and the other, which is an under standardization top candidate, but still not standardized, so combine those keys together. And also another guideline for developing such systems is that they should support crypto agility. Crypto agility is that you should be able to change the crypto algorithm in a fast manner. And our next speaker is definitely going to speak about, Professor Prabhakar is going to speak about PQC migration crypto agility. So we will come to know more about there. So in CDOT, we have a PQC based communication systems development which is taking place. And we have, our focus is on basically two types of, two subgroups. One is the PQC based IP layer encryptors, other is the PQC based end product. So in the category of PQC based IP layer encryptors, the low capacity, commercial high capacity, and then ultra secure. And in the PQC based end products, we are focusing currently on the customer premise equipment like video IP phone. So in our, these all our products, the compact encryptor and the video IP phone are in fact available in the exhibition area. So I would suggest you can have a look there. So our compact encryptor module that supports NIST PQC key exchange algorithms, and it is useful for securing data communications over internet across geographically distributed sites. And this particular device, which is currently displayed, is supporting up to 80 Mbps encrypted traffic, and it supports hybrid mode of classical and PQC algorithms combined, and it also supports crypto agility. This slide displays a use case scenario of PQC IP encryptor where two private LANs are connected over a public IP network using this encryptor. Then we have work under development for commercial high capacity post quantum IP encryptor. So where we have want to increase this the throughput to 1 Gbps, which is scalable to 10 Gbps. And again, NIST post quantum key exchange algorithm, and that is the criteria, the guidelines. And then we have operations performed in FPGA for better security and performance. And then we have tamper resistant enclosure and side channel analysis attack resistant implementations, and commercial FIPS 143 standards supporting, and again in hybrid and crypto agility mode. These are the guidelines there. Then we have an ultra secure high capacity post quantum IP encryptor. Again, it is at a high rate, and there we also plan in future to have proprietary post quantum key exchange, as that is the need for some of the defense agencies. And also we have the tamper resistant enclosure and side channel attack resistant, and the platform security guidelines as per the defense guidelines as given by Cypher Policy Committee. Then for the customer premise equipment, we have this quantum secure smart video IP phone, and these are some of the features. For the cryptographic features, again we support all the standard guidelines which I suggested for the crypto systems. This is a use case scenario, the network diagram representing how you can make a call using this video IP phone. So in front of SIP server, we are having again our compact encryption module. So all the signaling which is taking place between the phone and the signaling, the SIP server, that happens over post quantum key exchange. And on one side, it's implemented in software in the phone, and the other side it is in the encryptor box. So to summarize, all future voice, video and data cryptographic security systems should support algorithms which are as per NIST PQC standards. And during migration phase to post-quantum cryptography, all security systems should support hybrid-based approach for PQC algorithms and should support crypto agility. So that's all from my side. Thank you. And just I wanted to mention that we are having a number of talks of QKD and PQC, and some of you might be confused whether QKD is a better approach or PQC is a better approach. And then certain countries are also having a focus on QKD, and certain countries are saying that they will focus on PQC only. So I think the way forward is to work on both. So CDOT is working on both QKD as well as PQC, and we also have a mechanism of combining that. No, so we don't know much about what will happen in future, whether all PQC will be broken or QKD will have certain side channel things and constraints. So we have to work on both QKD as well as PQC, and we have a way to combine them. That's all. Thank you.
Thank you, sir. I would now request Dr. Prabhakar Krishnan for his keynote address. He's a research scientist at the Department of Cybersecurity Systems and Networks at Amrita Vishwa Vidyapeetham, India. He has over 2 decades of industry experience in the USA and 10 years of academic R&D projects in cybersecurity. Dr. Krishnan regularly speaks at international symposiums and workshops for the Indian Quantum Roadmap Deliberation and is a core R&D member of the Quantum Techade as a key stakeholder in taking India forward in quantum technologies. Dr. Prabhakar Krishnan, please.
Namaste everyone. Thanks for the kind of introduction. I thank DOT, the tech department specifically, and the friends at CDAC for inviting me to this deliberations on quantum communication technologies. So here we've been last 2 days we've been talking several months we've been talking about what to do and why to do. The case is made, the business case is made, the technical case is made. Now how to do it. So it's a big topic. It should be a separate panel discussion on how to do it, how to migrate, how to transition our existing legacy systems to post-quantum secure systems. And brief introduction about Amrita. In the cybersecurity, we try to guarantee the triad, we say the confidentiality, integrity, and availability. So confidentiality is what we are talking about, how to encrypt data, how to make sure that we establish secure channel to transfer data, and then other things like integrity is having error correction or checksumming in the channel, or it could be the availability is about access and something that Sri talked about. So Amrita has been doing a lot of work last 10 years in this area, not only that, and also about the ethical hacking. So during the conversation yesterday, I think we had talked about the hacking, how to make sure that current existing systems are proof, security proof, and so ethical hacking and other stuff is very important. Research at Amrita in this quantum on different accesses, and then specific to the context of quantum communication, I would say we are working on PQC standardization activities, how to verify some of the test suites and different usage domains, and then QKD in the classical post-processing, we are doing some research in it, and obviously the crypto agility. So this outline is post-quantum security, and then I'm going to sketch a map on my views on migrating, how to migrate to a post-quantum world, and the new thing paradigm that is coming up in the development security world is about developing the system, software, and hardware, which are agile for future updates and upgrades. And then I'm also going to introduce the new frontiers in cryptography, how it is relevant for us to keep in mind the transition into the post-quantum, and then with the concluding remarks. So the case is made that quantum threat is real, and then how to handle the current situation when cryptographically relevant computers are still a decade away. And then not to forget that we are making a lot of developing, adding more and more legacy stuff to every day. So like earlier speakers talked about how to address the post-quantum security, the two well-known paradigms that we are talking today is using the mathematical techniques. We developed the post-quantum cryptographic mechanisms, and the quantum key distribution is one method how to handle only the exchange of keys. And of course, the data transfer will still happen on the classical channels. So previous speaker talked about the advantages. Quickly, I'll run through it. So advantage of PQC is very readily we can upgrade without no major equipment or hardware upgrades, and then it is very fast. And then disadvantage, obviously, lots of things are going on, many standards, many people are working, so many candidates there, and there is no really rigorous cryptographic security proof, we say in the cryptographic world, to validate the existing algorithms. QKD, as you know, it involves equipments. It works on the physics, and then obviously a lot of optical components and many things are involved, and it's time consuming too. This I will rush through because this is the genesis of our whatever we have been talking last 20 years, 30 years. The Shor's algorithm 94 and 96 about the from the Gruber's algorithm. Here achieving post-quantum security is many challenges, what to choose, QKD or PQC. Whether PQC is selected, many categories are there, lattice, isogenes, and hash-based, what to choose, which algorithm to choose, And then even the colleagues at the quantum computer, they are having some different paradigms about superconductor or optics or photonics, ion traps and all that. So everybody is having, some kind of decisions to make. And the other challenge is then it should be, as we know, the whole business today runs on security and then cryptography. How to make the transition smooth and seamless. There are some challenges. Probably the investment we can make can gradually increase as the threat perception increases from the business point of view. PQC transition, as you know, today is an unprecedented move. We are in a very, just like Y2K, where we had to upgrade so many live systems. So we are seeing the similar thing today. It is not just a drop-in replacement today, because our systems are not, classical systems are not built for upgrades and updates seamlessly. So simple and well understood classical is probably easier, better, we can say. That's why we are working on deliberating on the PQC, which works on classical methods, which we understand, like math, we understand really well. So how do we begin? So I think whenever we try to do something, we take a stock of the current cryptographic assets in the infrastructure. So just like the previous speaker Sri Narendra talked about, so we have to address the kind of end-to-end large big picture of the applications to the host nodes and the libraries that we use, and then the hardware that we are using, the firmware there, what kind of a booting, secure booting infrastructure we have, and then the clouds today, and many of the current modern applications are using clouds. They deploy. So how do we ensure that all the applications deployed in the clouds, and how the key inventory, like all the HSMs on key storage and the rotational policies, long-term keys that are stored there, how do we secure that? So these are some of the aspects we have to look at when we do that. Okay, so this is from the PQC migration handbook given out by ATSI. So they talked about the level of urgency of migration for all these algorithms, and across they compared with the features and speed and memory requirement for transitioning all these algorithms. So light green to all the way to the red is like red, as you can see the elliptical curve, and RSA is very urgent today to migrate. So some of the considerations I want to present here is when we try to do the transition process, we look at the algorithmic complexity and then hardware complexity and then performance in the network. So if you look at the algorithmic performance, obviously the memory usage, the power consumption, the computational complexities, execution times come into play. And as you know, the PQC algorithms bring in more text size, key size is higher, and then more computation intensive. And the hardware point of view, how these PQ algorithms play out in the specialized hardware and the resource constrained devices we have today. And the network side, as we all know that if we increase the packet size on the wire, obviously it's going to take more time. And then the current networking devices like routers and switches and firewall appliances and many other network functions that are happening in software and hardware in modern infrastructure are tuned rather for the current classical algorithm. So how can we tackle all those implications is something we have to look at. Security consideration, in contrast to the well understood classical like RSA and ECC, it is the PQC candidates are less understood, and then we have a lot of knobs there. As you can see, lattices bring in some dimensions to that, and the code length and dimensions for code based schemes in the classic McLeese, for example. So understanding the trade-offs between security and algorithm complexity is very important. And though NIST tries to address the efficacy of the algorithm, they don't talk about these axes out there. And implementation, as we know, right off the bat, we keep repeating the same thing, that all the PQC has got heavily loaded with more higher key size, and then we have the problem of integrating the PQC into the existing software stack. where it has to integrate with the operating systems, the buffering mechanisms, and then all this secure coding principles come into play here. How do we handle the buffer overflows out there? How do we handle the system software stack? How do we handle the syntactic and semantic problem complexities in the software programming language and hardware language as well? So how can implementation help to guard the side channel attacks and code injection and many other things that we normally see in PQC implementation? We also have to look at the implications of migration in all different angles, not just about algorithm. It's all about deployment and the application centric way. On the right, you can see some of the usage domains are called out, like TLS communication protocols, TLS, SSH, IPsec, and then it could be digital signature schemes, and it could be a PKI, it could be authentication protocol, it could be IAM, or it could be KMS. So, and then if you look at the deployment platform, it could be the regular web-based computing, or the mobile computing, or IoTs and clouds and trusted computing architectures like TPMs and all that. So, if you look at these implications across domains, there are a lot of requirements come out, and then how these considerations play out in various cryptographic implementation is important. And how do we get there? Sorry, I think this is not legible. That's for a reason I put it that way, so that I'll talk less. So in the hybrid scheme is really the no-brainer to say that hybrid schemes, there are complexities there when we combine hash level, when we combine in the encryption level, when we combine in the different levels, we pick up the ECC, pick up the PQC candidates, and then combine and then do that. It is not just simple as it sounds. So how is it going to react with the, of course we have seen it in the TLS, how the protocols are negotiated in the TLS handshake. We could do that, and not to say that mathematics and cryptographics love formal modeling, formal methods, which are usually not not famous with the system integrators. That how do we model the new hybrid instantiation of key encapsulation algorithms, and then how the attack surfaces are specified. Those things, those assumptions we are making today have to be understood, and then we need some research in that. And not to undermine the automation that we are talking about, many of these new things that talk about automation. How do we analyze the live integration of PQC in the field? We have to see, and then how the new PQC libraries play out. We have to see. And also the new understanding of the PQC migration in complex architectures, heterogeneous architectures is also important. The other part, so there are some work going on in the PQC transition, as we see. NIST PQC standardization process is going on for algorithmic level, and then there are some groups working in upgrading and enabling the protocols today, communication protocols with the PQC, and there are some systems which are implementing the PKI and hybrid certificates right now, which HSMs and all processes are going on. And there are some crypto agile PQC libraries that exist today. One example is the Open Quantum Safe group, and I am part of that, and Amrita is contributing to that in a way that we have the OpenSSL. Many of the current secure shell or SSL or VPN or hybrid certificate X509 certification CA process are available for open source. And key findings in all the migration process that happened today, I'm just highlighting certain things. So main thing come out is no candidate has got everything we want. So all involve some kind of a trade-offs and choices of confidence in security versus the ease of deployment versus performance. So no need more security analysis, obviously. And then custom modification in the PQC protocol, bring in new flaws in that, implementation flaws, which is very important. And then size constraint, as we see in our experience in OQC, we see that unexpected bugs pop out because of size. And then, as you know, when the memory consumption comes up, all the multi-threaded applications we have today run into buffer, stack overflow problems. It's very common. And then in the overhead, as you say, whatever said and done, I think the earlier speaker talked about the latencies. The PQC overhead as such is amortized over the long, tunnel times out there. And I just want to point out 2-3 findings here. Versioning difficulties we have. See, algorithms that are qualified, they start updating the versions of it, and then the specification keep changing. It's a moving target. And then we have the API problems too. Today, some of the KEMs, how it doesn't integrate well with the existing PQC APIs. And there are some good news there. Migration of long-lived hardware trust is more urgent today. And then Sphinx perform okay for software signing, and the algorithms like Rainbow works for the CA, all these TLS connections. And the next part is, I just want to touch upon this cryptographic agility. Is something like I call it a science. It's not science. Purists will object to that. It is something, a new approach, we can say, new approach where we make the existing software and hardware cryptographic infrastructure to be easily upgradable, more modular, more manageable. On the right side, you can see the scope of CA. It touches upon all these aspects of it: algorithms, program code, and then protocol modules there, applications there, services written there, and systems, all that. So I got a flag here. Okay, so need for crypto agility, and I just want to touch upon 2-3 things. Post-quantum readiness it ensures, and then in-field crypto update we have to do. I don't think we can bring all the systems back to the vendor and do that. And then next is crypto agile architecture. This is a view of it. So applications are stacked on the crypto API, and then every level of the software stack goes down one layer, and then all the mechanisms, specific algorithms are hidden. And the key findings in the agility we have seen is that is in the context of PQC, it enables agility as we go along with the NIST approval process. Cryptographic agility independent of PQC is very important for secure software development, secure IT development, I would say. And then we are seeing a lot of developments in the hardware and then software and the different computing and also accelerators there. The new frontiers, these are some things that are relevant to PQC migration. For example, the MPC, the identity-based cryptography, the homomorphic encryption, blockchain, which uses heavily the cryptographic hashing and PKC, and then the threshold cryptography. All these things, the one question pops up that how PQC migration agility is going to apply to this approach. And concluding remarks, I would say, even if you don't believe that quantum computers will ever come or is gone, and as a good practice, I think I recommend deploying PQC today. And past transitions have shown that PQC will be a long haul. ECC we have seen 2 decades to gain adoption. AEC has got 4 years competition, and then adoption after that, 3-5 years of competition. NIST, right now PQC we are seeing 2016 was announced, so around 6 years now we are still in the competition mode. It will take some another 10 years to get adopted, and like the earlier speaker told, probably hybrid is important. And I think as a concluding, we really have to stop somewhere. The standardization process should end, deliberation should end, we should start working. And then steps to follow, as I told earlier, we have to build an inventory. We have to identify the candidates for immediate PQC transition, and then ensure cryptographic agility. And probably as a final remark, I would say we acknowledge that over the period of 2 years I've been working in the PQC. It's like all stakeholders, like software solution providers, hardware vendors, government, standard bodies, consortiums, open source developer, where we derive all the pieces today. We go through a lot of heat there, how to integrate all that, how to validate each versions of it, each different bits and pieces out there, different software pieces for different hardware, how we do that. And I think all the communities listed out here, And then I would say that academia is very important to do the R part, where we do a lot of research, and then and the companies and the industries and probably the integrators like CDAC and CDOT and all these people can take this these research into a product and technology, and probably engineer solutions for the mass. So thank you very much.
Thank you, Professor Krishnan. And now I would request Sri Swamisaran to make his keynote address for us. He's currently working with Thales as the technical lead for identity and biometric solutions in India. In this role, he manages the development and deployment of biometric devices and solutions for both enrollment and authentication as a part of Aadhaar ecosystem for India, as well as for modular open source identity platform, the foundational identification system for the countries outside India. Sri Swamisaran, please.
Thank you, ma'am, for your introduction. So good afternoon, everyone. And at the outset, I would like to thank the organizers to give me an opportunity and give basically Thales an opportunity or a platform to share our views on post-quantum cryptography, especially in the HSMs. Now, to some of you, HSM would be a new word. So HSM stands for Hardware Security Module. So it's a hardware piece where you store your keys. So we are talking about cryptography, we are talking about protection of data, but the most important or the basis of everything is the protection of the key, and that's what we do. We protect the key, we put that in a hardware like a jail where you cannot take out the key, and it's securely stored within the HSM. So setting out the agenda, I would just like to give a very brief introduction on the Thales Group. Then I would be covering the classical computing versus quantum computing, which is already well known thanks to the previous presentations and the whole session. Post-quantum era, post-quantum algorithms, post-quantum preparation, which is very necessary, and I would conclude with a summary. So as a brief introduction, so Thales is a French headquartered organization with more than 81,000 employees, presence in 70 countries and across at least in every continent of the world. So we have an R&D which is self-funded with 1 billion euro and sales in excess of 16 billion euro. So we operate in the areas right from the bottom of the ocean to the depths of space and cyberspace. To tell you, one of the product of Thales is the well-known Rafale aircraft. So in the Rafale aircraft, the intelligence of Rafale, so what makes Rafale really a Rafale, the electronics is by Thales. So we are also into digital security and also in the quantum computing space. So very quickly, classical computing versus quantum computing. So the quantum principles of superposition and quantum entanglement, it gives the quantum computing power exponentially stronger than a classical computing. Of course, assuming that the qubits are secure, they are not disturbed by the environmental noises. Post-quantum era, so it's terrific. And it's also terrifying. I'll let you know how. So in the past 20 years, so what we have, what I've snapshot, it is between 1998 to 2019. So that's the journey which the organizations in the likes of IBM, Devise, Intel, Google. So if you see on the right hand side, you have the number of qubits which have been increasing right from 1998 till 2019. So it moved from 2 to 128, And now in these sessions we were hearing and we were talking about qubits, a post-quantum a quantum computer to implement qubits as high as 1000. So you see the quantum jump in the quantum computing is what you see here, and that's what is going around in the world. Now, why the post-quantum era is terrific? It is because the quantum computing promises a lot of things: molecular discovery, drug discovery, supply chain, energy, finance, oil and gas, optimal path finding for the complex systems, very large number system, very large number of factorizations and whatnot. So the list goes endless, and you've got a lot of computing power at the helm, which makes this possible. But at the same time, it's terrifying. Why is it terrifying? Because the quantum computers, they are ideally suited for solving complex mathematical problems like factorization of a large number. And that's the core of the current asymmetric crypto system. So all our data today is protected because of primarily because of public cryptography, and that is the area, and that is the cryptography which the quantum computers are going to attack. So that's a terrifying scenario. So cybersecurity relies on rather restricted number of cryptographic primitives, which is ECC and RSA algorithms, as we all know. ECC and RSA, they are based on hardness of factoring, and quantum computers can easily crack that. Harvest and decrypt, we have heard in this session a number of times. So today's data with long-term value and long-term shelf life is definitely under quantum threat. So that's the situation which you see. The quantum is a big fish and the classical is a small fish, and that's how is the state of affairs. So we should be scared of that. Who needs data security? Practically everyone. So if you love your data, you have to encrypt it to protect it. Banking, government, defense, critical infrastructures, enterprises, data centers, healthcare, telecommunications, all have critical data, all maintain data, so they have to encrypt that in order to protect it. Coming to post-quantum cryptographic algorithms. So NIST has ventured to come out with the standards of post-quantum cryptography. So definitely in the previous presentations we have been seeing the number of algorithms which are the candidates and which are the candidates in NIST and which NIST is trying to evaluate. So it all started in 2016, where there was a public call for the submission of post-quantum algo candidates. So in 2019, approximately 26 out of 69 post-quantum algos made the cut. And the process of evaluation and scrutiny by NIST is still continuing, and we expect that by 2023 or 2024, we would have the NIST draft standards for the post-quantum algos. So primarily the quantum resistant algos, they are based on lattice-based, code-based multivariate, which all of you know, and my previous speakers have already talked about it, so I'll just skip that. So we have to do post-quantum preparation. So the steps of quantum safe security we feel is threefold, is based on three pillars. First is you should have a lot of entropy or randomness generated in the system. So the randomness, you can get it by quantum random number generator. You need to have a forward secrecy and data integrity, and quantum key generation and quantum key distribution are the solutions. So you need to be crypto agile. You need to future proof your cryptographic primitives and implement the quantum resistant algorithms. So that's just a snapshot. So you've got quantum at the core, and you need to have quantum distribution, quantum random number generation, quantum safe algorithms. All these three are important. You cannot ignore any one of them if you love your data. So quantum random number generator and hardware security module. So Dr. Bruno, he had already mentioned from ID Quantic, he had very eloquently spoken about the quantum random number generation. So the blue, outer blue concentric circle, you see the quantum random number generator from Quantic. And the circles below that, they represent the hardware security module. So the hardware security module is the appliance, or is a hardware which stores the key, which generates the key and stores it securely. A hardware security module from one of the product of that Thales provides in the market is Luna Network HSM. So Luna Network HSM, it does primarily the key storage, the generation of the key, the storage of the key. It does cryptographic algorithms, encryption and decryption. Plus it has got a number of other features, like it also has algorithms for the 5G, 4G, 2G technologies. But the main focus here, the main focus area which I would like to point out is the crypto agility, the ability of the HSM that we have. It's crypto agile. Now, when I say crypto agile, it means that the algorithms, when they become quantum safe and when they become available to us, we can upgrade we can upgrade our HSMs to be compliant with the crypto with the defined standards that NIST would be defining. Now, how does it work? So Quantis appliance is a true random number generator coming from the quantum physics. So it has got sufficient entropy, randomness. So it generates random numbers. It gets seeded into the HSM, and the HSM uses this random number coming from a high entropy source to generate a key, and this key is at the heart of the encryption. So both Quantis appliance and the Thales Luna HSM, they both are appliance. They are network connected. And of course, the source of entropy and the source of key generation should be linked together, should be very near. And once the HSM has got the key generated, all the encryption algorithms and encryption services can be provided to the application, the calling application to the HSM. Quantum key distribution, not to talk about it much, because already we know about quantum key distribution. It is definitely secure based on the quantum principles, no cloning theorem. An observation leads to perturbation, which means that any probing into the quantum key distribution would be detectable, and so that's why it's very secure. Quantum safe algorithms. So these would be a typical public key infrastructure. What does it have? It has a certificate. So all of us, when we go to a trusted source, which is a certification authority, we get a certificate. Now, certification authority is a trusted source. And what is a typical structure of a digital certificate? It has got a serial number. It has got an issuer. There are two stakeholders here: a certification authority and the user of that certificate. So the subject is the user individual. If you see the left-hand box, you've got a validity of a certificate. You've got a subject public key, and this public key is signed by the issuer. Now, typically in the present case of classical, you've got a classical digital signature certificate. But when we move on to a post-quantum era, so then you would see that in the green, these parameters are going to change. So the issuer would be a CA, and at that time, in the post-quantum era, he would become a quantum safe CA. The subject is still the individual. The certificate still has got a validity, and the public key would be a quantum safe public key. The issuer signature would be a quantum safe signature. So that's the change that you can visualize and you can see between a classical and a quantum safe certificate. Now, when you want to move your PKI or a crypto system, public key infrastructure, there are a number of solutions. I would be highlighting 3 of them. First solution is that on the left hand side you see the classical PKI, on the right hand side you see the quantum safe PKI. So one solution is to replace the existing classical with a quantum safe PKI. Now when I say replace, it means that when do we replace that? So this replacement is only possible when all the systems are quantum ready and when the quantum safe algorithms are fully available. But what does it entail? It entails high time plus cost consuming migration. It has got a high planning, it is very highly intensive in planning. Rollback if it is not working, and vulnerable to quantum attacks. Solution number 2, you duplicate. So you have got a classical system, PKI, and you duplicate the existing classical to make a quantum PKI. But again, you've got a high cost to maintain 2 PKIs, 2 certificates in the operation, roadblocks in seamless operations, and affects end user experience. So the solution is the third solution which Thales recommends. So that's a crypto agile upgrade where you have got both classical and quantum safe algos, they coexist. Migration to full quantum safe is in phases. Maintaining backward compatibility between classical and quantum safe PKIs and seamless user experience. And how this is possible? So you have already seen in my previous talk. So you have the classical digital certificate and you've got a quantum safe digital certificate on the left hand side. But what we propose, and in partnership with ISARA, so we have one new digital certificate which has got a combination of the classical certificate and the quantum safe certificate, which means that you have got the same serial number, validity, blah blah blah, and then you have got the subject public key which is classical as well as quantum safe. You have got the issuer signature which is classical as well as quantum safe. So I think with this we end the summary. To summarize, so threat on cryptography by quantum computer is definitely real. The need for protecting classically encrypted data is there, definitely. The existing PKIs have to migrate to quantum safety, and planning has to be done now. Implementation of the migration has to be done sooner than later. Thank you very much.
Okay. So what a session. I mean, I learned just so much in this session. I think I'm a little bit wiser about post-quantum cryptography versus quantum key distribution. So PQC and QKD are sounding a little familiar, and some of the challenges, why it's important, why hybrid is important, what are the challenges with migration. Okay, so very interesting session, and I wouldn't go around repeating everything that people have said. I think, as somebody said, this is difficult and the repetitions are important, and now slowly it's getting ingrained. But what I want to share with you is a very interesting story on the quantum wake up that I had in my own career, right? So sometime in the early 2000s, I was setting up a semiconductor lab, and we hired a kind of a very talented person. He was from one of our colleges, a BTech from our college, but had done his PhD in solid state from MIT, and he wanted to work in India, so he came and joined our lab. So we were initiating this work, so we were working on some of the older technologies, okay, the 180 nanometer. This was the era of 40 nanometer and beyond. So he was not satisfied with that kind. He comes and he writes up a proposal and submits it to the research group, talking why he wanted to work on 14. He was challenging the way the models for the devices were being developed, the very basis on which modeling of the, because you do all the simulations, right, when you design chips. So he was challenging that, okay. And he was using quantum physics to explain why the modeling techniques in this company was all wrong, and they need to quickly move to the quantum type of modeling. And so the experts in that country, obviously in the US, were challenged by this young rookie challenging what they've done all their life, and they threw him a problem. So what had happened way back in the 90 nanometer era, so one of the semiconductor manufacturers, I don't know if it was TI or Intel, had by mistake taken a wafer, and this wafer had been 90-degree phase shift. In the processing, it was phase shifted by 90-degree. It has to have a certain alignment, but by mistake somebody shifted the wafer by 90 degrees and did the semiconductor processing on it. And what they found was that the leakage current suddenly went down 10x, because as they were moving to newer geometries, the leakage current in the semiconductor was becoming a big issue. So by phase shifting it 90 degrees, this leakage current went down 10x, which was a big thing, and it was an experimental result. Now they asked the modelers to explain the physics behind it, and nobody was being able to explain this, right? This was an unsolved problem, and the whole semiconductor industry adopted this in terms of processing, manufacturing, but it was an unsolved problem. So these guys threw him this, that you apply your whatever you are thinking of the new ways of modeling to this problem and show us a solution for that. And he actually did it. He applied quantum physics to explain the leakage current issue, and he solved it. This paper was actually published in the Nature magazine, okay? And so when you move into these new paradigm shift eras, right? So data is, we are in a world today where the physical and virtual, the boundaries, data is becoming so important to our lives. The virtual world and the physical world are meshing together. So obviously the security of this data, the long-term security as we are talking about, is so important. And then we are the country where we have all these, young rookies who are unbiased by legacy. They can look at things afresh, and they can, solve these unsolved problems. So the challenge I want to throw to this team is that look at this NIST competition. Where is the algorithm from India? Have we submitted any algorithm? Right? To challenge the other algorithms? So if this team here can get together in the lunch break and form a team which is going to submit one algorithm at to NIST in this competition, that's the challenge I want to throw to you, and I'm sure Mr. Naren Nath will support us, okay? Because that's what he said. Unless we have leadership position in advanced technologies, that is what we need for our national security and to take that next jump. So with that, I would like to end the session. Thank you. You have to collaborate. Have a bigger.
Thank you so much for this very stimulating session. I request Shri Abdul Qayyum ji, DDG 6G TEC, to kindly present a memento to the chair, Srimati Pamela Kumar. And now I request Honorable Chair to present the mementos to all the panelists. Shri Narendra Nath.
Yeah, very nice plaque.
Shri Atul Kumar Gupta.
Yeah.
He's asking.
Huh?
He's asking.
Oh, look up.
Okay, thank you.
Shri Prashant Chugh.
I'm amazed that CDOT has so much equipment already out there, and you're making profit on it. Are you profitable?
One for Professor Prabhakar Krishnan.
Thank you. That was a very comprehensive talk.
we deserve to have one session.
Shri Swami Saran.
Your name came in a little late, so they were unable to. Thank you very much. Thank you. That was a very good talk. Thank you so much.
So as we have a group photograph clicked with all the members. लंच से पहले एक और विषय ले लेते हैं. Let's have one more session before lunch. We'll enjoy lunch better then if you are more hungry. So let me quickly give a brief of this session. Standardization efforts on quantum technologies. Quantum technologies are rapidly advancing and have the potential to revolutionize computing, communication, and other fields. However, the lack of standardization poses a challenge for the widespread adoption of these technologies. This session will explore the standardization efforts underway in the quantum technology industry, including the development of standards for quantum communication, quantum computing, and quantum sensors. And let me invite on stage the chair of this session, Shri Uma Shankar Pandey ji. Can we invite the panelists on stage first?
We'll wait for 5 minutes. जल्दी मैंने रोका सबको और बोला कि 5 मिनट्स में रुकना है. पैनलिस्ट को बुला देते हैं बीच में.
Joining us in this session will be Shri Ritu Ranjan Mitterji, Senior DDG and Head of TEC, Professor Anil Prabhakar from IIT Madras, Professor C.M. Chandrasekhar from IISc Bangalore, and online also we'll be having two of our presenters, Shri Matthew Campina, AWS Cryptography from United States, and we will have a pre-recorded talk by Dr. Dustin Moody from NIST, United States. We are waiting for the chair to be amongst us. Can we have the other members kindly on stage, please? Shri Uma Shankar Pandey ji will be joining us later. Shri Ritu Ranjan Mittal, Professor Anil Prabhakar, Professor C.M. Chandrasekhar. So let's welcome on stage Shri Uma Shankar Pandeyji, Member Digital Communication Commission, Department of Telecommunications. He is going to be the Honorable Chair for this session. He joined ITS in July 1986 and has worked in different disciplines and areas. Headed a number of telecom districts as Telecom District Manager, Aligarh and Raebareli. In the capacity of General Manager and Principal General Manager, worked at Aligarh, Faridabad, Noida, Ghaziabad and Gurgaon for 14 years. Promoted to CGM grade and posted as Chief General Manager, Himachal Pradesh for about a year, and then CGM Haryana Telecom Circle for 3 years. On promotion to Senior DDG level, he got posted as Head Madhya Pradesh LSA for approximately 1.5 years, and from February 2023 working as Member Services DOT. I request Honorable Chair to kindly begin the proceedings.
Very good afternoon to each and everybody present over here and under dais also. So friends, last 1.5 days, all crypto and crypto. I think now things may be going overhead, all of you. So I'll not talk much about crypto. So I'll tell you one small story about me, then I'll read whatever has been given me to read over here. So I did my MTech from IIT Kharagpur way back 84-85, so almost 4 decades. After completing my 2 semesters, I was asked to do some project. Some academician maybe here, they must be knowing Dr. M.N. Farooqi. He was a great scientist over there, later he became director IIT Bombay also. One digital lab was there that was known with the name of Dr. Farooqi's lab. He told Mr. Pandey, work with me on the linear prediction of speech in 84-85. I mean, how to communicate, mind-machine communication. That was the very beginning, some work has been done. We thought, sir, what is this? Then he told, oh, come with me. Then I think I worked with him around 8 to 9 months' time. Then this ITS was to be joined in July 86. Then I left IT after completing my projects. So what we did say 4 decades back in the linear prediction of speech, how the speech is predicted. Today it is reality. I've got so many things, Alexa, etc., etc., etc. So that was one small story for me. Today you people are doing brainstorming on the crypto. A lot of things have been done, and some more things are yet to be done. The session is going very nicely. Now friends, this conclave organized by TC, CROT and TSDSI is being held at a time when the world is witnessing a rapid transformation in the field of telecommunications. As we move towards a more connected and digital world, it is imperative that we pay close attention to the security of our communication networks and ensure that they are safe from the threat of cyber attacks and other forms of malicious activities. As has been discussed in the previous sessions, the advent of quantum computers has the potentials to render current communication infrastructure vulnerable. Quantum computers are capable of breaking many of cryptographic systems currently used to secure information transmission. As a result, sensitive information such as financial transaction, medical records, etc., etc., we have seen quantum key distribution, QKD, and PQC are 2 potential remedies for vulnerability of communication infrastructure caused by the advent of quantum computers. QKD uses the principle of quantum mechanics, which everybody has read in the early schooling days, to establish secure keys for the encryption, making it impervious to attackers from the quantum computers. Similarly, PQC uses the principle of quantum mechanics to secure keys for encryption, making it impervious to attack from the quantum computers. PQC, on the other hand, relies on the mathematical problems that cannot be easily solved by quantum computers, so making it a potential solution for the long-term security of the encrypted data. Many industries and startups are working on the developing of QKD and PQC technologies with the aim of creating a new generation of secure communication system. This includes research into quantum-resistant cryptographic algorithms, as well as development of new hardware and infrastructure capable of implementing QKD and PQC technologies. Governments and international organizations have also recognized the need for these solutions, with many investing in research and development programs to address the security risk posed by quantum computers. As quantum computing technology continues to advance, it becomes increasingly important for organizations to incorporate QKD and PQC technologies into their communication system. Making standards are crucial for development of products. Now, today's session is for the standardization of the equipments that incorporate QKD and PQC technologies. Standardization ensures that products from different manufacturers are interoperable, which is essential for the adoption of these technologies on a large scale basis. A lack of standardization can lead to fragmentation of the market, making it difficult for businesses and organizations to choose and implement these technologies effectively. Standardization also helps to ensure that products meet the necessary security requirements and provide a consistent level of protection against attacks from quantum computers. To address these issues, various standardization bodies are working to develop standards for QKD and PQC technologies, providing a framework for the development and deployment of these products on a global scale. With the increasing use of quantum technologies in various fields, telecom, finance, healthcare, and defense, it is essential that we have a robust and reliable standards to validate our products in order to ensure their performance. TEC released a set of standards and test procedures for QKD systems. These standards provide a framework for the development and deployment of QKD systems in India, ensuring that they meet the necessary security and interoperability requirements. The standards cover various aspects QKD system, including key management, security protocols, and performance evaluation. The release of these standards and test procedures is a significant step towards the adoption of QKD technology in India, providing a clear path for the development of these systems by business and government bodies. This session will play a crucial role in bringing together experts from the different fields to share their knowledge and expertise and work towards establishing standards that can ensure the security of our communication system. I am confident that the discussion and deliberation that will take place over the course of this conference will help us in identifying the gaps so that installation activities could be started in these identified areas. So basically, the session is for the making standards which can suit to the industries and it cannot be fragmented. Being a member of DCC, just I would like to intimate the whole gathering that Government of India, Telecom Ministry is doing a lot of funding for the startups who are coming with some development of some technologies. So if some people are interested in developing the new system depending upon QKD, they can come up to us, give the presentation, and if it appeals, then definitely we will fund it. With these words and a small story about me, now we are the teething problems with all the technologies. QKD is the future for the encryption and security of our networks. So I would like you share that all the knowledge available over here to the betterment of the country. Jai Hind. Thank you so much.
Thank you so much, sir, for your insights. And now I'd like to introduce Sri Ritu Ranjan Mitterji, Senior DDG and Head TEC. He is an Indian Telecommunications Service Officer with over 35 years of experience in the telecommunications industry. Shri Mittar has worked on various projects related to the development and deployment of telecommunications networks, standards and policies in India. He has also been involved in the development of various technical standards and specifications for the telecommunications industry, including quantum, 5G, IoT, and M2M technologies. Under his leadership, TEC has released standards on quantum key distribution system and quantum safe cryptography system. Sri Ritu Ranjan Mitterji, request him to kindly deliver his keynote address.
Yeah. Thank you, madam. So, experts on the dais, experts of the dais, ladies and gentlemen. TEC, as you know, is a technical arm of Department of Telecom. Coming to international standardization, we are a technical arm. Being a technical arm, we have national study groups corresponding to the ITUT study groups in ITUT. Somebody mentioned about ITUT study group 13 standards. So there are a number of study groups, and we also have a national study group. So I take this opportunity to invite you to connect to these study groups. Rather, we will welcome the participation from academia, eminent professors here, industry, so that whatever we discuss and deliberate in national study groups, that can go as a national contribution, and it has a better chance of getting accepted at the international community because it goes as an Indian contribution. Because being government, it's a member state, so member state has more power than the sector members. So I invite you to contribute to the national study groups. For this purpose, we have opened a standardization coordination portal. So you can join that portal, contribute through that portal, and become part of the collaborative effort that we want you. Another important thing I would like to inform you is that India in Delhi would be hosting WTSA, World Telecommunications Standardization Assembly in 2024. It will be October 2nd week in Delhi. So time is now to start, because though the technical work is done in the study groups, but the directions to the study groups is given through the WTSA meetings. There are resolutions. So I request that you please go through those resolutions and see what are the gaps. So whatever we want 5 years hence, we can direct through the WTSA resolution. Even a small phrase would be a direction to study groups that this work need to be done, and the priority it needs. So that is about the ITUT. Coming to TEC standards, you are aware about the QKD and the PQC standard, and the test guide was released yesterday by Honorable Minister. So we have standards of a couple of types. One is the generic requirements, where we try to go into details, even the details about if a product is there, what would be the safety standard, what would be the EMI EMC standard, environmental conditions that would, and the technical features of course. And corresponding to these standards, we have certifications. So corresponding to generic requirements or those standards, we have certification which we call type approval certificate. So if you think that you comply to that, your product complies to any particular standard, you can approach us, and we would, through a team effort, we will test and give a type approval certificate. Even if you don't comply to a complete standard, then we have something called certificate of approval. That means that if you have your own standards, you can approach us, and as a third party, we will test and give you a certificate of approval. So certificate of approval is normally given to a product for which standards are not existing. But even if now we've become a little more lenient, even if a GR is there and you're not meeting and you still want a COA, normally a certificate of approval is given if there's no GR. For example, free space optical system from Google Tara, that was given. We have application from Nav Tech Ahmedabad. GR is still not there. SD-WANs, software-defined wide area network. We have GR, but we are trying with we are helping one organization to get a COA, though GR is there. So these are two certifications. Then something called technology approval, which we mostly do for CDOT, because any technology which is gone through R&D and is tried in predominantly BSNL network is given technology approval. So that is another approval. We also do something which is called mandatory testing, which is in response to DPIIT, and we are a single inquiry point for World Trade Organization technical barrier to trade for the telecom sector. For the other sectors, it is BIS. So we make something called essential requirements. That means a bare minimal set of requirements which a product should meet to be inducted in Indian telecom network, but it should be notified. So that also is going on in phases. So apart from this, in short, we make specifications and we do testing and certification. Yesterday, Honorable Minister announced 10 million called simultaneous test for C.4G EPC. I'm proud to tell that TEC was involved in that testing, and incidentally we had the test gear, and the whole load was generated and sent from the TEC office in New Delhi right to Chandigarh over fibers. So that is something which is we are also, mostly all testing and certifications TEC is involved. And just to end on a lighter note, we are talking of standardization. I was pleasantly surprised to note that sender and receiver has been standardized as Alice and Bob. So many presentations. Thank you.
Thank you, sir, for apprising us of the role of TEC in standardization of quantum technologies. We next have Sri Matthew Campina. He's with us virtually. He's a senior principal engineer and cryptographer for Amazon Web Services. He oversees the design and analysis of cryptographic solutions across AWS. He is a member of the ETSI Security Algorithms Group Expert and chairman of ETSI TEC Cyber's Quantum Safe Cryptography Group. Previously, Matthew managed Certicom, BlackBerry's cryptography research group focused on the development of intellectual property and standardization for elliptic curve cryptography. Do we have him online?
So, yes, can you hear me?
Yes. You may switch on your camera, and your audio is, we can hear your audio. Just switch on your camera if you want to.
It shows my camera is on, and I see it in the portal.
Yes, we see your presentation. Yes, yes, thank you.
And I'm not sure, the video seems to be running on my end. Okay, great. Thank you. My name is Matt Campagna from Amazon. I appreciate the opportunity to speak to you today. I'm going to be talking about the work we're doing in ETSI TEC Cyber for the working group on quantum safe cryptography. So I have a short agenda, starting with a brief history of the working group, some basic information on the working group today, participation, and roles within the organization. I'll go through the completed set of technical recommendations and specifications we've done so far, as well as current work items that we're working on today. And then finally, how to participate in ETSI TEC Cyber. So ETSI is the European Telecommunications Standards Institute, and it's a regionalized standards body focused on information technology systems. Within there are 29 technical committees, and these are organizations that can create technical specifications and European standards that are normative standards, as well as technical recommendations. And then we have 17 industry specification groups that typically produce technical recommendations as opposed to standards. And 2 open source groups developing compliant software to specifications. ETSI plays a special role within Europe to produce harmonized European standards along with CEN and CENELEC. And these are standards that can be included in, for compliance with European regulations. They also participate in a few partnerships. There's a 3rd generation partnership project, which is the cellular standards, as well as 1M2M, which is focused on the Internet of Things, machine-to-machine communication. ETSI is funded primarily through its membership fees, but it also receives some financing through the European Commission and the Europe Free Trade Association as part of its special role to produce these harmonized standards. It's located in Sophia Antipolis in the south of France, and the Director General is Luis Jorge Romero. So the working group really started back in 2013, and maybe even a little before that, when ETSI and the Institute for Quantum Computing at the University of Waterloo was looking to bring together the communities beyond what was really going on in academia, the post-quantum crypto, bring together members of industry as well as governments to sort of focus on the problem of really changing the dialogue from post-quantum crypto to developing these new cryptographic standards now, with an awareness that after participating in the transition from RSA to elliptic curve and watching the standardization of AES and SHA as was earlier indicated, that these things take 20 years, 15, 20 years for adoption. And if we didn't start that process for quantum safe cryptography, we'd be exposed to the development of some future quantum computing, at least when it comes to the confidentiality of our information. In 2015, we published the Quantum Safe Cryptography and Security White Paper as a result of that initial workshop. And we also started an industry specification group of quantum safe crypto. We've had a lot of great participation in the workshop. Members from NIST, Microsoft, BlackBerry, NCSC, and other government institutions really participated. And I think as a group of focused people on quantum safe crypto, we were delighted when NIST opened their call, because NIST is one of the few organizations that can really corral the global audience of cryptographers to arrive at a new high assurance cryptographic algorithm. They have a great track record with AES and SHA. In 2017, the working group became the industry specification group became a working group of TC Cyber, enabling it to begin writing beyond just recommendations, but also some specifications and normative standards. So today we meet 4 times a year in coordination with TC Cyber, and it's held in hybrid mode, so it's friendly for teleconferencing, which makes it easy for people to participate modulo the time shift. So today I'm the chair of the working group. We have 2 vice chairs that consist of Philip LaFrance from ICERA, Dan Grundy from NCSC. Our secretary is Tony Barnett from Talis, and our technical officer is Laura Portion from ETSI. And all the working groups at ETSI have a technical officer to help us align our work with the requirements for development of standards within ETSI. We have a healthy participation, typically 30 to 40 registered participants for each of our meetings, with a variety of corporate, government, and academia participating in this. So what have we been working on? Well, when we started, sort of our first kind of technical recommendation was a broad survey of post-quantum techniques. This was prior to the NIST process. So we were just looking at sort of a field study of what's available in the industry or in the publication to sort of develop new post-quantum schemes. We revised those in subsequent TRs that were based a little more focused or completely focused on the round 3 candidates for the NIST process, breaking them up into the public key encryption, key encapsulation, schemes, as well as the quantum safe signature schemes. And these were both taking a look at the broad survey of what's available, as well as measuring and speculating on how well they would fit in our existing protocols and use cases to inform the NIST process on making the selection. We produced 2 technical recommendations on how to apply these post-quantum schemes, or how to make things like our virtual private networks, so VPN technologies like TLS, IPsec, SSH, MACsec, and moving that to post-quantum. So it has a lot of migration proposals for moving those networks, as well as the use of lattice-based crypto to generate identity-based encryptions, which were also used within other organizations within Etsy. We developed a general migration strategy document for quantum safe schemes, kind of starting with inventorying, has very practical recommendations on how to start that process. Produce a technical recommendations it's based on NIST published a specification, NIST SP 800-208, which is about stateful hash-based signature schemes. And these have a new requirement in terms of managing private keys, and that you need to manage the state of your private key, because they're essentially modifications of one-time signature schemes. This provides additional recommendations on how to carefully manage that state so you don't reuse the same state. And we have one technical specification around quantum-safe hybrid key exchanges, and this outlines 2 methods in which you can do both a classical key exchange or a post-quantum key exchange, or CAM, to derive at a key establishment that would require your adversary to break both of those schemes. It comes in 2 flavors, sort of what we call a concatenate, where you're doing the 2 key establishments without adding additional round trips, and then arriving at a key to secure that session, and then a cascade method, which is more akin to building something like a tunnel within a tunnel, which lends itself really nice to IPsec. Our current work items, we're just finishing up a technical recommendation on migration for quantum safe crypto for the intelligent transport systems. This has a unique set of constraints. It has 1, a fairly complex PKI infrastructure, and 2, very severe bandwidth constrained application, vehicle-to-vehicle communication, that poses, really outlines some of the struggles that ITC is going to have to migrate to post-quantum crypto. And a lot of these migration plans early on, the earlier you can begin this work and take inventory and analyze how the proposed schemes are going to work in your environment and your specific use case, the earlier you can realize if you need to re-architect, which is significantly more work than sort of figuring out how to do without re-architecting, how to drop in or do a hybrid mode. We have a work item on deployment considerations for hybrid schemes. We heard earlier about the potential of using certificates that are either, I'll say, a composite certificate that has both a classical and a post-quantum scheme, or 2 separate certificates, a classical and a post-quantum scheme, as well as how they might be related, like enforcing that the post-quantum scheme certificate is pinned to the classical certificate, and working through some of those edge cases of what happens when you revoke one or the other, or one key within a certificate but not the other. So it's making general recommendations about that. This is pretty early on, that TR. We're updating the quantum safe hybrid key exchange specification. The first version was intended for sort of ephemeral key exchange. It provided what's known as security against chosen plaintext attacks, where we're augmenting that and adding in security against chosen ciphertext attacks. And this would be applicable to something like mailing systems or key establishment techniques where it's not interactive. And then we have 2 technical recommendations. One that's looking at the quantum computing effects on the cryptographic security assumptions that we make in developing the proofs. So when we develop a standard, we typically accompany that with an academic publication that provides evidence of why this standard is secure. And that contains security proofs And those security proofs make some assumptions on the hardness of problems. And not all of them are just public key assumptions that we make. There's a number of other assumptions, and we're looking at sort of a more of a clinical analysis of how do those assumptions hold up against quantum computing. So kind of informing the cryptographer and the researcher on how do we update the set of evidence that we have for our existing standards. And finally, looking at the impact of quantum computing on symmetric cryptography, taking a deeper look at the application of Grover to things like block ciphers and hashing algorithms. So finally, how to participate. I know there are members heard from Talis, and Sarah's name came up. And of course, the Center for Development of Telematics are all members of ETSI. You can find us in the ETSI portal. One of the nice things about ETSI is the work is driven by its members. They participate in the working groups and they drive the agenda and the work items. And we're focused on trying to solve our constituents, our members' problems. So any member can come and propose work items for the working group to take on. Another nice aspect of the ETSI standards in general and recommendations is that once completed, they're publicly available. They're free to download. There's no paywall or no signing in. They're just public standards for use. You can find us under the Cyber Technical Committee or a working group, and you can click through and find our work program, our meetings, drafts of the current work items. We meet 4 times a year, as I said. Our next meeting is in May. It's a great time to come to Tafia and Tiflis because it is in the south of France. It's a little bit before the busy season, but the weather is terrific. We'll meet again in September, which is a little after the busy season, but still nice weather. And then we'll meet again in December. So I want to thank you for your attention. I really appreciate it. Some of you get an opportunity to attend. Thank you very much.
Thank you, Mr. Matthew. We know it's late night in US, and thank you for taking out time for us, for our conclave. Thank you so much. Our distinguished panel also has Professor Anil Prabhakar. He's been with the faculty at the Department of Electrical Engineering, IIT Madras, since 2002, and is engaged across multiple laboratories that work on quantum technologies. He has more than 50 publications and co-authored 2 books and is on the editorial board of 3 international journals. He is the founder of QNU Labs and Confluence, companies incubated by IIT Madras, pursuing quantum communications and quantum computing, respectively. Professor Anil Prabhakar, please.
Thank you very much for that introduction. I guess I'm struggling with the green buttons. Is that what it is?
Green, there are many greens. You can try and you can tell us.
All right. I'm going to be between you and lunch, and there are more speakers, so let's see how well we can do this. Right? Thank you for inviting me. It's always a pleasure to come and talk about some of the work that we do. This forum is also, I'm happy to see there are lots of people who are doing all this work, so I can stop working so hard. It's my takeaway message. No, I'm sure it's wrong. Okay, yeah. So very brief outline. We'll tell you a little bit about our center called CQuick, and then we'll jump into talking about the Metro Area Quantum Access Network. It's got the acronym MACAN, and the MACAN collaboration consists of IIT Madras, CDAC, SETS, and ERNET, and we have shared responsibilities. Describe some of the practical problems with doing something like this. We have seen a lot of people, with demonstrations, and I'll show you the problems we faced and then the future prospects. There's a timeline out there. There were many firsts in this conference. I told someone I'm going to say we were second, so no one can take away the second position. I think the DST funded us in 2009, and then starting with 2016 was our version of Quantum 2.0. And each successive generation has actually been moving us along the technology readiness level. Hopefully, we are now in the stage where we can deploy some of these solutions. Few students, faculty, staff members who have helped us on this journey. We have three main verticals that we talk about. One is quantum networks, the second one is quantum computing, and then the third one is more about building hardware. We do all of them. It's very interdisciplinary. Today we have faculty from all kinds of departments. The few photographs you see are there are the ones who have contributed to some of our journey in the quantum networks. So this is the Makan topology that we have. It's a testbed for different protocols. It's optical fiber that connects IIT Madras Research Park, the Society for Electronic Transaction Security, there is SETS, which reports to the PSA's office, and will eventually get to NIC, which connects to the National Knowledge Network. We have also brought in ERNET and BEL, so we are expanding our network as we get more partners joining us. And the idea is that this can act as a test bed for anybody, and whoever develops solutions for QKD, quantum secret sharing, quantum queues, and quantum network standards. The Makan collaboration itself, the way it works is, I'm quite proud to say that we've actually managed to get people to work together, which is itself a first or a second. So IIT Madras brings in the expertise on DPS QKD, cow QKD, over long distances. We also do the quantum queues and the quantum information. SETS does the FPGA firmware, does the post-quantum cryptography. CDAC Bangalore takes the brunt of the work. CDAC Trivandrum does a lot of the standards, is building out the software layers. And ERNET, who's our latest partner, is going to take on the link monitoring and the network management. So it's not just a temporary demonstration, but it's actually supposed to run 24/7 long term, right? This is something that I often put up. It's a slide that tells you that most of quantum key distribution is actually very classical. It's about 90% of it is classical. There's 10% of quantum. So if you don't know quantum mechanics, it's perfectly fine. You can still work in this space and contribute heavily. There is a big difference between the quantum channel, which is running at about 100 kilobits per second, and the classical channel that is running at about 100 gigabits per second. It's this information theory layers that work, that provide us the ability to actually encrypt, although we do not have 100 gigabits per second of key generation rates. So in summary, I would say that people who promise you unconditional security are actually giving you false promises, because there is this big discrepancy between the key rate and the actual data rate that is on a fiber optic channel today. Right? In simple terms, it means that I am using your password 1,000,000 times, which itself gives you sort of insecurity. So this is the Makan field trials. We worked very hard to do this by Independence Day. There was IIT Madras connected to IITM Research Park over a single fiber. So that was done on using wavelength division multiplexing, and then we had two fibers from SETS to IIT Madras Research Park. So we did both on a single fiber as well as two fibers. We did picosecond distributed clock synchronization, and we had point to multi-point demonstrations. Maybe this image is not very clear, but this is actually an image of the Darpan Q software that is developed by CDAC Trivandrum. It allows us to monitor the network and connect different nodes as they come live. So it is fully software defined. It's interoperable. It meets the ETSI, ITU-T and the ISO specs. And as we learn more about these specifications, the burden comes to make sure that we are meeting all of them. And the idea is that Darpan Q will then allow new nodes to come on, having different hardware. Maybe CDOT's hardware will come on, maybe QNew's hardware will come on, whoever gets new hardware can plug it into the network and then we can test it out. Our own hardware is actually embarrassingly looks like a student project, but it's what we call an open hardware, open quantum system. And the reason we stress on open quantum system is because quantum key distribution systems are supposed to be secure because of the information theoretic aspects of it. It's not what we would otherwise call security by obscurity. So, I mean, anyone who tells you that, they cannot open their box, you have to ask why, because it's supposed to be secure even if an eavesdropper is there, right? So, I think we have to start relying on these open quantum systems where we know what is inside it, and even then these systems are secure. This is typical WDM, and I put this up, many of you will already know what it is, but the last line which says that the WDM channels have an isolation of 50 dB between them for classical. Actually, we need more than 80 dB if you want to use the same fiber for quantum along with classical. That means we need new standards on what we are going to be able to do on the fiber if you are going to try to do QKD on a WDM network, right? So that is something that we have been looking at. The optical assembly, as I said, is all open, and it looks typically more dirty than this, but we try to keep it cleaner. Right? Okay, so here's another standard that should be there, right? So this is a very short distance from IIT Madras Research Park to SETS. It was basically across the road. And our losses out there were about 4 dB on a splice. So when people say 50 kilometers fiber, what they are basically telling you is there's 10 dB of loss, because it's 0.2 decibels per kilometer and you have 50 kilometers, so you have 10 dB of loss. On a very short link, if you don't have any standards, I can see already 4 splices and a 4 dB loss at one splice. Right? Between IIT Madras and IIT Research Park was another such link, and I had 4 dB losses out there, and I had another 3 dB connector loss. So this is the problem with standards which are not implemented correctly, right? And to set up this link, we had to go in and actually clean up, well, I didn't do it, but a lot of the students and staff had to go in and clean up a lot of these links, right? And it was not so simple classical problems. So you look at it, one of the splice boxes, you can see light leaking out. If you want to know why you want quantum, because this is the state of what we are actually having in the field. The splice box in the bottom right was covered in mud completely, and then after cleaning, it's supposed to look like what was on the top, right? And these are the practical considerations that overwhelm quantum communications. We are talking standards, and this is what we are actually having to deal with. Crosstalk between 2 fibers. Remember, it's not crosstalk on one fiber. I'm not talking of crosstalk between channels. I'm talking of crosstalk between 2 fibers. I'm sending the clock on one fiber and my quantum channel picks it up on the other one. Right? I don't know. I mean, what are we talking about, right? Our quantum channels are very sensitive. So this is the crosstalk. Okay, look at 2 fibers next to each other, spliced, but they're covered with transparent sleeves, right? And the light that goes on the clock, the signal that is going on one fiber, I'm picking it up on the second fiber. So we go in there and cover it with tape and try to minimize that, right? We don't have specs on a lot of these things. So if you are talking of specifications from a practical standpoint, I think one has to think of it from end to end. If I'm going to say I'm going to do quantum key distribution across long distances, we need specs on all of these things, right? Chennai to Bangalore, right? 550 kilometers of fiber. The plan is to do this. There's a station every 30 to 50 kilometers. So instead of having 2 secure nodes, I need 14 secure nodes, right? I have to reduce the swap and the cost, and that can come only if you use photonic integrated circuits. So that has got to be our next goal for anyone who's planning to do these kind of things. The route is not straight. It has to go through all the various stations. This is actually the BSNL network that we have begun looking at. So So what is the purpose of doing something like this? To leapfrog, right? We do not want to keep doing what other people have always been doing, right? So we did Makan, right? Metro area quantum access networks. So you build a house. The next thing, I'm going to switch to Hindi. Makan to bana diya, abhi to kila banayenge hum, right? The quantum internet with local access, right? So we have to think big, we have to leapfrog, and so this is what we do, right? We're going to do Chennai, Bangalore, and then we go Bangalore, Delhi. That's 2,200 kilometers. You're probably going to need a lot more nodes, secure nodes. It's probably not going to be 2,200 kilometers on fiber. The Chennai, Bangalore was 350, but we ended up with 550 with 14 secure nodes, right? So when you start looking at these practical things, and you can imagine how many splice boxes I'm going to have and how much leakage I'm going to have on them. So some of these ideas that we are now projecting are quite futuristic, but we don't have the time to do it in 20 years. We're going to do it in the next 3 to 5 years. At least that's what I hope. Right? So I'm going to stop here with my acknowledgements. As I said, we started in 2008 or 2009. We got support from DST, and then the PSA's office kick-started our journey again, and now we've finished Makan, and the hope is to do Kila, which is the quantum internet with local access, right? So the next time you think of QKD, do not think of point-to-point links. We are actually going to try to do an entire backbone down the country from Delhi to Bangalore, right? And then move it over to Chennai. Delhi to Bangalore, you'll cover Hyderabad, you'll cover Indore, Bhopal, right? And then you can set up feeders across that. So we do need our standards to enable something like this. And it's not going to be done by one person, it's going to be done by the collective, all of us sitting here. Thank you very much.
Excuse me, sir. Sir,
Yes.
I have one question, sir.
Sure. I don't know.
Can I ask?
Can we have questions online? If you just scan our barcode, we can you can put your question there, because we have one more presenter here for this. Maybe you can talk later during lunch. So Professor C.M. Chandrasekhar is here with us. He's a professor at Indian Institute of Sciences, Bangalore. He's also an affiliate member at the Institute of Quantum Computing, Waterloo, Canada. Over years, he has worked in close collaboration with research groups working on different platforms for quantum computation and by developing protocols and algorithms suitable for the hardware. Professor C.M. Chandrasekhar, please.
Thank you very much. So I work on both theoretical and experimental part of quantum information theory. So at IISc we have, just most of my talk would be on the current state, what we call as quantum simulators and what is quantum simulations. So it will be less of the work we do and more than work we do. I'll try to cover what is considered as a standard and what we call it as quantum simulators and what are the benchmarks and when do we call that, when can we treat that we have reached some supremacy, and that's what I'm going to cover. So before that, I just want to say we also do some experiments at IISc where we are single and entangled photons, and we are trying to engineer photons so that it can be used for communications, computation and various other applications. So just to give, okay. So there is still, it's going forward.
The red one is back.
No, that is not the back.
You are close to branch, you can only go forward.
But then I should finish it now.
Just keep pressing forward.
No, it's only going forward. I think the small red, right? I think there is this.
It's the small red one. Yeah. This one. Press it hard.
Oh, okay. It's an extra power, I guess. So I haven't had my lunch, so I. sure that. Okay. So sorry. So I think over years, it has taken nearly some 80 years for the quantum theory to be developed, and almost 20 years for scientists to learn how to engineer quantum states. It can be two levels, atomic system, photons, or superconducting qubit, and lot of things. And it has really taken a lot of effort and time. So first experimental proof of Bell's violation was in 1983. So we can see the timeline here, and it was in 2020 that some supremacy of quantum computers, which means that no classical computers can do, and there was something that a quantum computer did. So we'll look into that in detail a little bit. So, and there has only been like couple of supremacy results till date. So which means that we have a lot of work to do, and probably other 2 decades, 3 decades to look at how we progress with it and what are the current status of it. So just 2 examples of supremacy. So this was the Google, which claimed using 53 qubits, said that some randomized circuits, there is nothing useful about it, and that randomized circuit gave us some output. And from that output, they said, okay, there is no classical computers which can do that. It has been debated, it has been questioned, but that's still a reasonable, effort to say that there was a quantum processor which was used, a 53 qubit, and did something which a classical computers can't do. So this is a kind of what we call as universal quantum computer. I'll come to that, where circuit was done and anything can be done. The other one was a Chinese experiment, which had some 76 photons roughly. On an average, it was only 43. Where they did one specific problem. It's not a universal computer. It was not something which was circuit based and did everything. What we call as a boson sampling problem, and there's a mathematical equivalent of it which is called calculating permanence. So you can look into the Wikipedia and say it's one of the hardest problems. So this is something which you can't do in classical computers, and they did do this experiment in a quantum computer. In the sense, in a quantum simulator, what we call. So these are the only 2 known examples which recently have shown that there is some supremacy. It's been looked into. So these are big problems, and you should notice that we're talking about some 50 qubits or 60 qubit here. Where does that come in? Is that okay? So there is okay. So we call. I think again I got started. Okay. So there is something called superposition, which you all have seen, and the power, if you look at it, so if I am looking at, okay. So when we talk about 50 qubits, so why was that 50 qubit important to show supremacy? So if I am taking any quantum systems, if I can just take an atom or any 2 energy levels, and if I start looking at bringing them into a superposition state, the number of possible configurations I can look at, even with 3 quantum systems or 4 quantum systems, you can see the way it scales up. So you get up to like 10 to the power of like 15, 16 number of classical bits are needed to simulate some quantum system which is equivalent to about 50 qubits. So which means that if I'm crossing a 50 qubit system, which means that any classical computers above this power is needed to mimic it and simulate. So what happens with the power increasing with classical and the quantum? In quantum version, I just had to add 1 extra qubit to double the capacity of it. In a quantum classical processor, I need to multiply. It means that I need to double the processor size to increase the speed of it. And this is just to say that how it scales up and why supremacy people talk about after 50 qubits. So if I'm looking at gross understanding of our day-to-day life problems, we have water, ethanol, there are many of our daily use applications, right? So if I want to simulate them explicitly in a quantum processor, the number of classical bits needed and the number of quantum bits needed are given here. It's a rough estimate, right? So now, even water molecules, we really need about 10 to the power of 4 classical bits to do it exactly. But how do current quantum chemists do? And how do the drug industry or many of these people look at this problem is that they try to kind of approximate, in the sense remove unwanted states which are there and then say, okay, these are the only required states, and then they start looking at simulating them. But this means that there are a lot of approximations and a lot of improvisations. If you want to get into more precise, you might have to simulate them as explicitly as possible. So quantum computers do have an important role to look at simulating those chemical complexes, right? So in simulations, there are standard definitions. These are like academic definitions and people strictly follow them. So there are two kinds of simulations we look at. One is called digital quantum simulation and other is analog. So when we talk about digital quantum simulations, it's a universal computation kind of thing. You can have a problem, you can decompose into quantum circuits, you can build a quantum circuits, take it to a computer and then implement it on a computer and you get an output. The other one is an analog simulator, which means that you are having a system, a quantum system, which probably can't do everything you want, but it can do one specific problem. Just like in the beginning, I gave two examples. One was the Google's one, which is a universal quantum simulator, which means that you have a quantum circuit, you can implement those circuits. And there's another example which solved a boson sampling problem. It can do only one problem. The whole machine can only do one problem. So that's what we call as an analog quantum simulation, which means that it can't do many things. It can just do one problem, which is hard. Now that's still good enough. And these are two categories which we study kind of. So they solve one of the problems. It's not always about the number of qubits. It's also about how we are going to use qubits. This was one of the problems we worked in collaboration with Meddles and IonTrap. We had an algorithm we wanted to implement in their machine. And in this collaborative work, we had access to 50 qubits. But the problem is when we want to simulate them, we want to break it up into the circuits and then see how we can make a meaningful or get a meaningful output of it. So the current architecture, almost all the computers which we have available, in the beginning I mentioned there are only two problems which have been really broken up as a supremacy one. It's just because we can't implement enough number of gates on them. In any architecture which are available today, it's not about 300, 400 qubit, it's the number of gates we can implement on them. So from one of the best architecture today available is also ion qubits, where coherence times are good. We could only implement about 78 single qubits and 32 qubits before the system dies. It means that the noise seeps in and then becomes decoher in the process. So when we were looking at standardizations, we need to see about the processors and what is that it can really do, and how many number of, or what is the coherence time of them. And it's not just about the qubit, it's a qubit and the number of operations which it can do, and then the coherence time it is needed to be looked into. Right? So there is another this is again an analog simulator, so which is called as an optimization problem. So probably you might have heard of another kind of computers which we call D-waves, where it only tries to find the ground state of a solution. You have a complicated problem and you want to optimize it and you want to get a ground state of it. So classically what happens is that you might end up seeing that this itself has a ground state and you happily sit there. But what Hamiltonians or a quantum mechanics does is that there is always some kind of tunneling which happens, and because of the tunneling you will be able to find out a real ground state is possible. So this is again a kind of a classical simulator. So we can, what we call an analog simulator, which does an optimization problem. So there are broad categories which in academia we try to look at. One is the universal quantum computer, which can do what we call a universal simulator or digital quantum simulator, or there are a special task quantum computers which does specific problems. It can be a boson sampling, or it can be a quantum annealing, or we are also looking at this noisy intermediate scales now currently, where people are trying to look at, you have noisy systems and you can start working on how we make a better use of it and understand the noisy category. So this is the broad categories which we have. So there are various other problems in academia which we are interested in and try to see how we can make use of the small scale quantum computers which are available. And you really don't need a big qubits for them, and just to understand and build an algorithmic base, right? So this is one of the problems where you have real-time dynamics of lattice gauge theory. These are the problems which, you might all know this Large Hadron Collider, where billions of dollars have been spent by the international community to do certain experiments. Now you can, if you have a quantum simulator and you can do some experiments and have a predetermined idea of how and what experiments is what protocol should exactly has to go to an hadron, or you can save billions of dollars to the world. So that's one of the motivations where it can be a CERN or various other academic communities have got together to see that, to develop algorithms for such problems. This is a simple 2 qubit or 3 qubit problem which was kind of looked some years back, and a lot of progress are going on in that direction. right? So there's another interesting problem, which in fact, it's still an open problem. We all know how efficiently the nature works, the photosynthesis problem, right? I mean, and we still don't have an exact model of photosynthesis. And there is an algae which stays 5 kilometers below in the sea, and it receives just 2 photons in a day, or probably 3 photons, and efficiently converts into an energy. Now, if we understand the whole quantum process which is happening in the algae, and then if we can simulate and mimic them in some other quantum systems, which means that we have actually built an efficient solar cell. And this problem is been something from over last 10 years academicians have been working on. There has been various models, and we also have looked at some particular models. It's been published. All that you would need, if you understand the dynamics, is only about 5 qubits, right? Which means that you can have some device with some equivalent to 5 qubits, and we can mimic the whole process and have a very efficient solar cells. Today's efficient solar cells, even in laboratory settings, are only 30, but those living organisms work at above 90% efficiency. So these problems remain open, and for quantum computers and algorithms, both the directions, to look at it, right? So I mean, we have a circuit for it, but it's only 5 qubit, but this circuit can't go into any existing quantum computers, because the number of operations needed are already to complete this whole process at the current understanding, right? So there is a light which falls on one of the centers, and then it takes some particular paths in superposition and ends up being in the reaction centers and efficiently converts into an energy. So that's the model which is currently accepted by the academicians. It will still get improvised with more work in this direction. Now, if I want to simulate this dynamics, then we have to have some kind of circuits, and this algorithm is there, but we need a processor to be looked at it, right? So there's another interesting problems. With the interest of time, I will just skip this again. There's another interesting problem, again, which can serve the community in labs, is nitrogen fixation, right? So this, again, a very, very useful problem. The whole of our life sustenance is based on how nitrogen is getting converted into ammonia, right? The current classical computers which we talk about can efficiently simulate only one of those F clusters in this whole nitrogen processes, right? Nitrogen fixation processes. And people have been trying hard to use the best of the supercomputers to try to simulate P and F clusters. And there are proposals of how a classical and quantum computer combinations together can solve or try to help in coming up with a proper understanding. The simulation itself helps in understanding how the nitrogen fixation happens. And if you have them, then the whole fertilizer industry and agriculture industry can completely be revolutionized, right? Because it kind of makes things a lot more simpler by understanding the nitrogen fixation problem. So there are problems like this. I know plenty of them. I just picked 1, 2, 3 in the whole process. And there are, again, quantum simulators were the way academicians look at is a quantum simulator is a simulator which is quantum mechanical in nature, which means that there is some real system, and which is quantum mechanical. There is another quantum mechanical system which mimics the system. But I do hear many times there are classical systems which people start talking it as a quantum simulator. They are not. So in fact, if you look at literature, they are very carefully worded, even like the one which IAC and CDAC developed, they call it as quantum computer simulator toolkit, which means that it is trying to simulate a quantum computer, which means it has only an upper limit of simulating what a best classical computers can do. Today's best supercomputers can only do up to about like 50 qubits, 53 qubits, and that's what one can do. So you can't have any classical simulator to mimic quantum system above 50 qubit. You can do some approximations, and one can claim, I know there are some people who have claimed within India we have 500 qubit simulators, but it probably in that 500 qubit there are so many basis states, and they are thinking that okay, you can approximate, remove them all, and only this much is needed, and they are kind of rounding it off at so classical, but this is a very good toolkit. Like what IAC and along with CDAC had developed is that it's a very good educational tool where people can learn to develop circuits, develop algorithms, and they get hands-on experience. If you do it even for less than 30, 40 qubits or 20, 30 qubits, you have a knowledge and you can have a base ready for it when quantum computers are there to be explicitly used. And if you look at Wikipedia, there are about 150 different kind of simulation, what we call as a quantum simulator of classical, what we call as quantum computer simulator toolkit equivalent in in public domain and using different languages. And there is also an IBM quantum circuit simulator and Amazon bracket simulator. So these are all like classical systems which are simulating some close to a 50 qubit. So we have to clearly differentiate the difference between the quantum simulator and a quantum computer simulator. I think the standardization has to come into clearly categorize between them, and then within the quantum simulators, the digital quantum simulator and an analog quantum simulator, which means that something which is universal to look at different problems and something which is specific to one specific problems. And then if somebody claims that we do have a simulator, or if somebody claims that we are developing some kind of, then they should be able to demonstrate what is the quantum phenomena in that process. Like, like Anil Prabhakar was mentioning that if you are saying that it's secure and there's quantum mechanics, the box should be open. So if you say you have a quantum simulator, then they should be able to demonstrate what is the quantum process in that simulator, which anybody can see that, okay, there is this quantum process which is defining it as a quantum simulator. And this standardizations has to come in to fix that, there are various degrees of quantum field. So it's not just superposition. You do not have to always have entanglement. So one has to identify the classes of quantum features which you can consider as something which can be put into a catalog or a manual, say, for these are the few quantum features which can be considered to get into the standardization of the technique, right? So I think I've taken a bit of time, and I would stop at this point and leave it to you. Thank you.
Thank you, Professor Chandrasekhar. I ask Honorable Chair if he has any remarks to make. Okay. So lunch in such serious scientific conclaves is just incidental. But you still want to break for it? So in the schedule, we had to play a pre-recorded message of Dr. Dustin Moody, which we will do post-lunch, immediately after lunch, before we start the 7th session. We thank our distinguished panels for this very engaging, stimulating talk. I request Ghazala Faisalji, DDG TEC, to present memento to Honorable Chair, Shri Umar Shankar Pandeyji. And now I request Honorable Chair to present mementos to the panelists. Shri Ritu Ranjan Mittal, DDG and Head of TEC, Professor Anil Prabhakar, and one for Professor C.M. Chandrasekhar. Three. Thank you so much. We can have a group photograph if you can just step forward, or you may just stand here. So we resume with our sessions at 3 o'clock. Thank you. So we are now playing the pre-recorded message of Dr. Dustin Moody from NIST. He has talked about standardization developments at NIST in post-quantum cryptography. Can we please play it?
Look forward to sharing an update on NIST standardization efforts in post-quantum cryptography. My name is Dustin Moody. I'm from the National Institute of Standards and Technology in the United States. So you're probably well aware of the threat that quantum computers pose to cryptography. It's well known that if we had a large-scale quantum computer, then they would threaten some of the crypto systems that we use today. This is an algorithm known as Shor's algorithm that was discovered in the 1990s. At NIST, I'm in the Computer Security Division, where we have cryptographic standards, and there are several of our cryptography standards that would be threatened by quantum computers. This includes some of our public key cryptography standards, such as 856A and Special Publication 856B, which deal with key exchange algorithms. These include algorithms like the Diffie-Hellman algorithm, elliptic cryptography, and RSA encryption. We also have a standard known as IPS 186-5, our digital signature standard, that includes public key signature algorithms like RSA, DSA, and ECDSA. And because of Shor's algorithm, all of these algorithms would be completely broken once we have a large enough quantum computer. And so we need to find replacements to put into our cryptographic standards. In NIST, we have a variety of other standards as well, dealing with symmetric key algorithms like AES or hash functions like SHA-2, SHA-3, random number generation. All of these would also be impacted by a quantum computer, but not as drastically as the public key algorithms. So for a block cipher like AES, we would need to use longer output. For a hash function like SHA-2 or SHA-3, we would need to use longer output. Excuse me, I think I said AES, we need to use longer keys, longer output. But we can handle that change easier than the public key crypto side. So that's where our focus has been. Now, when we wonder how soon should we worry about this problem, quantum computers are being built, they're being worked on, but they're still pretty small scale. On the center of the screen, there's a well-known theory due to Dr. McKinley Most, an expert in the field, who helps us understand that we need to worry about this problem well before a quantum computer comes out. And that's because if our information needs to be protected for a long time, we need to transition to an algorithm. We need the standards to be developed, all the evaluation and analysis put into products. We need all that to occur first before we can begin providing information security for the information that we have. And if the sum of those two things is greater than the time to the quantum computer, you're going to have a problem. The United States government has been taking action. There have been several concrete steps. I'm going to talk about what NIST has been doing to prepare. And just in the last year or two, as our post-quantum cryptography project has achieved some of our milestones, the United States government has been passing legislation, issuing national security memos from the White House, the NSA has come up with the CNSA 2.0 suite, all with the goal of transitioning as much as possible the cryptography that the United States federal government uses to quantum-resistant cryptography by 2035. We know we won't be able to get everything transitioned by that time, but we want to get as much as we can. This all just underscores the fact that while we don't need to panic, there's not a quantum computer that's built that can break the crypto today. We definitely need to be working hard so that we will be prepared, and we need to be doing things today. Now, NIST started a process to standardize new cryptographic algorithms back in 2016. This is about QC competition. And specifically, we were calling for new algorithms for our public key cryptography standards. This included two different functionalities: public key digital signatures, as well as public key encryption and public key establishment. We saw our role as managing a process, bringing the cryptographic community and the industry together in an open, transparent way, that we would be able to select the strongest and most promising algorithms at the end of this process. We knew this would be a lot more difficult, a lot more complicated than some of the past competitions we've run, but as those have been very successful, we felt good about the process. We said from the beginning there would not be just a single algorithm selected, there would be multiple good choices that we would be able to select. That's for a few different reasons. Because QC is a relatively newer research field, we want to be able to have more than one type of security problem to base our assumptions on. And as the performance profiles of various of the algorithms are different, the different applications, some algorithms will be better suited than others. So having multiple algorithms will be valuable. On the other hand, you don't want to have too many for interoperability. For our selection criteria, we announced this back in 2016. First and foremost was security. And we want these algorithms to be secure against both classical and quantum attacks. Classical we have a bit more experience with. Quantum attacks are newer, and there's not even yet a universal consensus on the best way to measure quantum attacks. In this, we defined 5 security categories, so that when submitters were designing their crypto systems and selecting the parameters, they could try and categorize each parameter set into one of these 5 levels to tell us about how much security they thought they were providing, and then we could use those to compare different algorithms with each other. So for example, level 1, we said a schemes in level 1 that's at least as hard to break as AES 128 doing an exhaustive key search. It would take the same amount of resources to break AES 128 and to break your proposed algorithm. But we similarly defined other levels all the way up to category 5, tying it back to standardized cryptography we already have in this, and use security we have a pretty good idea on. So security involves a number of different ways to measure it. Security reductions and security proofs, the theoretical complexity, the asymptotic complexity, taking a look at the best known attacks, all of these sorts of things. And we recommend that submitters provide a lot of security analysis in their specification. Our second criteria was performance. How do these systems perform on the classical platforms? Because even though they need to provide protection against quantum computers, we are still going to be running them on our classical architecture that we have. So how fast are they in software? How fast are they in hardware? How does the memory look? How big are the key sizes? How big are the ciphertext and the signature sizes? A lot of different benchmarks you can make. So performance, that was our second criteria. And then third, we listed a number of other properties that it would be nice to have as many of these as possible. So as much as possible, be a drop-in replacement, provide forward secrecy, be resistant to side channel attacks, be simple, be flexible, things like that. So our process has been going on a number of years, and we've been through 3 rounds of evaluation and analysis. It kicked off in December 2017. There were 69 candidate algorithms submitted into the process. The tables there show the different types of families that these were based on. Most of them were based on lattices or codes, but there were several other ideas as well. Submissions to this process came from all around the world. We had submitters from all 6 continents, 25 different countries. We held a workshop where all the teams came and were able to present their algorithms. And that first round, after all this specifications were posted online for people to evaluate, all the code was posted, about 25 of those 69 schemes were either broken or pretty severely attacked. But after a year, we selected 26 of the most promising schemes to move on into a second round of evaluation and analysis. and we wrote a report to document our selection and explain why we made those decisions. The second round lasted about a year and a half, where we focused on those 26 schemes. The cryptographic community and industry also did as well. They did a lot of research, a lot of experiments and benchmarks. There was another workshop. Again, more schemes were broken and attacked. And at the end of the second round, we selected 15 algorithms to move on to the third round. This included 7 finalists and 8 alternates that still represented the different mathematical diversity of ideas that had been in place since the beginning. The workshop, lots of research, and finally, in July of 2022, we selected the algorithms that we were going to choose for standardization. So these are the algorithms we selected. For key establishment or equivalent republic key encryption, we selected the Crystal's Kyber algorithm. And on the digital signature side, we selected Crystal's Dilithium, Falcon, and Sphinx Plus for standardization. And we have a report, Mr. 8413, that explains why we selected those schemes. Overall, we expect Kyber and Dilithium to be the main 2 algorithms that people use. They are based on structured lattices and have very good performance and should work for most applications. Falcon has a little bit smaller signatures, more complex implementation. There are some trade-offs there. If you really need small signatures, Falcon might be a good option. And then Sphinx Plus is based on a different assumption, hash-based cryptography. It's bigger and slower, but if you need a different security assumption than lattices, we have Sphinx Plus available as well. In addition to this, we have 4 algorithms, all chems, that were selected to advance on to the 4th round of evaluation. And we also are going to be beginning a new process for digital signatures that I will talk about. So our timeline, this shows us where we've been and where we're going. Where we are now, the 3rd round ended, we selected algorithms for standardization. We're currently working on drafting those standards. We also have the 4th round of evaluation going on for the TOZ algorithms. And we issued a new call for signatures. And so this kind of shows our future work as well. One thing to note is draft standards. We expect to have those ready in a few months, summer of 2023. And we expect the first PPC standards to be published in 2024. So for the chems in the 4th round, 3 of them are based on codes. They're still being studied. It's likely we'll select 1 or 2 of these at the end of the 4th round for standardization. 4th algorithm site was broken almost a year ago, and we don't recommend that anybody use it. The submission team agrees with that as well. Coming up soon on June 1st, we have a deadline for new signature schemes. We want these to complement the ones that we selected for standardization. We're hoping to find a more general purpose digital signature scheme, not based on structured lattices, but that's more efficient than Sphinx Plus. Sphinx Plus is a little bit too big and slow for many applications. That's kind of what we're looking for, although we might be interested in other properties. So after June 1st, this will begin a new process of looking at these algorithms. It'll take many years to evaluate them, and possibly at the end we will select some for standardization. We do not have a similar process for chems currently. We're writing the PPC standards as FIPS. Each of the algorithms will have their own document. It will include a complete specification for how to implement the algorithm. There's many choices that need to be made. We don't expect a lot of changes from the round 3 specification. We've been discussing some of these on the PPC forum and at our workshop as well. But we definitely encourage you to provide feedback to us on any of the questions that we post on the PPC forum, or you can always email us directly as well. There has been some IP considerations. We very much want these algorithms to be adopted, and we know that patents can sometimes hinder that. For Crystal's Kyber, NIST made 2 license agreements with some holders of patents that potentially were related. And so we have that posted on our website, information about those licenses, with the end result being, if you follow what's in our NIST PPC standards, then the license allows for royalty for use of implementations from those those families. So that should hopefully relieve any concerns there. A lot of the focus now is on the transition and the migration. There's been a lot of discussion on using a hybrid mode. That's the idea where you combine a classical algorithm and a post-quantum algorithm in such a way you have to break both to break your hybrid solution. That makes a lot of sense. NIST will provide guidance on transition to PQC standards once we have the standards published. I also want to point out our National Cybersecurity Center of Excellence has a very good project on the migration. So if you want more information on transition and migration, that is a very good place to look as well. In conclusion, NIST is very grateful for all the work and the effort that people have been doing to help us with our standardization. We certainly welcome feedback. You can email us directly or you can engage with us on the PPC forum. That's where we use an online message board where we put announcements and there's a lot of discussion about standardization that goes on there. While we reach the milestone of having standards very soon to be here in 2024, there's still a lot of work to be done in the future as well. Foreground going on, and we have the new call for signatures as well that we will invite people to evaluate. So once again, thank you again for your attention and the chance to provide this update. And sorry I'm not there to take any questions, but you can contact us and we'll be happy to answer them. Thank you.
So welcome back to the post-lunch session, the 7th session of our conclave. Our esteemed panelists, dignitaries, who I'll be inviting on days, will be discussing and making presentations on quantum communication, industrial perspective and use cases. Quantum communication is a secure method of transmitting information using quantum properties, and it has potential applications in various sectors. The session will discuss use cases of quantum communication in the sectors such as defense, finance, and telecom. Chairing the session will be Lieutenant General M.U. Nair, Signal Officer in Chief, Indian Army. It's a pleasure and honor to have him here with us. May I please invite you, sir, on stage? Ati Vishisht Seva Medal, Sena Medal, Lieutenant General Nair was commissioned into the Corps of Signals of the Indian Army on 15th December 1984. He is a graduate of the National Defence Academy, Pune, and a postgraduate from the Defence Services Staff College, Wellington. He has vast experience in command and staff assignments and has served all over India. He has been the Chief Information Security Officer of the Ministry of Defence and of the Indian Armed Forces and has been responsible for protection of critical information infrastructure in defence domain as part of one of his responsibilities. He has represented the Indian Armed Forces at several meetings at national and international levels. He's been part of working groups on cybersecurity and technology-related issues. He was instrumental in raising of the Indian Defence Cyber Agency and subsequently headed the Signal Intelligence Directorate of the Indian Armed Forces. He has the rare distinction of being a Chief of Staff of an operational corps along Indian northern borders, besides being a Chief of Staff of the Indian Army's Central Command at Lucknow. Let's give him a big round of applause. And now I would invite our other distinguished panelists on the days. Joining us is Dr. P. Syam Kumar from Institute of Development and Research in Banking. Dr. Dong Hee Sim from SK Telecom, South Korea. Shri Animesh Aryan, CEO of TACBIT Labs. Joining us also is Shri Dilip Singh, Chief Product Officer, QNU Labs. Shri Vikram Sharma, CEO of Quintessence Labs. And Mr. Bruno Hutner, Director, ID Quantique. Over to the Honorable Chair.
Good afternoon, ladies and gentlemen. At the very outset, let me just thank the organizers for giving me an opportunity to come and speak to you, all of you, on this domain of quantum. Extremely grateful to you, sirs, for calling me over here. Over the past 2 days, in fact, yesterday I was only there for the inaugural session. Post that, I left this venue. But I did follow up on the proceedings through the YouTube videos which are there. And everywhere, right from the first session, post the opening session, the first slide showed the applications of quantum domain is in the defense. So here I am actually, I think, the lone speaker in this entire conclave, speaking to you on how the users like me can actually benefit from whatever you are actually providing. So that's why I thought I'll speak to you. I'm also not going to get into the technology aspects of it, but I'll tell you that being responsible for a large communication network which is pan-India, with the entire army being provided with communication support by me, I think we require a lot of support from each one of you, the academicians, the industry partners who can actually strengthen my backbone. I'll come to that a little later. I'm also sure that each one of you are aware of the importance the armed forces have given to technology these days, since the warfare has actually transcended to a new domain where virtually it's operating on a technology domain. So you look at what's happening currently, the conflicts of today have intense presence of technology-aided tools, and that's where I think we are focusing at this point of time. I have this habit of going through the magazines of recent times, and I came across an article in one of the recent one of the weeklies which are there, and I found that the term quantum was associated with something called it was called as spooky. So I think yesterday also somebody made a mention of it, that it's still, for us who have learned technology a few years back or few decades back, it's still something spooky. I leave it at that. Progress in the field of science often comes from combining different ideas and approaches in seemingly unrelated fields. One of the most successful examples of this is the arena of quantum information, which has been evidently brought out in the ongoing conclave. The combination of information theory and quantum mechanics has led to a new and deep fundamental insight as well as idea into the new applications in computing and communication technologies. This has also significantly contributed to better understanding of various natural physics processes in the form of quantum information. New era of technology has only begun, which can lead to many unforeseen directions with immense potential and positive consequences and opportunities. Like any other development in technology domain, considering the vast array of inventions and advancements which have taken place over the past 100 years or so, and with an accelerated pace in recent years, one may conclude that quantum domain has immense potential in the field of military technology. Some may even define it as new domain of warfare, as Dr. Sumawagis had described yesterday, that we could consider quantum as a domain of warfare. She had mentioned quantum warfare. However, I would feel that it should be considered as an enabler for currently defined domains of military technology. It could be used to assist in protecting the military assets of a nation or for disrupting an adversary's military might. It could also be employed in an offensive manner where the technology is used to break, disrupt, or enable eavesdropping on classical secure systems. The quantum technology has immense opportunities in military domain. Computers based on quantum physics have the potential to solve military problems that would take a classical computer of modern era much longer. I'm sure all of you are aware of this. The huge computing power which will be available on our fingertips will be a major threat to classical secure systems of communication, with both symmetric and asymmetric encryption systems being under grave threat. The way ahead would perhaps be to look for designing and developing quantum-safe communication systems on fast track. As it emerged during the deliberations over the past 2 days, some key areas to focus on would be the domain of QKD based on principles of quantum physics and post-quantum cryptology based on classical physics. Both these fields have large number of use cases in the defense domains. Incidentally, the military networks may be more robust in terms of specifications, policies and procedures, and even network architecture and management. It would be a secure standalone network which is physically air-gapped, as in the case of our armed forces. And it may not be riding on a public service provider's backbone with no interference or connectivity to the internet. It will also be using multiple media, both wired and wireless. Now, I've listened to some of the speakers yesterday and some of the deliberations which came up. Dr. Upadhyaya first mentioned, he had mentioned about the various applications which are there, and one of the applications, key applications which we could actually, quantum computation and quantum communication are something which we could actually work on. We've been working very closely with the CDOT. The QNU lab, I think, Sunil had actually mentioned about hub and spoke model and point-to-point communication links. Now, we are at this point of time evaluating certain systems on point-to-point networks. We look forward to having trials, proof of concepts on hub and spoke model 2, where we can look at networks which are strengthened through quantum safe methods. Applications which were mentioned yesterday included GPS, which we have not looked at so far, the atomic clock, which has immense significance for our networks. But an aspect which we probably was discussed today was on the evaluation methodology for strengthening the networks. As I mentioned, the military networks need to be absolutely robust and secure. That's where we had to have an evaluation methodology, as also some standards which need to be promulgated and which we need to be verified. So this is something which is work in progress at this point of time. Some of the use cases, a quantum secure encryption system could be considered at device level, which could be provided layer 3 as quantum secure VPN, or can be integrated for individual applications as an application layer. The existing TLS protocols may also be considered for possible upgrades on a quantum safe crypto suite. A possible fallout of emergence of quantum technology would be the replacement of the time-tested but resource and logistic intensive physical movement of couriers for cipher key distribution. We have a process where the classical cipher keys are exchanged over distances through physical movement of couriers, which we actually want to get rid of at this point of time. It's extremely logistic heavy for us. A QKD solution can either be satellite or surface communication based between multiple headquarters and users in the field, with the system of cipher couriers being completely replaced for transfer of keys. This is something we are actually keenly looking forward to at this point of time. Quantum safe encryptions using QKD solutions would be added benefit, or development of QKD solutions with existing bulk encryption units being replaced by quantum safe encryptors. Additional benefits would be features such as QRNG capabilities, which if we reduce to chip level can be used in each device to further enhance security. I'm sure all of you would have seen what is available today in the current environment. Quantum secure VoIP phones, quantum secure video conference solutions, etc. are being discussed, evolved, evaluated, all of which have uses in the military domain. I'm sure some of the snapshots were given to you during yesterday's presentation. In one of my earlier assignments, we are working on a quantum secure Wi-Fi network to further enhance the security features of a campus-wide Wi-Fi system. It's still work in progress. Quantum technologies hold immense potential to revolutionize the design and management of protocols for communications and sensing and observation. Mankind's knowledge about the world and our technological advances are limited by what we can measure and how accurately we can do so. Researchers are also learning to use individual particles such as photons and electrons as sensors in measurement of force, gravity, electrical fields, etc. With quantum technology, the measuring power is pushed far beyond what's previously possible. As a nation, we have probably missed the bus in earlier years when far-reaching developments in ICT domain revolutionized the field of communication and networks, as also in chip development. And this is despite our nation's strength in the field of IT and software skills. Today, as the world is looking at a transition from a classical physics domain to quantum physics domain, it's essential that we form part of this endeavor right from the beginning. investments, and dedicated focus on the quantum domain can perhaps make our nation the leaders in the emerging fields of quantum technology, with resultant benefits to us in the military, who will also be part of any of the opportunities and endeavors at national level. We had made a recent entry into the domain by establishing a quantum lab at our Military College of Telecommunication Engineering at Mau near Indore, and encouraging the trainee officers and men to carry out further research and development. The results have been promising, with over 10 small projects in the domain being undertaken by the officers and the trainees there. We'll also look up to any developmental projects being undertaken by the Ministry of Communications, where we can actively contribute with our military might. We have also recently implemented a quantum secure audio video stack, probably one of the first in the country, in one of our units with the support of some of the other governmental agencies. This is being integrated with our homegrown messenger ecosystem for use pan-India and is in work in progress at this point of time. We are open to proof of concepts, trials, evaluations, both in our training facilities as also in field and on operational networks too. So I would request any participants, any members of the academia, industries, if you want to carry out any trials, evaluations, we are there to support you, and our contact persons are available right here. You can interact with them, and we are ready to take on any trials on this particular domain on any field. As a person involved in provision of secure communication, quantum domain offers considerable capabilities. We are assuring you of all support to the industry, the academia, and the government agencies involved in the domain to freely interact with any members of my team, as also the other services, and take this effort forward to its logical conclusion. I would like to assure you that the Indian Army would be there to actively support any initiative and development in the quantum domain. Thank you very much, and Jai Hind.
Thank you so much, sir. I now request Dr. P. Syam Kumar for his keynote address. He'll be elucidating on the use cases in fintech sector. Dr. P. Syam Kumar is BTech, MTech, and PhD in computer science and engineering, and is having 12 years of teaching experience in different institutions. His research interests include cloud computing and security, virtualization and containers, edge for computing, cryptography, and post-quantum cryptography. Dr. P. Syam Kumar, please.
Thank you, ma'am. Good afternoon, everyone. So now I'm presenting IdeaBit developed one product called QSafe. So it is secure the data in the cloud and also secure on the quantum computers. Okay. So when you outsource data, we need to secure the data. So we developed one product called QSafe. So let us start with introduction. So the rapid development cloud, so banks tend to store their data in the cloud to reduce the cost and maintenance. But at the same time, since cloud is not trustworthy, the privacy of data may be compromised. So to protect the data privacy, the bank can prefer to encrypt the data before storing in the cloud. Okay, so once you encrypt the data you stored in the cloud, so it will give the privacy of data. But you don't allow to search out the encrypted data, so whenever you want to get the particular record. So that means whenever you're storing 100 records, whenever you want to get the particular record, so simple encryption does not allow you. Okay, so one solution is we can download all documents and decrypt locally and search it and re-encrypt and upload, but it's not a practical solution for many applications. So to perform search or encrypted data, so public key searchable encryption is proposed. So it will encrypt the data first and store in the cloud. So later it perform the search or encrypt data with the multiple keywords. Okay. So and also you know that traditional public key schemes designed based on the district authority problem and packaging problem. So these problems are vulnerable to quantum attacks. Hence, existing PKI schemes no longer secure in the quantum era. And it is also not providing access control. So then we proposed and developed a quantum safe. It is a quantum safe encrypted cloud storage. So using lattice-based cryptography. So lattice-based cryptography is one of the promising post-quantum cryptography due to its hard problems like learning with error problem and shortest interview solution. So the QSAPE writes on attribute-based SQL encryption from the lattice. That means we develop a attribute-based SQL encryption from the lattice, and it provides the privacy and access control for the bank customer data in the cloud. The security of the QSAPE proved under the learning with problem. So we'll discuss what is learning with problem. So learning with problem is the solving of system of linear equation with the error terms. Okay, if the given hierarchy b equal to a plus e mod q, so our task is find s by given a and b. Okay, so s is a secret and a and b is a public keys. So it is difficult to find s by given a and b, because if you want to find s, you should know the error term e. So e is generating from the Gaussian distribution. It does not reveal anything about the secret. So you can see below diagram, it is a lattice. What is a lattice is it is a set of linear independent vectors. By given a random vector and asking to find a secret vector, it is a very difficult problem. So more precisely, if you have equation a is equal b, it can easily be solved by using Gaussian elimination in a childhood problem. But this problem is very difficult if you add a small lines to this problem. So E is generating coming from the Gaussian distribution. It's a random term every term. So if you want to find secret S, you should know the A. And again, LW is coming in the two terms, search version and decision version. The search version is by given A and you need to find the S. And decision version is, it is difficult to distinguish from the sample is coming from uniform or uniform distribution. So the QSAPE architecture contains 4 entities. So TA, trust authority, data owner, and data users, and cloud server. So TA is responsible for generating public and private keys, and data owner, who is the owner of the data, we encrypt the data using public key and send to cloud server. And later, when after storing data in the cloud, the data user who is authorized to he generate the search query based on some keywords and send to cloud server. Then cloud server search for the, any documents. If any document match with the keywords, you will send that file back to the user. The user decrypt the data and access. So this is the overall process of QSAPE. The QSAPE contains mainly 6 algorithms. So first one is setup algorithm. So this algorithm run by TA. It takes large security parameter and generate the master public and master secret key. And next is encryption algorithm. This algorithm run by data owner. So you take the set of files documents M and set up keywords. The keywords which is extracting from the document set. Next is P. P is a policy. Go to move back. Back. Okay. No, previous.
Red one, proceed hard. I think there is.
Okay. Okay. So the P is a policy which decides that whether people can access the data from the cloud, then public. Then after encryption data and outsource to cloud, the ciphertext contains 2 things. One is a ciphertext of the documents and cipher of the index. Then key generation algorithm is generated, executed by TA. It generates the private key, secret key for the data users based on his attributes. Here, every user has their own secret key. Then trapdoor, whenever user want to get a particular file, you will generate the trapdoor based on selected keywords and send to cloud server. Then search algorithm is executed by cloud server by taking input of ciphertext and trapdoor. So if any file match with the trapdoor, you will send back that file to the user. So finally, user decrypt the data with the secret key. So these are the 6 algorithms QSAPE contains. So what is the overall process of QSAPE is? It mainly contains 2 phases, setup phase and retrieval phase. In setup phase, which happen before sending data to cloud, and retrieval phase will happen after storing data in the cloud. So before storing data in cloud, what you are doing is, first we are building the index by extracting the keywords from the documents. Then after building index, we encrypt in the both documents and index and stored in the cloud. So later, whenever authorized user want to retrieve the particular file, so you will select the some keywords, and based on the keywords, you will generate the search query. The search query will send to cloud server. Then cloud server will search on the encrypted index for the matching files. If any matching files will, if any file match with the keywords, that particular file will send back to the user. Okay. So this is what we are storing data in the encrypted form and also getting the data back in the set of the encrypted data. So what the key safe object is? So main object of key safe is protect the data price in the cloud. So since data stored in the encrypted form and also retrieving based on the set or encrypted data, so there is no way for another user to access the data in the cloud. Now key safe also provides fine grained access control. So since we encrypted, we developed this one is RTPD based searchable encryption. So RTPD based encryption is a one-to-many encryption. So with a one public and many private keys. So it will allows only authorized user to access the data from cloud and restrict the unauthorized users from accessing data. Next is the key safe is secured. The security of key safe is proved on the learning with problem, which restricts the quantum attacks and also provide the long-term security. And it is both secured on the classical computer and also quantum computers. And key safe is efficient. So this key safe is designed based on the lattice cryptography. It does not require any pairing, heavy pairing operation, which was there in the traditional schemes. So that is efficient than existing schemes. Summary. So IDEA-BT developed a key safe product to protect the data privacy in the cloud and also secure on the quantum computers. So bank can use this key safe product to store data in the cloud and also retrieve the data without disclosing any information. So we are giving this product to banks as a POS. Thank you.
Thank you, Dr. Kumar. Thank you so much. Our next keynote speaker is Dr. Dong Hee Sim. He's been actively involved in global standardization activities for more than 15 years, including 3GPP, OMA, IEEE, HC, and ITUT. For the last 11 years, he's been with the SK Telecom, out of which for the last 5 years, he's been leading activities for the global standards and ecosystem development for quantum technology at SK Telecom. Dr. Dong Hee Sim.
Thank you for the introduction. Actually, my name is Dong Hee Sim. She asked me how she should call me Dong Hee, Dong Hai, but both is okay because some people call me Dong Hai. I think it's a very welcoming name, so you can call me Dong Hai too. So it's obviously a difficult name to pronounce because I'm the only Korean in this room, a bit strange, but I'm very happy to be here because to be honest with you, when I was invited to this event to give a talk, I was a bit curious, also a bit surprised because India quantum. So, but when I heard all the presentation made yesterday and today, I was really surprised and impressed by all your achievements. So really congratulations to your achievements actually. So thank you. Also thank you for the special thanks to all the organizers and the so your hospitality, etc. Also the people behind the scene. It's really hard work for them, especially Atul and Rakesh too. So my talk is about the quantum safe communication infra in SK Telecom. Basically, it's what we have achieved so far. So let's see that. So everybody's talking about this button. So I hope this is. Which one? This one. Yeah, I did. Sorry. Too much. It's okay. Because I'm here today, so I will talk about briefly what have been achieved so far in SK Telecom side. So from 2011, we established our own quantum lab, actually. So to build up QKD devices. So in 2014, we developed the first QKD device by our own. And then we tried to build the QKD network in LTE 2016. And then during the collaboration, during the development of these QKD devices and QKD network, and we heavily collaborated with ID Quantic from Switzerland. So we decided to invest to them, ID Quantic. So we actually now majority shareholder at the moment. And then we tried to build up QRNG applications, and then we also deployed the QKD network for the 5G. So we use QKD for our network, and also we put the QRNG into our 5G authentication server too. And after that, we collaborate with the Samsung to put QRNG. You may probably saw the QRNG chipset in the ID Quantic booth. So we put that ID Quantic, the QRNG chip into the Samsung mobile phone. We developed already 3 models already. Now we are working on the quantum sensing at the moment. So it's been over 10 years journey for the quantum technologies. So I'd say we are maybe the most advanced operator in the world for the quantum technology, especially QKD and QRNG. Okay, so now talk about our LTE 5G backbone. So this is our first attempt for the QKD, which is the point-to-point actually. So this is southern part of South Korea. So in 2016, we tried to put QKD devices developed by ourselves to put them in our LTE network and back home. So there's 2 cities in southern South Korea. So I guess the distance between two cities was 50 kilometers. So we developed put the QKD devices in the LTE backhaul. That was our first attempt to try to QKD network. That was point-to-point actually. And then for the 5G in 2019, if I remember correctly, we try to continue to put the QKD devices into our 5G backbone. So if you look at the left figure, that is Korean Peninsula. So if you look at the 3 dots over there, there is our main switching center for the 5G backbone. And then you can see the 3 cities there, Seongsu and Dunsan and Tapyeong. This is name of the area in South Korea. And then you can see the big, this is a laser, I guess. This is, no, I'm laser, this one. Okay, so you can see this big, the switching center over there, Seongsu, Dunsan, and Tapyeong. And then we put them, the 3 trusted nodes between 2, and then 2 trusted nodes between them. So between 2 switching center, that was 221 kilometer, and then between 2, there's 109 kilometers. Totally, it's about 303 kilometers, which are covered by our QKD devices. So we basically use a trusted node concept. We heavily collaborate with ID Quantic, and then we use them, their devices, to protect our backbone. So this is our basic use case to protect our backbone, to protect our data for the customers. So that was I guess, the first attempt for the 5G backbone in the world, I guess. And during the process, as an operator, it is extremely important for us to control and manage our network equipment. So everybody talking about QRNG, QKD, and PQC today and yesterday, but I think that you have to remember that the QKD, maybe it is very QKD-centric and QRNG-centric, PQC-centric, but if you want to use them properly in the current network, you have to also control and manage properly. So from our perspective as an operator, which is extremely important, so we try to control our QKD devices properly, not manually, which is expensive. So we have to develop our own platform to manage them. So you can imagine we have our optical network, which we use actually SDN as software-defined network concept to properly control and manage them. But for the QKD part, we developed our SDN to control both them. And you need to synchronize both them, the optical part and then the QKD part, and then we developed a platform to control and manage both networks at the same time. And then we went to ETSI, which is European Standardization Organization, but it's also global, like ITUT. So we tried to develop the new standard for the SDN, the interface to control both networks at the same time, so which was already published by we made an effort for that. So this is very centralized control for the QKD, which is quite convenient for us to control the network equipment as QKD network, treat them as one of the QKD devices, network devices in our network. So you think this is extremely important to be used properly in the commercial network. You have to remember it's not all about QKD. You have to have other mechanisms to control and manage if you want to really control and manage properly in your network actually. So that is QKD part, but for QRNG part, we also try to use QRNG as demonstrated by Bruno and many other colleagues today. And we actually, if you are familiar with the LTE and 5G specification, you have to have a random number to authenticate your users. There is authentication vector, and there are 4 parameters in it, and one of them is a random number. So you have to put the random numbers in it. So you have to have your own authentication server, and then we try to use the QRNG instead of the current available, the RNG, to authenticate our users. So we use the RNG Quantic QRNG appliances to put them into our authentication server. And then, as I said before, we collaborate with the Samsung mobiles to put the QRNG chipset into the mobile. So it's like a vice versa. It's in both directions. We try to use quantum technologies as much as possible. So this is another attempt. It's not to try to protect our network. It is over there are use cases for the vertical sectors. So you can see there is a power sector and finance sector. So NICE is kind of security, a credit information company. So we try to collaborate with them, the power sector and also this security sector, the finance sector, what I'm saying, to protect their data and headquarter, between headquarter and then their data center. So it's P2P actually, but we try to build up the vertical sector use cases to try to use, try to convince them to use QKD as much as possible too. So this is another use case. And now talking about the New Deal project, which is funded by the Korean government. During the COVID time, they wanted to have this kind of the project as a stimulus package for the Korean quantum safe infra. So it was done from 2022 at about 3 years, and the budget was about 29 million euros. You know, is the exchange rates fluctuate all the time, so it's about 29 euros according to the current exchange rate. So if you see this part. This actually, the first part is actually the QKD part. So we collaborate with the other operator to interconnect two QKD networks. So I will get into that after this. And then this part, oh, sorry. I have to go back. Excuse me. So this part is actually testbed for the other QKD protocols. So they develop the QKD devices in it, and then they really try to various protocols in it to really testbed. And oops, sorry for my mistake. It's a bit. Go back. Go back.
It's the end of the conference. It's time.
Sorry. Okay. So and then the last part in this part actually is for the PQC. So there are 3 testbeds funded by Korean government. So the important part actually this one to collaborate with the other operators to interconnect two QKD networks actually. So as I said, we developed our own QKD network, but we want to extend our coverage to collaborate with the other operators to have a QKD network. So you can imagine there is a border nodes between two networks. So we developed collaborate with other operators to have a border node to interconnect, to deliver the keys between two operators, which is also quite important example. And so that's why we try to have inter-domain QKD control, which currently you are working on in Etsy side. We actually submitted 2 new work items to standardize this kind of interface between 2 domains, 2 operators, which were already accepted to work on actually. So in Etsy side, so which is based on also SDN concept, software defined control. So as I said before, the 18, the Etsy specification was about the controlling both optical part and QKD, but this is the inter-domain QKD part between 2 operators. So we heavily collaborate with the Telefonica and Deutsche Telekom in European operators and to define this interface. So we will do that to publish this specification soon in Etsy site. So this is another many examples for the vertical sectors. So it's also funded by government, not just about the QKD network. So you can see the health offices and water services and the hospital, and then also even factories. So they try to use QKD as much as possible to protect their own critical data, for example. So there's many examples out there, so you can maybe refer to that. Now the National Convergence Network, which interconnect all the government agencies in South Korea, which I believe is one of the largest government QKD network. So I think the Bruno already presented slightly yesterday, but this is the Korean Convergence Network for the e-government. So Korean government side wanted to interconnect all the 48 agencies in South Korea to interconnect firstly broadband part, and then on top of that QKD. So QKD actually covers 800 kilometers at the moment, I think, which is the longest one for the government QKD network. And then on top of that, key management. So they basically 3 layers out there. It's broadband infrastructure and QKD and then key management. You can imagine how complex it is, but we heavily collaborated also ID Quantic to put them devices into our for the government the network. So we call it Korean Convergence Network for the e-government, which basically behave as one big data center for the government data. So which is we are quite proud of it at the moment. So as an operator, I explained to you many use cases. So we try to build up the QKD testbed at field test, etc. But also, as I said, it's not just all about QKD. We have to manage properly to our network equipments for the QKD devices too. So if you really want to build a QKD network, then you need to think about how to control and manage properly that one. Also, I guess the next maybe step is network architecture design. So we currently think about the one domain particularly at the moment, one company, maybe one government, and one university, etc. But if you want to extend the coverage, you have to think about interworking, interdomain, etc. So you need to think about this architecture perspective and design too. So maybe that is another maybe milestone to be achieved in the standardization too. So everybody talking about P2P QKD, it was done that, and then trusted node was introduced and then to build up QKD networks, but still silo pilots, and then now we think about a multi-vendor even. So for example, if you want to have a multi-vendors, for example, as an operator, we normally use at least 3 vendors to deploy them. So, but currently we are using ID Quantic. But if you want to have a Toshiba devices, for example, then you have to think about multi-vendor network to properly manage them, also how to interconnect them also. So as an operator, which is quite important, so you have to think about, maybe you now think about just one devices at the moment, but if you really seriously think about QKD network, then you have to think about this multi-vendor concept too. So we are at this moment, and at decided they're working on it, and then I just constantly said that the control and management is also important. As I said, interdomain, inter-operator is now the topic at the moment, and then to build up quantum internet, we need to think about quantum repeater and quantum routing. Maybe it is in the future, I guess. So there are several stages, and then so we are actually at the third, in between 2 and 3rd phases at the moment. So we are really have to have actually as a next step, I'm talking to many operators, etc., but they have a different concept of key management on top of QKD network. So we have to synchronize and terminology and how to build up QKD, the key management, etc. So we need to have standard for that maybe. And then modular building blocks and standardization interfaces for the QKD network, maybe it's needed too. And then if you want to have global network, then interoperability for carrier grade interdomain, it's really need to be emphasized. So before going to ending my talk, we need to talk about also the integration of the QKD in the operators network. I'm constantly emphasizing that. Also, we need to think about integrating QKD in the current encryption solutions. That is 2 pillars need to be attacked in the future. So thank you for your attention. So thank you. Thank you again for the invitation.
Thank you, sir. And coming up next is Sri Animesh Aryan. He's the founder, CEO of TagBit Labs. He founded TagBit Labs, a deep tech startup focused on quantum communication technologies. TagBit Labs is one of few companies in India to have worked with Ministry of Defense, Government of India. He has close to a decade of experience in quantum technologies and worked in reputed institutions like Nanyang Technological University, Singapore, RRI, etc. Sri Animesh Aryan.
Okay. Yes. So, good afternoon, everyone. I feel privileged to be standing here and addressing this August gathering. I thank organizers Kishore Babu sir, Abdul Kaim sir for making this event such a phenomenal success, because you have been able to do one Herculean task, which is bringing all the key stakeholders on a single platform. So, thank you for giving us this opportunity. We are living in exciting times where new discoveries, especially in the quantum domain, are unfolding new possibilities for a brighter future. The speakers before me have already addressed different aspects of QKD. In my presentation, I'll be focusing on applications of quantum technologies in general and QKD or quantum secure communication specific. I hope at the end of the presentation, you will be able to appreciate the applications of quantum technology and how it unfolds in the near future. So without further ado, let me jump into my presentation. So, okay. Yeah. Okay. Just for the sake of this our presentation, let me define the 4 verticals which are important in defining any quantum technology that we talk about. Which is being an umbrella term to define one or more of these technologies, which is quantum computing, quantum cryptography or communication, quantum metrology, and quantum memory. And in all of these technologies, we have some of the properties of quantum physics in play. Among the 4, quantum cryptography is the most mature and is being already deployed in different parts of the world. Right. To briefly talk about us, we are an aspiring quantum communication startup, and we have about 24 people in the team, and we have a collective experience of about 100 plus years in the field. These are from different kinds of reputed institutions, from RRI to IISER Pune to IITs and also Max Institute. What we do is that we use quantum technologies to build quantum enhanced solutions. In the quantum secure communication and quantum internet, we have products while we do customized solutions in imaging, sensing, and also on algorithms. Our capabilities are in both fiber-based QKD and free space QKD, as well as QRNGs. Whereas in case of quantum imaging and quantum algorithms, we are kind of early, where we are trying to run and build some POCs. We also have our own entangled photon source, which is kind of a compact source for space applications. Now this is one interesting slide which talks about what kind of adoption we are looking at towards in quantum technology. So if you can look, majorly it is focused in US, Europe, China, India, South Korea, Japan. These are the prominent geographies which are or likely to look at adoption of quantum technologies. There are several reasons for that. People are looking at using the quantum advantage in computing, something to circumvent the adverse side effects of quantum computing, which I'll talk about. Right? There was one key thing which I wanted to address was while discussing with many people, people think it's quantum versus classical. I believe it is not. Quantum is never going to replace classical computing. Classical computers are efficient to address most of the problems we have. Quantum computers, on the other side, are better in solving problems like optimization or data analysis and some simulations which were not really possible using the classical computers. So this is how quantum computers will exist along with the classical computers. And of course, these are able to address some core issues, and we will see what are the applications of QT. So quantum technologies will almost affect every industry we can possibly, or sector we can think of, right? From government, defense, healthcare, space, finance, telecom, and critical infra. I mean, one analogy probably which I can draw, about 40, 50 years ago, when laser was invented, nobody knew it could be used in fields like medical imaging and doing something basic scanning of barcodes to QR codes and fiber communication. Everything actually came into picture the moment laser was developed. I believe this is what quantum technology is going to unleash, where almost every sector, and these, we are only scratching the surface now, where we see applications of quantum computing in healthcare, where whatever you could do in terms of drug discovery and having 5, 6 candidates run over a trial for 10 years could be simulated on a quantum computer. And thus, they can also try to solve optimization problems to reduce the impact of transport in climate, and almost every sector which relies on cost-efficient delivery to logistics to manufacturing, everything which we think quantum computing will make it, at least it's a promise that it will make it much more better. Right. The four things that we talked about, which is quantum computing, quantum communication, and quantum memory and quantum sensing. Quantum cryptography mostly came into picture because of the advent of quantum computing. So it was designed more as how to counterbalance the development and the risk possessed by quantum computers, which we see that quantum computers are becoming more powerful, and therefore the threat of quantum hacking cannot be ignored. So whatever data that we have today are either already compromised or at the verge of being compromised. Obviously, the first victims will be governments, banks, defense organizations, and therefore it's important to look at how to be safe in a post-quantum world. We always think of whether it is too early or too late. I believe that the timelines for quantum computing to be applicable in this context could be in few couple of years. But the harvesting which constantly happens is something that we have to worry about, and it's important that we are prepared to be having quantum safe methods in place. So this is what the Y2Q problem is, and this is kind of an example of how the conventional cryptography works, which is actually not quantum safe, versus quantum cryptography or QKD, where we are able to take care of all the three things, which is right from the algorithm to the channel to the key. Everything is secure in this aspect. Of course, it also has its own challenges in place, but what we see is that quantum secure communications has a variety of applications for strategic applications in defense, for military intelligence, for confidential projects. Whatever that we look at in terms of security is going to be crucial to prepare yourself in a post-quantum world, and therefore we are talking about quantum proofing your data for tomorrow. That's what quantum secure communication does. There are plenty of use cases, as I think some of the use cases the panelists before me have already highlighted. But this is mostly focused on the bulk of the data which lives and goes into the network, and how to ensure that that data is safe against quantum computing attacks. Right? These are into data centers, in telecom, in critical infra, you name it. In passive optical networks, everywhere that we look at, this is going to be very helpful. Right. In the near term, what we see is that we'll be using the fiber connectivity in place for applications in data centers, in banks, in Industry 4.0. The long term is when we will have a much more larger network of quantum satellites in place, which will exist with the terrestrial network. And this is going to be, we would call as the step towards the quantum internet. Right, so that actually completed our applications in quantum secure communication. This is actually on quantum imaging and quantum sensing. So because of the advantage of quantum, we should, we are able to look at something beyond the, the diffraction limits. So we are looking at, medical imaging systems which will be revolutionized using quantum sources. We will be able to also, some of these application use cases have been already done by ID Quantic, which to, do a thorough imaging in a very dense and snowy atmosphere. Some of these sensors, especially UK, is focused on quantum sensors for diagnosis of heart-related issues. Right. So now we are, this is also on the global landscape of quantum secure communication. It's China who is probably, I believe, is actually miles ahead. So with about 5,000 kilometers of quantum network already in place for their strategic communication. Japan also has a quantum metro area network in place. India on the other side has also joined the league, and we have also been able to demonstrate QKD over a longer distance. I believe with the support of all the industry and academia and the government, we should be able to build a future which actually exploits the quantum technology and unleashes the advantage. So yeah, that brings to the end of my slide. Thank you so much.
Thank you, Mr. Aryan. Well, Dr. Bruno Huttner has contributed to 3 of our earlier sessions, and we look forward to his talk once again. He is the Director of Strategic Quantum Initiatives and QKD expert at ID Quantique, Geneva, Switzerland, and also the co-chairman of Quantum Safe Working Group, organized by Cloud Security Alliance, and expert in quantum cryptography. Dr. Bruno Huttner.
Thank you. Okay, let me make it short. Okay, so one last time, I'm happy to be here once more. Since we had many talks until now, and especially we had a full session, several talks on the post-quantum cryptography, I will really emphasize the quantum thread to start with, to give you a little bit of a different insight of how you can understand a quantum computer. So obviously I'm not going to explain everything in 12 minutes, I was told. But I will try my best to at least give you the flavor of quantum computer. So the quantum computer is basically working with qubits, and as we know, the main thing is that it's working with superposition of states. And working this way, it basically behaves as a massively parallel computer. And the way to see this, I think, is to make the comparison between a classical and a quantum computer. A classical computer, you can see, we take the model of a maze. Okay, this is what I represent here. And the classical computer will try to explore the maze. So you start at the beginning, you make one step, and then another one, and another one. And in many instances, actually, a calculation is not deterministic. In many instances, you have a random choice which way you want to go. When you have the fastest algorithms, they are never deterministic. But there is also always choices which you need to make on the way, which are random. So basically, classically, you start at one point, and you move through the maze, each point at a time, and you arrive somewhere. And many times, it's not the right point, and therefore, you got to start again. Okay? So that's a classical way to see computation. What's happening when you have a quantum computer? As I told you, when you have a quantum computer, you don't make the choice, but you make a coherent superposition of the states. So you can see that as basically, instead of going one way or another, the quantum computer will go all the way and explore in one go all the possible venues of this maze, go all around it, explore everything, and then when you measure, will collapse. And obviously, it can collapse anywhere. But then, if you are clever and you organize the interference between the paths you have it's called quantum choreography. And if you organize that in a way that the probability is higher in one direction than another, then you have a good chance of reaching the end of the maze very, very much faster. Of course, it's not always the case, so you may have to do the calculation again and again. But normally, after a few times, you reach the end of the maze. So that's, of course, many quantum computer scientists would probably jump at me at this time, but I think it gives you a flavor on the two main ingredients of the quantum computer here. It's really the coherent superposition of all the possibilities and the interference which you can manipulate in order to reach the right point. With that, Of course, we know that a quantum computer can give lots of opportunity, as we discussed before, and lots of threats. And of course, the main threat we see here is the threat to cybersecurity. So here I'm not saying anything new, so I think you all know that, so we can go fast. Maybe I will even be faster than my 12 minutes. So what's at risk, really? The main thing which is at risk today for cryptography is asymmetric crypto, as we know, because the quantum computer will break it. And as many of my colleagues said that, told earlier, a big problem is encrypt now, decrypt later, which means that even if you have no quantum computer, you know that within a few years, every data encrypted might be at risk. So let's go to solutions. And again, we know what are the possible solutions. They go into two possible directions. One is classical. And the strange thing is that when you talk about post-quantum crypto, you have to realize, and many of my colleagues told that earlier, but repetition is never bad. Post-quantum crypto is totally classical. Really, you use classical algorithm on classical computers, and you hope that they will resist a quantum computer. You need to choose the right mathematical problem, and you need to make sure that it's solid enough, both classically and quantum mechanically, to replace what we have today. The other direction you can go to find a good solution is, of course, quantum. I call it quantum versus quantum. And you use the very properties of quantum systems in order to manage the threat against the quantum computer. What we have today is quantum random number generator on QKD. And if you don't know what it is, I think you've lost your 2 days here. And in the future, we hope to have full quantum networks where we can exchange qubits all around the world, locally first, and then all around the world, which is the quantum internet. So you see that quantum systems, quantum technologies are not totally developed yet, and that's why we are working to develop them here. Different solutions for different needs. So that's really where I think we start something a little bit more interesting than what I said today. You have very different crypto functions you need in a network. And each crypto function will be realized by one or another of the previous solution. Randomness, I hope I convinced you that the best way to get randomness is really through quantum. It's very easy. Quantum mechanics is non-deterministic. You make a measurement, poof, you got randomness. That's the only way that is so easy to make. Authentication and signature, on the other side, quantum mechanics for the moment have not proved itself at all on this one. If you need to authenticate yourself, today you use classical solutions. However, it doesn't mean you use only mathematical solutions. You got so-called physically unclonable function, which could be physical solution to solve this problem, but they are also classical. So you see, not one solution for everything, you can mix them. Key exchange mechanism, this of course we have seen many, many times. You got both mathematics with post-quantum crypto and quantum key distribution to realize that this kind of function today. So again, both of them can be used. Encryption, for some reason, so far is really much better with mathematics. You very seldom try to use quantum mechanics to do encryption. I've seen a few examples during this colloquium, this conclave, sorry, yeah. We had this discussion yesterday. It's still hard, but okay. So during the conclave, we had a few ideas. So maybe there are also quantum things to do encryption. But today, let's say 99% of encryption is really done with maths. So you cannot really decide what is best. If you ask me what is best, I tell you, depending on your use case, depending on the function you want to do, obviously one can be better than the other. I'm not going to read through this table. I just showed it to you. Maybe it will be available if people want to see afterwards. But basically, this is the same table as I showed before, but with all the details to explain a bit more. So I will just take two cases. First one is authentication. And obviously, again, quantum key distribution does not address authentication. So there is no way you can authenticate Alice to Bob if you don't use something else. Today, for quantum key distribution, we mainly use pre-shared keys. We can also go to good post-quantum algorithm. We can do whatever we want, but we need an initial pre-shared keys. If Alice has never met Bob, there is no way she can know who it is. So the only way is either they share something in common, or they trust somebody to give them something that they know will be in common. So somehow you need something to do that, and quantum cannot do it today. What quantum can do very well, QKD versus post-quantum, is really time dependence. Today, any kind of mathematical solution for key distribution relies on computing, and we know that because the computing power is increasing all the time, because the algorithms improve all the time, the security of the key exchange is getting lower and lower with time. That's the standard way for all mathematical systems. And what happened with RSA and ECC is that suddenly there is a quantum computer and then the security will drop to zero. We didn't forecast that many, many years ago, but this is what's happening. What we do today is we put post-quantum crypto. There will be a decay, and we have seen that already. The parameters used today for post-quantum cryptographic algorithm, which are being discussed, have increased a lot since the first choice, because people realize that it's not as safe as they thought for a given set of parameters. So you see that if you encrypt today, if you use post-quantum crypto today to exchange a key, the security will go down. For QKD, it's not the case. For QKD, if the eavesdropper can eavesdrop, it's only at the time you exchange the key. There is nothing left afterwards. Either Eve has the key, and we hope that we know it, because that's what quantum mechanics is telling us, or Eve will never learn anything about the key, because there is no mathematics behind which hides the key. So I think if you want to exchange keys and keep them safe for a long time, QKD is definitely a good idea if you can use it. I don't think I need to go back to all this because it has been exchanged before, and we know the risk associated with post-quantum algorithm. What I would like to emphasize is that we have seen today many classical risks. We've seen many of the algorithms which were actually destroyed already, or at least the security has been degraded. Even Kyber security was degraded by an attack from an Israeli group, Matzov, who found a way to basically destroy the first level of Kyber, with the others are still safe. But what would he know about the future, basically? What is more important, in my opinion, is the quantum risk. Today, we don't have a quantum computer which we can use. I'm quite sure that the day we have quantum computers available to all of you, there will be some clever people who will find new algorithms because they will play with it. Before you play with a quantum computer, it's really theoretical. The time you have it in your hands, or you can access it over the internet, I'm sure that there will be many, many new quantum algorithms, and one of them might be able to destroy what we call today post-quantum cryptography, and maybe we should change the name at some stage. And of course, I think it's interesting to always remember that we cannot really easily predict the future, okay? So something might happen which will destroy everything. And therefore, my message to you would be that whatever you do today, do not replace what you had, but add layers. That's why I called my talk the idea of the onion. Okay? If you have one layer and you add another layer and then another layer in such a way that to destroy the system you need to destroy layer after layer, you can be reasonably sure that at least one of the layers will be okay. Do not mix different things within the same layer. Do not put QKD with PQC together, because then if by breaking PQC you break your QKD layer, it's no good, and the opposite applies. So build your security as an onion, okay? Do not chop it, even though we want to make curry, maybe, but that's another story. So today, make the security as an onion, build it, use what you have, add a post-quantum layer, it cannot be bad, add a QKD layer whenever possible, and this way we hope that we can withstand the threat of the quantum computers and maybe other threats we haven't discussed so far. And I think I'm at 13 minutes. Thank you very much. It was a pleasure being here.
Thank you for being so precise. We know you're from Switzerland. So now our next keynote speaker, Shri Dilip Singh, is the Chief Product and Technology Officer at QNew Labs. He's a pioneer in innovating, developing, and commercializing quantum communication products. He's been the leader in developing complete QKD product suite at QNew Labs. He has over 30 years of experience in the digital product engineering space across telecom, media platform, industrial IoT, datacom, and defense electronics. Shri Dilip Singh.
So hi, good afternoon everyone. I know it's post-lunch and I think tea is just outside. Hopefully I'll try to finish it off in 10 minutes. So I would use this opportunity to actually present certain activities that we are doing at QNO, especially focusing around free space QKD. So it's a interesting area. Of course, we talked about the terrestrial QKD, the QKD networks, and so on. But obviously, if we have to actually have a global coverage of QKD and try to look at quantum internet or equivalent, free space QKD is something which is absolutely important. So I take this opportunity to present what's happening around worldwide. What is it that are the key challenges when we actually have to build a free space QKD system? And we'll talk about what is it that QNO is trying to do, and also trying to hope, and I'm hoping very seriously that we actually would together as with academia and some of the industry partners we can come together and actually try to have this complete solution for India, which actually we have been working on for quite some time, which we call as Quantum Shield for India. So just start with that. So I think this is what I think probably the font could be a bit less, but then this is what is actually happening worldwide. So on a free space front, China actually is leading. So since 2016, I think they have deployed satellites, and they did proof of concept in 2016, and then they extended their network. We have some work happening in US and UK, which is already there. The rest of the countries, I think they're planning to have satellites in this year, later this year, or early next year. So as we can see, we have work happening in Australia. The European Consortium is there. We have work happening in Canada as well as Germany. So there are multiple, let's say, proof of concept, technology demonstrations, and networks which actually are being created worldwide. And we at QNO also are actually going towards in the same direction. If we try to understand the whole free space QKD system, right? So it is not a very easy thing. So for example, if I have to do, let's say, a ground station and I have to connect to a satellite, I don't want my ground station to connect to only one satellite, right? So I want my ground station to probably connect with as many satellites. I want my satellites also to connect to as many ground stations, right? Because they will be moving, and I like to have that coverage. Then I want them to be basically operating continuously. I don't want to lose the key when, let's say, it is daytime, or let's say when the environment is not so good, and because then it is not a reliable setup. So there are lots of expectations which basically we would like to have from a free space QKD system or a satellite-based QKD system. So wherein we want it to be continuously operating with full reliability, day in and day night, and all sorts of permutations and combinations. But the reality is slightly different. The reality is that it's single photon which actually have to cross the atmospheric layer. There are lots of disturbances in the atmosphere. You can have rains, you can have storms, thunderstorms, and then you could have interference coming from the atmosphere, which actually is going to spoil your receiver. So it's not a very easy thing. The second thing is that because we actually operate at a very low power level, so most of the QKD technology I think operate at minus 85 to minus 90 dB or so. So at that level of power, it is very difficult to basically do switching. So for example, if you have one hub and you have 3 or 4 satellites crossing and you want to basically create all sorts of permutation combination, it is not so easy. Also because when the ground station is able to see the satellite, it actually is at a distance of, the horizon is probably, let's say, 1,000, 1,200 kilometers or 1,500 kilometers. So the more the distance, the lesser photons you receive and the lesser keys you will get. So the visibility to the actual satellite is when, let's say, you're at least looking at plus 70 on each side. So the time duration wherein you get actually to generate a reasonable set of keys is very, very less, right? So that's a real challenge. Also, if you look at it, unless let's say there is a huge set of users and we have deployment worldwide, the cost of operation is not very cheap, right? Because let's say if you just want to connect 3 metro cities, you actually would need at least 2 satellites and 3 ground stations and maintain an entire operation day and night. So it's not very easy thing to do. Right? The other challenging thing is that if you look at, let's say, the divergence that happens in the atmosphere, right? So let's say if you have a beam coming from the satellite is at 500 kilometers, and the moment it touches the atmosphere around 20-25 kilometers, it will start dispersing. So you can imagine, right? You have an inverted beaker, right? And the beam is typically coming straight when it comes from the satellite. The moment it hits the atmosphere, it just spreads like this. So if it spreads, then what happens is that the single photons basically get distributed over a very wide area. So if I talk about the technology, for example, today, so ISRO has a technology to actually have the alignment of let's say around 2 to 5 milliradians, right? Which is probably a kilometer or more 2 kilometers if I talk about a LEO satellite at 500 kilometers. Whereas if we have to have the free space satellite capability working, we actually need a maximum dispersal of, let's say, 50 meters. So we are talking about a technological change from, let's say, 2 to 5 milliradians, so to actually 1 to 2 microradian, which is 1,000 times improvement on what is existing today. So that is basically, I think, talk about the next slide, what were the key challenges. So I only talked about the dispersion, I talked about ground station challenges, the cost of operation, and so if I talk about the most significant problem or challenge that we have, it is actually the aligning and pointing. So India does not have the capability. I think there are very few countries, UK probably had some, China has it because they have done QKD, because otherwise you don't need this type of alignment. So we need to actually have a pointing and tracking system which actually would give me a alignment of 1 to 2 microradian. That is one. The second thing is it's not just about aligning, it's actually keeping the alignment on when the satellite is moving. So you cannot move beyond that alignment, because the moment if you move out of that, then I think the whole operation would work. So now if you add the complexity of each ground station and satellite acting as a hub, when I say hub, it means the ground station is able to connect to multiple satellites who would actually do the same thing. Then the complete enormity of the complexity actually increases multifold. So we at QNU, basically, we are trying to work and solve some of the problems. So this is what is the vision, right, that we're talking about. We hope that we would actually have our satellite probably third quarter next year. If I look at the graph, right, especially with the focus on creating a quantum shield for India, minus the satellite, we already have the rest of the stuff. We actually have the capability to do point-to-point, we have capability to do hub and spoke. But India being, let's say, a pretty large country from distance perspective, one end to other end is around 3,000 kilometers or so, with areas where, let's say, we only have forests and barren lands. So that is where we feel very strongly that with the satellite coming in, we can actually make sure that we can do interconnect across cities and then have local metro area networks in cities, and then have a complete ecosystem wherein we would be actually able to create any sort of network India-wide, and of course if we deploy it, the satellites outside, and we can actually do a complete secure quantum secure communication worldwide. So this is something which, so this is one piece which we're just working on. So as I said earlier, right, so there are 3 focus areas for us. One, it should work during the daytime as well. So if we do just nighttime, probably it's a challenge, because if there is rain, that's it, you will not be able to generate keys and all. So we are trying to have a system which actually works even during the day. We had a proof of concept demo some time back, and we have made it operational even during daytime. We are working on creating a very high precision PAT, the pointing and tracking system. We probably have an idea to do it, to bring it down to 100 microradians. But we are working on trying to see how do we get it 1 to 2 microradian, which is a challenge. So would definitely like to invite the academia and industry partners to see if they can, if they have the technology or they would like to work in this technology, we would be very happy and, to collaborate on that. And then we basically have done a very extensive study on the atmospheric conditions as to how do we compensate, what do we do and all of that. So we have, of course, the last 1 year we have done lots and lots of simulations and all, and we reasonably understand, okay, what will it take to compensate and take care of some of those things. So as we speak, I think we should be having a 2 kilometer horizontal free space QKD probably another few weeks time frame. And the next step we want to do actually is to go to a drone-based QKD system, because so in the past to going to the satellite, and then finally go to the satellite. So if I talk about the ultimate objective, right, this is what we are trying to look for, right? So we're trying to have a quantum secure space, air, and ground integrated quantum secure networks. So we already have the capability to do a complete terrestrial or ground-based quantum secure network. The next path we are going to take is actually a drone-based security. So basically we would be able to go to the air, so I can actually integrate ground and air, all resources, and create a complete quantum secure network. And then, and this probably we are planning to do it by end of this year. So probably end of this year, we should be able to create a very, very solid ground to air complete quantum secure network. And then hopefully by mid of next year, we'll also be able to do it on the satellite. So this basically completes the entire portfolio of creating a complete quantum secure network, and probably would help us help India become, let's say, create a complete quantum secure network worldwide, and our embassies or other infrastructure worldwide, even in India, can actually communicate in a secure way. So this is what we are looking for, and hoping that probably end of next year. Let's see. So this is an opportunity also now to start thinking a bit differently as well, because, for example, I think someone was saying that when lasers were not there, it was not known, but when laser came, we figured out, okay, now you can use it for multiple purposes. So now if you could think of scenarios, you can think of drones being able to communicate securely, you're able to think that, okay, it is a possibility that you can actually create securely, communicate securely from any point to any point of the world. So now we can actually start thinking on certain use cases which otherwise were very, very difficult and probably not possible. So I will leave it with this thought. I think the idea is that let's try to create a system. Thank you so much.
Thank you, Mr. Singh. I would now like to introduce Shri Vikram Sharma. He founded and leads the Australian headquartered Quintessence Labs, which is at the forefront of the global quantum cybersecurity industry. The company's capabilities have received a number of recognitions, most recently being named Global Innovator by the World Economic Forum. Mr. Sharma serves on several industry boards and is a member of the World Economic Forum Global Future Council on Cybersecurity, the Wall Street Journal CEO Council, and the Forbes Technology Council. Mr. Vikram Sharma.
Well, thank you very much for that warm welcome. It's always a delight to be back here in Delhi. And thank you for your fortitude to make it through to the last session, last address of this intense 2 days that we've had. And really, it's been quite remarkable, the kind of exchanges that we've had. And it's wonderful to see senior representation from defense and from government. Really gives you a lot of confidence. And the efforts of TSDSI, CDOT, and Tech in bringing us all together have been just incredible. Please join me in thanking them and congratulating them on a fantastic job. So I guess I don't know about you, but after this sort of rich conversation that we've had over the last couple of days, my head is certainly in a superposition of states. So I'm not sure whether this is how the talk will go, but it might be a bit random. So Well, with that, what I'd like to do in this session is maybe try and pull together. You've heard a lot, and I think there's probably little that I can add to the tremendous discussions that we've had over the last 2 days, but see if we can try and pull together a few threads about the various topics that you've heard about in the last 2 days, and try and provide you a 50,000-foot view. Basically, try and pull together three things. Well, what is quantum? I think we've heard quite a lot about it, but let's see if we can summarize that in some way, the cyber threat to it, and a little bit of maybe a short approach that you can take towards being quantum safe. So let me see if I can get this to work. There we go. Okay. So I don't think we'll go through this in great detail, but as you have learned, quantum is a rather broad technology. You can slice and dice it in many different ways. Here's one potential way, so putting sensing and metrology in one bucket, computing in another, and then comms in a third. So sensing and metrology, as we've heard before, revolutionary changes, particularly if you're looking for example, minerals discovery, to be able to detect deposits that are just not possible with today's technology. From a military perspective, being able to find tunnels, for example, underground, that are just not detectable today. The possibility, maybe somewhere out into the future, to be able to turn the oceans transparent. Now, what does this mean for naval strategy? So some dramatic changes coming out. Position, sensing, and timing. So when you're submerged for long periods of time, to be able to, in GPS-denied environments, to with great fidelity work out exactly where you are. That's not an easy problem, but one that quantum can help with. Computing, well, I won't belabor the point. You've heard so much about it. Problems which are intractable today, they just can't be solved, even with our best supercomputers, will be solvable by quantum computers. And as we've heard from colleagues, not all types of problems. Probably what's likely you'll see is, for want of a better term, quantum accelerators coupled with conventional computers, but giving you speed up, dramatic speed up for certain classes of problems. But of course, for all the benefits that these quantum computers will offer us, they will threaten our cybersecurity. And we've heard so much about that through the last couple of days. So I won't belabor it. But the good news is, and really echoing Bruno's comments, we can use quantum to fight quantum. So there are some fantastic approaches which we've heard about where quantum technologies can be used to defeat the quantum threat. Again, I think yesterday you would have seen from a couple of the speakers the scale of the investment that's going on last year. We had the opportunity to do some back-of-the-envelope calculations for a European agency. This was early last year. Please don't take these numbers as being precise, but I think they give you general trends. So at that time, about 30 billion euros had been committed worldwide to the quantum sector. That's growing day on day, probably 1 year out now. It might be 40 billion euros potentially. In fact, most recently, you may have seen last week, the UK in their latest budget announced 2.5 billion pounds of funding for their quantum sector. But an interesting couple of observations for this. One is that China has really selected this as being a sector they would very much like to lead the world in. And from our best estimates, about 40% of the global spend is coming out of China. The other interesting thing to point out is that private investment is starting to flow into the quantum sector. Largely, until maybe a couple of years ago, most of these initiatives were government funded. We're now starting to see private investment flow, I think because they start to see the commercial realities. Private investment is always driven by return on investment time frame. And now for some of the technologies, as you've heard from my colleagues, communications, sensing, perhaps in the return realization period of the venture capitalists. Again, I think that's probably the simplest way to say this. Quantum computers will break current encryption technologies very rapidly. So the small subline there is everything will need to be quantum resilient everywhere, borrowing from the recent movie that won a few Oscars. I think summarizing what some of the colleagues have talked about, so if we look at on the left-hand column here, is you see 4 different cryptographic functions. The primary tools that are used today is in the second column, and what is the quantum attack and its impact on those. So if we look at digital key exchange and digital signatures, so we primarily have RSA, Diffie-Hellman, elliptic curve, which are the basis of assuring security of those, and using Shor's algorithm, which actually, interestingly enough, is almost 30 years old now. 30 years old. So I think Bruno was making the point here, what about the unknowns? What about new algorithms that we may discover, or speed ups, as the Israelis have shown, on existing algorithms? But the impact of this was they'll be broken. So hence, we need to move soon. Data encryption, well, if we look at symmetric ciphers, I think as you've again heard from colleagues, generally the idea is if you extend the key length, we think we will be okay, we think. And then authentication. So there's a guy called Simon, and using his algorithms, you potentially can break some of the mechanisms we're using for authentication today. So what's the consequence? No comms link will be trusted to be secure. No communication could be trusted to be authentic. You don't know who's on the end of the line. I mean, our e-commerce today relies on the fact, or secure comms, that I know who's on the other end of the line. It's not an imposter. And for e-commerce particularly, it means that transactions could be repudiated. I just say, no, I didn't buy this. It would be terrible for stocks particularly. So just to give you a little concrete example, so we talked about Shor's a lot, but what does it actually mean? So here's a very simplified example of what asymmetric encryption looks like. So if I gave you two numbers, 165,181, and I said, please, can you multiply that with 417,953? Trust me, those are both prime numbers. You could easily, on your calculator, punch that out, and within 2 seconds, you'll say, well, Vikram, the result is 69,037,000,000, etc. Easy. And those of us who are good mathematicians probably could do it on a piece of paper in a matter of a few seconds. But if we want to, go the other way, and I gave you the 69 billion number, and I said, can you please tell me what are the two numbers I multiplied to get to this result, this product? That's a difficult problem. And that's the basis of asymmetric encryption. And as the numbers get bigger, the difficulty of reversing this multiplication scales very rapidly. Hence, this is just an example that, and is perhaps a year or two old. If we had a 1024-bit semi-prime, so basically a number derived from the product of two primes, it would take us thousands of years on our best supercomputers today to try and factorize that. With a quantum computer and Shor's, this would be done rapidly, in a matter of seconds or minutes. Therefore, public key exchange, asymmetric encryption, will no longer be safe. So Michele Mosca yesterday gave a very informative address to us, because we often get asked the question, all right, well, what is the time frame we should act within? And that's a very difficult problem to ask, given that quantum computers are still developing. There are technical challenges to be encountered, and it's not an engineering problem, it's a scientific problem. Therefore, you can't put precise timelines around it. But he has a very good heuristic to think about the problem. It consists of three very simple variables, x, y, and z. X is how long the encryption needs to be secure. Now, depending on the domain that you're operating in, the answer to that varies. It could be like a transactional data where it's seconds and you don't care. After the transaction's done, you don't worry about the security of that information anymore. However, if we look at intellectual property, drug design, for example, financial secrets, healthcare data, military designs, these are things which we want to be absolutely secure today, but we want them to continue to be secure 10, 20, even in some cases 25 years. Interestingly enough, we had an example that came out of, I can't remember, I think it's one of the European countries, where they said citizens' healthcare data must be protected for their lifetime. If you look at the children that are being born today, they're easily going to live to 100. What does that tell you? That data needs to be secure for 100 years. Why? Is how long it will take you to retool your existing cybersecurity infrastructure. Totally non-trivial problem. If you think about how long it took us to get the infrastructure for public key PKI installed, it was a decade or more. It's probably still going on, 20 years easily. So to roll out some of these systems, replace them with new technologies, easily 5 years for complex systems, if not more. And Z is your best guess of when a quantum computer would come out. And as Michele would say, if X plus Y is more than Z, that little bit where those secret keys are revealed, we've got a problem today, not in the future, today. So he gives a very good idea, and as I said, we can't put a precise number on Z. So here is a very good heat map that he's put out. This is the latest one. It just came out, I think about 3 months ago, December last year. And it gives a polling of people that have no vested interest in selling you quantum secure equipment. These are people who are developing quantum computers. And it's their estimate of how long, or the risk, till you have somebody who within 24 hours can break 2048-bit RSA encryption. Very precise question formulated here. And the way to look at it is, when does the risk level cross a threshold that you are comfortable with? Today in our businesses, in our military, in our government affairs, things which are more than a 1% risk of occurring, we go to extraordinary lengths to protect ourselves against those. So you need to make your assessment that where does in this timeline the risk tolerance cross a threshold that you are comfortable with for the organization that you work with. And that can help you get a guidance on Z. For many large organizations, governments, defense organizations that we're talking to today, it's somewhere between 7 and 10 years is where they think that Z might be. A little bit about our company. We were Australia's first quantum cybersecurity company, and after our friends at ID Quantique, one of the very first in the world. We've been going for about 14 years, arguably a little bit too early to the party. But today we have quite a mature set of products which are deployed globally. Some of the sectors, you can see banking and financial services. Somebody thought yesterday, I think, talked about if you love your data. So these are the sectors that love their data. Banking, financial services, government, defense, defense primes, critical infrastructure, cloud, Internet of Things. So those are the areas where we are focused on as a company today. There are 4 pillars we think that you need to adopt to have a quantum resilient posture. True random number generation, you've heard a lot about that. Enterprise scale key management. This is the critical piece that delivers you crypto agility. You need to support today's ciphers, all the ciphers which are so embedded in everything we do today. But you need the ability as early as possible and as smoothly as possible to transition to PQC as it becomes standardized. And that's the third column there is PQC. So keep a watching brief on that. NIST has announced the first 4 recommended algorithms, but we think this is going to be a rolling series of announcements. Over the next many years, you'll keep getting new announcements. So you need to have that agility to be able to adopt those new ciphers as they come out. At the moment, it's going to be a bit like Y2K. It's going to be really problematic. We have to look through all our code where it says, oh, I'm using AES. I need to change that out. But if you can do that in a crypto agile way, that pain of transition you can take once and be set for the future. And the final piece is, of course, quantum secure communications using QKD. We do it a little differently to colleagues that have been speaking. As opposed to using single photons, we use bright lasers in their entirety. And they have their pros and they have their cons, but happy to talk to any of you in detail about what we're doing in CV QKD, as it's known. This is a very quick picture of some of what these products look like. On the left-hand side, that's a very fast random number generator. It puts out 1 billion random numbers per second. It's about the size of a cell phone, measures an effect called quantum tunneling. So it's all in electronics. In the center is our flagship product. We call this the TSF. This really has the capability to manage encryption keys at enormous scales. As we go to 5G, 6G, IoT, massively sensorized environments, you are going to find you're not going to just manage a few thousand or maybe tens of thousands of keys. You are going to soon be managing millions, if not hundreds of millions of keys. This provides you the capability. It works in massively clusterized environments to give you enormous scale, redundancy, control. These are very hardened boxes, so very difficult to break into. And the final piece is our CV QKD. That's an old picture. It's down to a single 4RU unit now. So finally, in closing, perhaps just share with you an approach that we think if you want to consider moving to a quantum resilient posture, what can you do? So the first thing is what we find with a lot of organizations is they actually don't even know across the large organization what types of cryptographic systems are in use. So it's very important to discover those and then classify and make an inventory and say, okay, this is all the cryptographic systems I hold. The second is, what data do you hold? not known also by very many large organizations, and particularly not all data is valuable. Probably I could even hazard a guess saying majority, even in highly secure environments, doesn't need high-end, high-grade protection. But knowing what does need high-grade protection and identifying that and understanding the consequences of risk is absolutely critical. So once you've done that, out of that then you can work out which of those systems do you think are exposed to quantum risk and the consequences of compromise of that particular data. Because an important thing is, as much as you protect, you must make sure that you have a very good response strategy in the event that you are breached, which is a very real risk today for most organizations. And then I think, and this is delightful to hear what Indian government and what defense is doing, is engage in these pilot programs and trials. So very important. I think you see certain nation states have backed their programs very substantially, and it's an absolute pleasure to hear from all of you what India is doing in this regard. And then once you've done that, that gives you the ability to develop a transition roadmap. This is what you will be doing over the next 5 or 10 years so that your critical systems become quantum resilient, and particularly to adversaries who might have bad intentions, you're very well protected. And we just put out 3 or 4 steps there. So that's one approach that you hopefully would find useful as you think about how you might move to quantum resilient posture. So with that, I'm very excited, very delighted to have participated in this conference. Thank you for having me. And for India's quantum sector, I'm very excited to see its golden age now emerging. Thank you.
Thank you so much, Mr. Sharma. Well, we hope that the takeaways from this session will enrich you. We would like to thank all our distinguished panel for their contributions, for bringing to the table their experience and expertise. And I now request Shri Ritu Ranjan Mitterji, Senior DDG and Head TEC, to kindly present a memento to the Chair, Lieutenant General M. Unikrishnan Nair.
Thank you, panelists. Wonderful. Thank you. Thank you very much.
And now I would request Honorable Chair to present mementos on behalf of TEC to all the panelists. Dr. P. Sam Kumar. Dr. Dong Hee Sim.
Wonderful. I think we are looking at Thank you.
Shri Animesh Aryan. Shri Dilip Singh. And Shri Vikram Sharma.
You resume the audience.
Thank you once again, and ladies and gentlemen, we now break for a short tea break of 15 minutes. Do join us back for the last panel discussion. We'll have a group photograph here. All the panelists, I request you to kindly stand here for the group photograph. So there's a situation here, ladies and gentlemen. There's a lady, Vandana Bhatia, who has left her wallet in the Conclave bag. Now, all the Conclave bags look similar. So, in any case, if you have taken that bag by mistake, kindly go through your individual Conclave bags and see if there's any wallet inside. Vandana Bhatia, you'll find her cards also there, her PAN card is there, and you may give it to me if you find it. Thank you.
Back by 5:15.
Yeah, that's it.
So you know
A 15 minutes tea break. We'll be back by, okay, 5:15 we shall resume. our sessions, the concluding session at 5:15.
You don't have to, but I think नहीं उसका नहीं है, मेरा ही है अभी चेक किया है वो दोनों मेरा ही है दोनों मेरा
Nice start for you. Let's get the both topics. Nice start for you also.
Yeah, I mean,
Back after tea. Hope you all are rejuvenated enough to attend the concluding session today. It's going to be a panel discussion and an invigorating one as well. It's a pleasure to introduce the chair of this session, Major General Sanjeev Sharma. He is Sena Medal Additional Director General Tactical Communications of Indian Army. He was commissioned into Corps of Signals. He is an alumnus of the prestigious Defence Services Staff College and has held various command and staff appointments in key formations of Army in J&K, Northeast and along Western borders. He's been intensely engaged in technology scouting, development of solutions to suit military needs, and inducting state-of-the-art capabilities towards enabling reliable combat communications and electronic warfare systems for Army. General has also spearheaded the Defense Communication Network in unifying communications between Army, Navy, Air Force, which is critical to the national efforts of jointness in armed forces. In his present assignment, besides capability building in tactical and strategic networks and electronic warfare systems, he is pursuing adaptation of key futuristic technologies to military needs, including 4G LTE networks, 5G software-defined radios, E-band radios, Army's own satellite and quantum solutions. Secure Army Mobile is a key innovative indulgence through which the General is presently engineering a pan-India secure cellular communication network, which is an aim to achieve convergence of communications and data services. Welcome, General. Thank you. And moderating this session is Shri Abdul Qayyum, DDG, Telecommunication Engineering Center. Please join us on stage, sir. I would also like to introduce Ms. Shikha Srivastav, who is going to join the panel discussion. She is Director, Member Board, Center for Development of Telematics, C. She received her BTech in Electronics Engineering from IIT BHU, Varanasi, and Masters in Research degree from IIT Delhi. She's a gold medalist. She has hands-on and supervisory experience in communication system analysis, designs, development and support. Her area of work includes digital switching, UMTS, VoIP, chat protocol, law interception, internal navigation, text analytics, video analytics, big data analytics, mobile app development, artificial intelligence, and security. Welcome, ma'am. Also joining us this time is Dr. Dong-hee Sim from SK Telecom, South Korea. We just met him in the earlier session. And one for the last time, Dr. Bruno Huttner, ID, Quantique, Switzerland, and Sri Sunil Gupta, CEO of QNew Labs. I request the chair to kindly start the session.
The last 2 days, I think it has been really wonderful, and it has been enlightening for all of us that the work which is happening in the field of quantum communications and the way actually the Indian industry is progressing. It was even better for me to understand and know from the perspective, because I look at, as I brought out, that I was looking at technology and looking at scouting it for the Indian Army. And it also actually brings the belief to me that the quantum communication is actually fast moving away from the scientific curiosity to actually developing into an industrial product which can be actually used. Some clear applications emerging in the field of communication in the cryptography, while others I think will need some time to evolve. We're talking about optimization and other problems as the quantum computers come up, which is a little long way to go. But all in this, it was wonderful to be among a very learned panel who will be taking on the questions which have already been sent by the some of you, and during the course of discussion, the questions come up. I'll hand over to Mr. Kayum to start the discussions.
Thank you, sir. So, we all have sort of time. So, we have three panelists who have already spoken during the course of today's discussion. Only I will give 2-3 minutes to Madam Sikha to talk about what CDOT is doing. See, as an engineering center, it is having a lot of product, right? But from adoption perspective, what CDOT is doing to promote adoption of this technology. Thank you.
Thank you, Mr. Gayum. Distinguished panel members and my senior colleagues and ladies and gentlemen, CDOT has been working on the quantum technologies, on QKD, quantum key distribution, and PQC, post-quantum cryptography. And as you know, that with quantum technologies, the hashing key strength will be halved. The PKI will be compromised, and the symmetric key strength will also be halved. So therefore, all the computing, all the data that is being stored or is being communicated, that data is under threat. And therefore, we have come up with this post-quantum cryptography solution, which is also deployed currently. And there are 2-3 modes in which we have deployed it. One is that between two sites we can deploy it along with QKD, and we can also deploy it between a client and server, or we can deploy it between two clients. So this kind of solution is already there, and it is deployed, it's being used. And in the future, we are now working for increasing the capacity or scaling of the solution to handle more traffic.
Thank you, ma'am. Now, I will ask one question to Dr. Dong Hee Sim. So, perhaps SK Telecom is among few operators. I am not aware any other operator has used quantum in such a big way. So what has been the challenges when you started introducing quantum in your networks, and how long it took for you to reach a level when customer is satisfied? I am sure when you are introducing any new thing, there might be problem with the user experience itself. So what kind of challenges that you faced, and how you could dispel the apprehension of the customers? Thank you.
Thank you, Mr. KM. Is it correct pronunciation? KM. Okay, sorry. Thank you. So for us, the most difficult part in the past to deploy QKD for our customers was to how to convince them, actually. So it's like from my perspective, personally, it's like selling premium insurances to the customers. So it's not really visible. So if you have a QKD keys and so on, you don't see the value, right, with keys. So you don't see the real user experience with keys, because it's part of communication. You don't see, it's like app, it's like application. Instantly you experience that, you enjoy it. So it's like a part of the infrastructure. So it's very difficult to convince the customers there is value out there. So you need to educate them So what is the difference between the existing conventional solutions to this one? And then it takes time to talk to customers, to convince them there is threats, but it's hard to imagine if you are not familiar with this. So it's very difficult from the beginning to convince them first and to educate them slowly. So even ID Quantic had a winter school for that, and then we had our internal education program to talk to our customers. So if we try to talk to the banks and hospitals and factories, etc., it was very difficult to for us. It's not just about the technology, because technology also difficult part. But if you have a technology, it's how to convince them, use them. So for me, it's like more sales and marketing to educate them to sell like premium insurances. That was actually the most difficult part. And the second one is also the policy one. So it's as you notice that a lot of funding actually from government side, and also the maybe European Commission, Indian government, or the current government involved. Then it's like how to change the policy perspective, the conventional, the key players in the government side. So they also from the beginning were not familiar with this, and then it was also we also try to not lobby them, but try to educate them to change the policy to adopt these advanced technologies from security perspective. So it was also a difficult part. So that was the second. So the major two different difficult part was to convince customers whether there is value or not, and then also change the policy to adopt these advanced technologies for them and government, also for the customers. Thank you.
Thank you very much. Just a follow-up question. Has it helped you to increase your revenue? I think many investors will be, like to know.
Okay. I'm not going to lie to you, as I said. So it's, as I said, that's why we started to use QKD for our backbone first, to see the benefits for ourselves, to convince our management to also. A lot of stakeholders involved, as you can imagine. And then with that evidence, with our experiences, we try to talk to our customers and many vertical sectors and government, etc. At the moment, it's not really huge revenue at the moment. You're laughing. So as I said, I'm not going to lie to you.
No, it's an investment, you say.
Exactly. So you need to have a proper product first to really convince customers. So we are at this stage to try to make sales as much as possible, to try to convince as many vertical sectors possible. So at the moment, it's not there yet. So it's. I think the quantum technology, especially QKD, is niche. So we need to build an ecosystem. That's why personally, our company trying to talk to other operators like British Telecom, Deutsche Telekom, Telefonica, Orange, maybe I don't know, maybe Indian Telecom, maybe there is operators out there interested in this QKD and pick the other technologies. So that's why we are talking to the many operators, also participating many SDOs, standard development organizations, to talk to them and to build an ecosystem, and then to find out any gaps over there, or to try to find our customers. So it's not quite making money at the moment. So we really hope we get there soon. So that's the current situation.
If I may add, because we have the insight of 21 years now of quantum at ID Quantic, and I can tell you that the worries Donghi says were much worse when we started, because nobody knew about quantum, nobody was interested about quantum, nobody knew about the quantum threat. And I think, as Mr. Sharma just said, it was a little bit too early. And the company thrived because we were making random number generators and photon counters, and that somehow we helped. So initially it's an investment, that's what you normally say, and then the investment goes on and on and on for several years. And exactly as Donghi said, I think what's really interesting nowadays is that you have many telecoms who are really interested in implementing QKD. And we see Telefonica in Spain, who is very active. Deutsche Telekom is also active and is building a network around between Berlin and Bonn. I think, there's a lot of activity. British Telecom is actually building a network around London for customers. So they're really basically making a network and trying to sell the QKD keys to their customers. It's early, so I'm not sure how much money they make, but that's very new as well. Even Orange in France is now moving in and working with us and with others. Actually, I think that's quite fair enough. So you see a very large difference between several years ago and today. Making money maybe is still, is still an investment maybe.
Thank you very much. So now I will come back to the panelists. Now the audience can raise their hands and ask few questions. We'll have few questions from the audience and then I will come back to the panelists. Please.
Hello. So I am Shomo from Tata Consultancy Services. So from the few talks we are listening that quantum computer will come, but when we will know that quantum computer has actually come? See, when quantum computer will come, so they will publicly announce that we have a quantum computer and we can break 2048 RSA, or they will start breaking the 2048 RSA or stealing some of our monies. So when that will happen? And my second question is, so like UK and China has already developed, India will be already developed to build this QKD. But the third world country like Africa, they have not done anything. So what will happen to them? So if quantum computer will come, so hacker will hack all the money from the Africa. So what will happen to the third world country? Right.
So I'll request Mr. Sunil Gupta to answer if he can.
Okay. So I will give you the answer I normally give. It is sooner than what we expect this quantum computers will be there. Unfortunately, quantum computers will not come announced, right? It is believed that some of the countries already have significant compute power available to them with which they can today break even the current encryption. They may not disclose it, like when the Britishers broke Enigma in the World War II, they did not let Germans know for a long time because in counter intelligence or espionage, not disclosing that you have that capability is an advantage, right, to you. So I think the question is not if about when, right? Question is about if, right? So the question is what we need to be prepared for, right? Is that if it happens, how secure is our critical data? Now, it is also a function of your economy and your growth, right? Developed countries have where the GDP is more digitized, right? There the digital data, right, is all about, we're talking about digital economy, right? Digital economy will be more impacted. Africa is not yet digitized, barring a couple of countries, right? India digital GDP is growing exponentially. That's the reason the risk for India is significantly higher, right? So I think important is that we need to be prepared because as per some of the research, 2015 was the year. After that, we are in red, which means that now any data which is not quantum encrypted is under risk of harvesting and decrypting later because data would be relevant for 15 to 20 years or 25 years, right? So that is the problem that we need to worry about, right? Yeah.
Thank you very much. So, question.
Dr. Dong, that I think in presentation you have shown that Samsung Galaxy phone has used the QRNG. So what is the advantage they are getting it? And they have anything publicized or marketed as a marketing tool that they are using a QRNG and that their phones?
So I guess that was heavily marketized in South Korea at least. I think that particular three models, the spanning 3 years actually only were sold in South Korean market at the moment, I guess, if I understood correctly. So then it was used to generate random numbers, as you know it. So it's like a provide randomness inside of smartphone too. So it was heavily productized in South Korea, but I don't know why it was not really exported to other countries maybe, but it was Samsung's policy. But it was a kind of pilot project to put QRNG into the smartphone to demonstrate the capability of quantum technologies. As I said before, we already used the quantum random number generator in our authentication server in the network side to authenticate users. So we thought, why not it using the smartphone side and the mobile side to use quantum technology as much as possible. Because for us, it doesn't make sense. If you have already technology, it doesn't make sense not to use it. So as I said, we already deployed the QKD, we already used the QRNG, and then we thought it's useful to put the QRNG also to provide quantum level randomness to mobile, to use quantum technology as much as possible to provide at that level of security. So that was the idea. So.
Thank you.
So,
more secure communication. You buy a phone because it has quantum randomness. Somebody will buy a phone because the application using this randomness is more secure. And in Korea, what's happening is that Samsung and SK Telecom work together to develop some applications, for example, banking application, where they told their customers that if you are using the random number generator, the QRNG, to connect to this application, you will have a more secure environment. Now, how secure, that's a very interesting issue. You know, with security, it's always the same. You always spend too much on security before you are hacked, and you have never spent enough after you are hacked. So when you buy a phone, quantum phone in Korea, and you connect to your bank and you're happy that you haven't been hacked, you're happy. Now, how many people are hacked and wouldn't have been hacked if they... It's not something we know for the moment. So I think it's a little bit of chicken and egg problem. People will take the quantum phone when they have enough applications, but you need to develop application for the phone. But of course, if you want to develop, you need to do that before you have the application. So it's a little bit hard to start. They started in Korea. They are now at the 3rd generation of phones. They have sold several millions of them. So let's say it's getting there. We are working hard to sell the same kind of technology to other manufacturers, clearly, and it takes a lot of time. I would say we're quite optimistic, but it does take a lot of time. And their problem is also how to market. How do you market security? It's not so easy.
Thank you.
No, I think you already talked about it. Then normally what happens is that every device that you have, it has an entropy generated through the operating system. A lot of time the entropy is not sufficient, as Dr. Bruno was saying, right? So the quantum random number or chip on the mobile phone means that you're never starved of the entropy. And entropy is the basic root of trust. All the keys that you generate is generated through random number generator. So idea here is that with the QRNG on a mobile phone, you are having the best in class high entropy, right? And high randomness, right? A high entropy and high throughput that you have in order to make sure that numerous applications never starve of the random numbers. That's the whole objective.
Thank you very much. Okay, on this side.
First of all, thanks to TC and the organizers and the speakers for excellent knowledge they shared. One thought that comes to mind is regarding waste management. We are all concerned about the Mother Earth these days, sustainability and recyclability and circular economy. Now, e-waste has become a problem because perhaps, I don't know whether while developing so much of electronics, we never thought by design. Now, will there be similar problem of Q-waste also? I don't know whether it's a right question or long-term question. Will that lead to circular issues or linear issues of economy? I don't know. Probably the experts may like to share their view.
Who would like to answer?
Yeah, I think it's a tricky question. In terms of quantum computation, maybe I can get out like that. Quantum computation, what is nice, it's the computation itself is reversible, so you don't generate entropy in itself, and therefore maybe you don't generate so much heat. And actually, the quantum computer can run without generating heat until you measure it. So maybe that's better than a high-power computer which generates a lot of heat, which has to be cooled. But on the other hand, you need to cool the computer to minus, to almost zero. So maybe this answer is, you need to cool it, but then you don't heat it too much. But so that's probably not so good. Now, in terms of electronics and so on, I think we're wasting a lot of resources on many, many things. That could be one of them. I don't see this as a problem in the short run, because we won't have many of these. I think it's a problem for the future. We need to think about that, but there is nothing special about quantum which will make it more wasteful than anything else. I think maybe on the opposite, actually, because you can work maybe with smaller and smaller things. You don't need this very large thing. So I would say maybe getting to smaller and smaller is probably better for the planet, assuming we don't throw the chips away afterwards, which are written by somebody who. So we need to be careful, but still, the idea to get to smaller and smaller size is probably a good one in any case. I mean, that would be my answer.
Thank you very much. Actually, I'll just add what others said, that like many other items which has gone into communication system, in due course, this quantum itself will go inside the communication. It will not be something what we are talking, that an identity, a separate particles or separate system. This will go inside the devices itself. So the discussion of having separate quantum and separate electron itself will cease. So whatever e-waste we see, it will be the similar kind of things. Thank you very much.
Yeah, so I'm worried about a future dilemma which we may face. As we know that law enforcement agencies are many times compelled to intercept calls and data of citizens, and this quantum era will lead us to a possible quantum encryption by the users. So how these two situations will go hand in hand in future?
Thank you. Who would like to answer? Yeah, please.
I think quantum era will be a boon for the LEAs, because they will get to hear many of the data and see and hear the conversations of all the encrypted in communication which is happening right now. Because if you see with the onset of HTTPS and even encrypted communication over audio communication, so all that information which is being intercepted right now is not very easily decryptable. But with the advent of quantum computers, at least they will be the beneficiaries of this and they will benefit from it. In the beginning, of course, till the quantum encryption itself is being used widely. I mean, the way it depends on how soon it, as he's saying, that people are not readily adopting it. So the adoption rate will actually determine that. But that there will be one period where everything will be exposed. Even see, there are three parts of the security: authentication, and this confidentiality, and reliability. So integrity. So even what information is being sent to me, whether it is correct, that will also be doubtful, and the person who has sent it, that will also be doubtful. So that era will be a very, very difficult era, especially in the area of communications. So probably all the defense and other security organizations, government organizations, they will be having their own networks probably at that time to ensure this.
Thank you very much. Would you like to add, sir?
Yeah. You see, the security also depends on the applications. If somebody is bringing out today, it's the hardware plus the applications. If you see the interception, the way it takes place today, it is not purely dependent on the way the application is encrypting things. So I'll just leave it at that. there are other means to handle the encryption, to the interception part, and that will continue. It's not going to change actually.
Thank you, sir.
One supplementary question on this. I think I am audible. We are saying that on quantum security, whenever we intrude the system, it will stop working. Security will be break and it will be classical one. So how we will intercept this? Security agencies, how they will intercept this?
So
yeah, you can take one, please.
I can. I mean, actually, I could answer that also with a question: why would the bad guys want to use quantum encryption? The problem is that in order to use QKD, you need to authenticate yourself first. So, and you need also to have linked with an optical fiber and so on and so forth. So, I think it could be actually easier for people to track the bad guys if they are using quantum encryption. If I was a bad guy, I would probably rely on something else, which is totally independent of the network. For example, I would exchange keys with another bad guy, and then we can communicate securely even today. I mean, if I give you a 256-bit key and we share it together, then we can use it and it's totally unbreakable. Okay? So why do we need if we want to use QKD to do the same thing, okay, we need to go through the network, we need to authenticate ourselves to the network, we need to connect to the network in a very specific place. I mean, the bad guy could do it without QKD, basically, and QKD will not change that too much.
No, I'm saying that bad guy is not encrypting. Your transmission system itself is encrypted. In normal case, if you want to intercept in your transmission system, what we are doing today, so how it is possible for TSP's network to intercept on the TSP's network? In this case, suppose we are having quantum network. Across the network, it is quantum implemented in that scenario.
Maybe I didn't understand well. What I was saying is that basically, if today we share a secret key together and we encrypt with it, then nobody can decrypt it. Not the best possible law enforcement agency. So we have a way to use symmetric keys today, and it's very simple. Because if we want to communicate between two people who know each other. So I don't think that QKD will change that much this fact. But maybe I didn't really understand the question.
Okay, I would like to add. Basically, I think you're talking about tapping the QKD link. So I think now we are not doing any tapping. Even in this current interception system, that was an old system where we used to tap, means from the wire tapping used to be there. But even in the current interception system, that is not the case.
I am very much aware about that. I am just saying that even photon can implement
that's what
your quantum system. So if you are tracking anything from the existing tunnel, that is going to disturb it. No?
So that's what we are not taking from the tunnel, we are taking from the end. So, that is the difference. Like you are saying that we will take from the tunnel.
Okay, I will just add. Actually, whatever we are talking about, it is the transmission systems. It is not on the switching center itself. So whatever tapping is happening, that is at the switching center, not in the transmission. So here the security is being provided between two nodes, and there is no switching in between. It is just transmission from one end to another end, and there is no tapping even today in that. So any other question?
Yeah, I have.
Yes.
I am Arun Agrawal, DDG in Telecom Engineering Center. Now we are talking about quantum communication, where there is a lot of emphasis on secure communication. So do we foresee that in the future the quantum communication will be used in a big way, just like normal optical communication as we are using today, or whether it will be primarily used only for secured communication for defense purpose or for other purposes only? Thank you.
So who would like to take this question?
I can answer. See, even now, even today, even the OTT apps which you're using are secured. So everyone wants security. No one wants that I should be using insecure communication for whatever reasons. I think that would be a normal choice, and therefore quantum networks and quantum computing will be a part of the natural evolution of our computing system and our communication system, and slowly it will evolve, and maybe it will take over. See, even there's nothing static. Even our computing right now has gone an evolution. It has increased in power, in efficiency, etc. Now we have GPUs which are giving much better performance. And now with quantum, this artificial intelligence will be faster. And the error rates of artificial intelligence results are much lower with quantum computers, as has been seen. So therefore, this will be a natural evolution, and people will use it, I think, in future.
I'll just add a little bit. You see, what happens, how secure is secure. Today, your financial systems, for example, if they come under threat, you'll have no option to change over. You see, the point is that what kind of security you are asking. We were just talking about that somebody asked that how fast the quantum computers are going to come. And the answer was perhaps they have come. So today we see that the classical algorithms have already been broken. All banking systems will have no choice to change over. So because you see the way the economy today, in fact within India, the way the digital economy is building up, the options will be very limited not to change over. So that is one example, and similar examples will follow, as the ma'am said, that it will be natural evolution coming up from there.
So one question.
So I think
one last question.
His question was that whether the classical communication is going to be replaced by quantum communication. No. Actually, what we are talking about, that only the key that is used in the encryption, whatever, if you say quantum network or quantum internet, that means the keys are on a network, not the data. Data will still keep on going on the classical channels. It is just, add on to the classical network. Thank you.
If I may add one thing, I totally agree with what you said. I think it's very important that the network, quantum network, which transmits keys today, because we have QKD. In the future, we have quantum repeaters. It may transmit quantum states, and that's what we call the quantum internet. But again, these states will not be used for data transfer. The classical part will always be used for data transfer. The quantum states will be used to connect quantum computers to do some very, very specific things with very low rate. I mean, we are not going to have terabits per second of data of of qubits. That's totally realistic. We will have a few qubits with high value, which we can use to connect quantum computers maybe. Today we have relatively short keys, which we can use for encryption. And again, it's exactly really no data. Don't think that the quantum system will replace the data. It's very important to remember the two will work together, each one for each particular application. Today keys, tomorrow quantum states for the quantum network.
Thank you.
Yeah.
Thank you. Yeah. You have a question? Yeah, please.
Let him ask first.
Sir, I'm this side Murali Krishna, DDGRTC. Sir, from the yesterday and today, at least my understanding is that we have been deliberating this quantum communication is based on the perceived threat from the China, and all countries world over is pumping billions of dollars towards this. My question is, okay, quantum communication may lead to, whether it leads to secondary benefits other than the security. That is point number one. Point number two is that, is there any other method of handling to counter the security threat from the China or any other, any other method of countering the security threat of hacking or disturbing the RSA 2048 bits security keys?
Yeah, I'll just answer this. So you would have seen that the two things have already been talked about. It's not about against China, it is about threat against quantum computer, right? Now the quantum computer, as we know, that it threatens to break the asymmetric keys, right? PKI. So there, earlier when that ID Quantic started, it was largely QKD, right? That was the only way using quantum physics to break the quantum physics problem, right? But later on, as you saw, that mathematics have come in, right? Advanced mathematics, lattice code. So that's the second way of solving the problem. Tomorrow, some other new algorithms might come up, which will become quantum resistant. The idea is that how do we use algorithms, right, or a mechanism to generate keys that are quantum resistant or quantum safe. That's the whole game, right? Because quantum computer threaten to break that encryption key, right? So we already seen in the last decade, so at least 2 or 3 methods, right? And today people are talking about using hybrid, right? Both QKD and PQC, or classical keys and PQC keys together. So hopefully in the near future, there are new algorithms might emerge, right? So that's the way it's going to happen.
Thank you. So your second row.
My question is to CROD, Mrs. Shikha. So this is primarily with respect to the fact that CROD has now been entrusted the responsibility of spearheading the National Quantum Mission in the form of taking ahead the quantum alliance of the country. So what are our plans? What all is coming on in your bucket list? What do you aim to achieve, especially in the context of the fact that the stakeholders have varying commercial as well as the development interests, the IPRs, all those issues are there. And CROD itself is in the development domain of the products that you listed that you are developing. And the second associated part is that when we are looking at security, talking about the cryptographic applications of quantum, we are looking at the entire sea change to the current traditional cryptographic policies and framework under which the evaluation and the implementation of the products is happening. So how do you achieve the plan to achieve a change in these policies, and in what time frame do you expect that these changes can come in the country?
I think CDOT has got a very huge responsibility of this heading the mission of quantum technologies in the country. And but today, in this 2-day conclave, we have seen that there are so many experts in the country, and definitely we would like to work with all of them. And we will work with academia and industry, and in a collaborative mode. And we need to work out some basic building blocks which should, and by the time frame by which those building blocks should be ready, and so that our country's security and the security of the critical infrastructure is not compromised. So that we can decide along with the security agencies, and then together in the consortium we can see the expertise of the different institutes, and together with them we can assign those building blocks to different institutes and then stitch them together. That is one way which we would like to work. Of course, innovation in this field is very much required, so we would encourage these agencies to continue their research work, which will definitely help us to move forward in this area. And regarding the policies, and also I would like to add that we can also have an advisory board of experts for leading this consortium, which will guide us in the right direction, in the right technology direction. And also from the security point of view, there will be some testers also to see whether the products which are being developed are secure or not, are meeting the security standards or not. So then we also need to have this development of those test bodies, the people who will actually test these new products. So development, research and testing in a collaborative way, that would be the path which we would definitely like to take. And regarding the policies, I think that will take a little time, because this is being picked up as we see worldwide in the globally. If we see, even other countries have now come up and have made use of PQC as compulsory, especially for secure and government organizations. So even now in India also, probably we need to see at which point we have to do that. Are we ready for it? So it may take say 6 months to a year, when we can say that yes, we are ready. Probably in 6 months or a year in time we can start these policies changes, but they will evolve.
Thank you very much. Yeah,
Yeah, myself Sushil Kumar, DDG IoT in TEC. So from the transmission network, let us come to the Internet of Things domain. As we know, the IoT devices are being used in the critical infrastructure, and that is we are speaking about the transmission network that can be secured by using QKD. And my question is, Microsoft published a report in November 2022 that a large amount of malware infection is being generated by the IoT devices, and on the top is the China, then US, and then the India. And India is at the third position in generating malware infection, and almost all the IoT devices, whether it is the smartphone gateways or the Wi-Fi hotspots or smart cameras and so many, they say that all are vulnerable. Whether after using the QKD techniques for the IoT devices, I think, which will be developed in near future after like NIST and other algorithms, other organizations are working on this, whether the vulnerabilities can be reduced or it can be, this network will not be vulnerable at all.
Yeah, we'll take this question.
First of all, let me correct one thing. IoT devices cannot be connected through QKD today because they are too small and they are not connecting through fibers. Maybe what you meant is a QRNG. And that's what can be done. Basically, you can improve the... First of all, you need to encrypt the devices. And that's actually the first step, which is not really done today. Many of the devices you mentioned are simply put on the web without any kind of security, which then opens them totally to malware. So the first thing is to stop that. And that's totally classical means. I mean, there is no quantum threat or whatever. You can really do it classically if you just want to. And the worry is that you don't do it today. Second step is, if you want to secure the devices better, then the best is to use better keys when they connect to the internet. And therefore, you can use, for example, a random number generator to make sure that every entropy used by the device is a good one. And that's actually a very important point. If you have a device which is on its own, let's say a camera, you cannot get randomness from anywhere. You should only get it from inside the device, and that's where the quantum is good, because a quantum effect can be really directly in the device and give the randomness. But again, it's important, but it's only a second step. The first step is just encrypt every kind of IoT device you put on the internet by any means you want, and that would probably reduce this problem a lot.
I think you are speaking about the secure onboarding of the devices, and I think that is already being done across various smart city platforms.
It's
and
changing,
IoT
you're
platforms.
right, yeah.
Using the X.509 this certificate in the PKI infrastructure. That is already being done. But the malware infection is being generated a lot even then. So it means the basic guidelines which are available from the various standardization bodies like ITSI or the World Economic Forum, those are required to be used for securing the IoT devices, and I think QKD will not be able to secure the IoT devices.
Thank you very much, sir.
Sir, I will answer.
No. Any other question? Yeah.
Sir, can I ask?
Good evening, sir. I am Sri Krishna, DDG NCCS Bangalore. One of the speakers have told that the quantum computer supremacy could be established with 50 qubit system when compared to classical computer. And QKD systems have been deployed now in various telecom networks. Whether any study has been done to compare it with the existing key exchange algorithms which are already available, how supreme or how secure they are compared to existing key exchange algorithms? Any study has been done or any information is available on that?
I think the best part of this QKD is, as the gentleman over there has said, that if anyone is listening to the conversation, that can be detected very easily as compared to the classical. So that is why it has been, and these systems have been tested, the keys transmitted between two sites, and they are being used also. I mean, in the routers for encrypting the traffic. So it has been tested in that way. I mean, our product as such has been tested.
So I'll just
Thank you, ma'am.
I'll just add to that. Sorry. So there are two different concepts, right? Quantum supremacy is a term used when then quantum computers can solve a problem that can't be solved by classical computers, right? So that is different, and 52 qubit can only solve one particular problem, right? It's not that it can solve all the classical problems. While to break encryption, right? Encryption key RSA or elliptical curve cryptography, you need at least few thousand qubits of quantum computer, right? So that probably is not going to be available for another 2 years, right? We will know. I think the important is not that. If you see, earlier it was said that you probably need a few 100,000 or a million qubits to computer to break the RSA 2048. But recently Chinese scared everybody when their scientists came back and said 373 qubit of quantum computer will be able to use their algorithm to break the RSA 2048, right? So effort is on that how do we build a more efficient quantum algorithm who can run on today's available quantum computer, not a future universal scalable quantum computers. That's where the threat is, right? Imagine if that is true, 373 qubits, and IBM will actually launch a 400 qubits, odd qubits of quantum computer by end of this year, right? Or maybe middle of this year. That is the risk case, right? So people are continuously devising a smarter algorithm that can run faster on the existing quantum computers, right? While supremacy is a different concept.
Thank you very much. Okay, Raju, do you have a question?
Sir, I'm Venkat Ramaraju Chelle, Director Quantum Technology. If you NIST has taken 4 phases of quantum algorithms. Look at each phase. Some are being eliminated. Some are being eliminated because of they are found they can breakable, like a cycle, rainbow. Just example. Similarly, we don't know how much sure they are secured against the not breakable. Somebody assume that they know that how to break the key algorithms. They will not disclose outside. So does it depend on NIST exclusively? Does it a right way, or shall we make a best efforts to further do ourselves? And then next,
that's a very interesting. That's a very interesting point. Really, NIST said that the best way to test if the algorithm is broken or not is to put it in the open. Obviously, if today I know how to break lattice-based system, I will not tell you. I will just do it. You know. But it seems that the cryptographers are a kind of special bunch, but they are really, mostly honest. And what they really want is to try and break the system and be known that they did it. You could see the Belgian guy, I don't remember the name right now, I should actually, because he managed to break a psych, and he did not hide it, he actually put it in the open. Now, what these people say, which is also interesting, is that if one of them manage to do something, another one will find soon out also. Which means that, okay, if you break something, you keep it for yourself. In a few years, not so long, somebody will do the same, and then all your effort will be in vain because you won't even be recognized. But again, the only possible solution is, like NIST said, to be in the open and to try and convince people that the best solution is to actually publish what you're doing. And we had a nice example of that with the Israeli, actually it was Secret Service or something like that, and they didn't even want to say who did that. The only, what we knew is that it was from Israeli Defense Unit called Matzov, no name, we don't know, but somehow they said, we found an attack against Kyber, we believe it is our responsibility to let you know. That was it, okay? So maybe somebody else will find another attack against Kyber, but I encourage every single cryptographer to do it, and that's what NIST is trying to do. It has to be in the open. If you hide something, then it will be much harder to trust it somehow.
Thank you very much. Any other question? Yeah, please.
Good evening, I am Dhruv Shaw from LP Jalandhar. So my question is specifically for Bruno sir. So Sir, you said that quantum with the quantum computer you can get the true randomness. So like there is a superposition of state, and if you want to like take the value out of that superposition of state, you get a random number. So does that randomness actually speed up the computing power, like from that randomness to get something deterministic, we need a pseudo random generator which is actually less secure. So please comment on this.
Okay, so in order to get, first of all, it's not quantum computer. I mean, there have been talks about quantum computer giving randomness. I think, of course they can, but it's probably a sledgehammer to break an egg. So you can generate randomness with a single quantum. What I was saying is that you take a qubit in the superposition of 0 and 1. When you measure it, you have a random result. Now, you may not have enough randomness if you use that, and therefore sometimes you need to expand the randomness, or you need also actually to make sure that you have perfect randomness, which you don't get from a physical system. For example, if I put my system in a superposition of 0 and 1, it will not be 50-50, it will be 51-49. So somehow you generate the entropy, which is not perfect, you run it through a classical processor, which will then give you perfect random numbers. And that's why you need to have these two steps. And it's not me telling that. I mean, yeah, I'm telling you that, but it's from NIST. It's not from me. It's really two different things. Source of entropy, which has to be random but not perfect, and then you process it to make it as perfect as possible through a classical processor. No quantum computer in all of this anyway.
And then just to add to that, that's the reason getting a high throughput and high entropy quantum random is a holy grail, right? It's not very difficult because you can get a low entropy, you get a high randomness, low throughput and high randomness. But if you want a high entropy for most of the application, high throughput, then you have to do DRBG and other stuff, right? And that's the reason real quantum QRNG is rare.
Thank you very much, sir. We will have only 2 questions from the audience. Yeah.
Good evening, everyone. Myself, Manish. I am from CDOT. So right now, what we have discussed is the securing the transmission channel. So my question is, since most of the world has been working on the application layer, so would there be any threat to the application layer by coming of the quantum computers? And if, in one of the presentations, we heard that HTTPS and IPsec would be undermined by coming of a quantum computer. So would that be the case? And if so, then is there any work in actually someone doing work right now to actually securing it? Thank you.
Yeah, actually, a lot of work is already happening. India has already the solutions to we call it quantum secure VPNs. So basically what you do is that, again, IPsec, when you do, the algorithm that you're using are classical. So what happens during handshaking, you have an option to choose the quantum algorithms, right? So today, post-quantum crypto algorithms are used to create the IPsec or the other TLS which is using based on the post-quantum cryptography, right? And that's the reason it is secure in future. So that work is already available.
Thank you very much. There is a quantum product for each layer. So,
if I can add that, I mean, for the IPsec, I guess as a pre-shared secret, even QKD keys can be used as pre-shared secret too. So it's the IETF that's working on it, and I guess the RFC is already available. So I guess we have a solution for that already. Thank you.
I think OpenSSL APIs have not yet included these PQC algorithms. So that work is still pending. So it will come in, I think, next 6 months to 1 year. So the applications part.
A question from this.
Sir, I am Captain Yuvraj from Naval Headquarters. My question is regarding applications other than communication. So the last speaker brought out that by using quantum technology, the effectiveness of various sensors will improve. So if the effectiveness of sensors will improve, it will result in the better effectiveness of weapons also. So any predictions on that? which somebody else in the world is already working on it. Specifically with regard to magnetic sensors, EOIR and radar.
I mean, quantum weapons. No, I think you're right. The one thing we can get is improved sensors, and sensors may be part of a weapon system. I don't see quantum today being used in the weapon itself, but more to help the weapon. For example, that was given by Mr. Sharma just a few moments ago when he said that with a quantum sensor you find a tunnel. So if you can, from above, from a plane or something, find out that there is a tunnel, then you can use it and destroy it or something. So you can enhance your weapons with the quantum sensors. I have not heard of any weapon directly using quantum to do something. I mean, that's something.
I just want to add to the officer's thing. Yes, it does improve because lightweight, low light scenarios, it's been seen that the imaging, the sensors, it is really going to improve. So more optic you get, it's like a telescopic effect you get out of the night vision goggles or night vision weapons you have. So it is certainly going to do that. So even today, lasers are being used for night vision thing. So when you have same optics, so we are going to use that for quantum is being used there. So in a previous conference, somebody was telling about the sensors. Quantum sensors here might corroborate, but it's true that it is going to improve that.
And quantum radars are there anyway. Quantum radars have the capability.
Yes, my question to that is, any predictions on that? How many years down the line?
It is already there.
Because the last speaker said something about transparent oceans. If somebody talks about transparent oceans, it means submarines are totally vulnerable.
So work is going on where probably in another year or so, right? We would have in India a sensors to detect underground any movement around in the undersea cables, and also detection of tunnels. And radar work is also going on where you can use quantum physics phenomena to detect the stealth aircraft and submarines.
So we can safely assume in a few years. 2 years.
It's there.
So thank you very much.
Just when you have a startup, 2 years is what you tell your investors, because otherwise they won't invest. When you have a company or when you're building a quantum computer, you say 10 years because then you have time to do whatever you need to do. So it's either 2 years or 10 years.
So I just wanted to state one thing regarding somebody here talked about the IoT. So in the context of cryptographic standards, NIST has recently, announced a call for algorithms for test vector code for lightweight cryptography. So there is a whole slew of things going on there. There are a lot of candidates. It's going to go through another 5-6 year cycle. So specifically targeting the lightweight cryptography parts. So I think anybody who is looking at it, so PQC is one thing. We are going to look at the implementation constraints and all that lightweightness of the existing thing. So PQC is pretty much towards replacing or advancing the existing cryptographic infrastructure, but for the devices and all that spread out across the world. So they are looking at standards because very important that sensors and the lightweight IoT device have to be compatible, because we can try to all the important servers and clients we can do heavyweight cryptography, but updating the millions of IoT devices is going to be a problem. That's where interoperability comes into play. So this need has been recognized. So both NIST and ATSI are working on it. So there is a call there. If anybody has algorithms, they can submit too.
Thank you very much. And that was the last question. Now I request Chair to.
Yes, one last question. Yeah.
Take on.
This. Yeah.
Yes.
Please.
So my question is open for all the panelists. So given the different types of QKD protocols, which one do you think has the highest potential for mass implementation?
Mass implementation.
Yeah.
I think
you're saying
I
mass
think
implementation.
I think PQC he mentioned, he referred maybe PQC.
No, I'm talking about QKD protocols. So we have a number of different QKD protocols. Which one do you think has the highest potential for mass implementation? Because that's what we are looking for, right?
Okay. Yeah, I think we can answer together. No?
Yes.
I mean, each protocol has advantages or inconvenience, but the one which is typically going to be standardized and that will probably be used everywhere is BB84 with decoy. That's probably the first one that at least we are working on that. Etsy is working on that, and everybody I know is working on trying to put that. There will be others later, but this one is probably the first one and the mass one.
Yeah, I was going to say the same thing. Yeah. Bureau QCI is also adopting that, right?
Yeah.
So,
if I can,
BB84 the decoy. Yes.
Thank you very much, Madam Sikha. Would you like to? Yeah. So thank you very much. Now I request Chair to allow closer on this.
Yeah, it's I think the most interesting session. Very, very interesting questions, and with the interest of audience, it is very evident that the quantum is heading into the right direction in India, and equally interesting answers. I thank my fellow panelists for such wonderful and taking interest and answering each and every query with a lot of enthusiasm. And I think it also actually comes on me to thank the organizers for organizing such a wonderful event where the entire academy and the industry, the international fora has been brought together at one forum, and it is the right step into stepping into the quantum era for the country. Thank you very much.
Thank you so much. Well, as Dr. Bruno put yesterday, that quantum communication era is at the door. Well, sooner or later, it's going to enter the door and be part of our lives. It is inevitable. The future of quantum communication looks very promising, as it has potential to revolutionize the way we communicate and secure data. However, there are many challenges. The perspicuous presentations, the engaging deliberations and stimulating sessions, the brainstorming provided food for thought, and the takeaways will definitely enrich everyone. That was the last session of the first International Quantum Communication Conclave. 2 दिनों में जो मंथन हुआ है, जो चिंतन हुआ है, आशा करते हैं आप सभी का ज्ञानवर्धन करेगा. और आगे बढ़ने से पहले we have closing remarks also. We'd like to present mementos to our few of our members, as some of them have already got it. So I request Shri Arun Agrawal, DDG TEC, to present a memento to Honorable Chair Major General Sanjeev Sharma. And now I request Honorable Chair to present memento to Shikha Srivastav, Director, Member Board, CDOT. And now one memento for Shri Sunil Gupta, CEO of Q New Labs. Let's have a group photograph with all of you standing. And may I request Dr. Manjunath Iyer from Wipro to present his closing remarks.
Friends, hope you can hear me. Yeah, thank you. So this is the last session in the entire conclave. So bear with me for 5 minutes. I won't take more than 5 minutes, of course. Yeah, we had a lot of technical talks, very well defined and structured talks. The entire conclave was held in a beautiful way. So our enthusiasms and knowledge got boosted up multifolds. So it was a great opportunity for all of us to get interact among them. So a couple of observations which I may take a few minutes, 1 or 2 minutes to tell and conclude. So one thing is, the important aspects that hindering us in the technical sense to go forward is the temperature, as I was telling yesterday. The other thing is the channel modeling. In the morning, many people touched upon this in the context of satellite communication, where it is very difficult to model the channel, open space channel, and also to locate the satellites. Maybe in the future, when quantum teleportation becomes a norm, or when that becomes, it catches up, then it will not be very difficult to transport the whatever the information we have, or replicate the information from one place to the other place. That may provide an alternative technology for all these issues, channel issues and all, where we don't have to deal with the channels. So it's a long, very long way to go. Until that, we have to bear with the QKDs only and to keep modeling the channels. That is one thing. Secondly, we thought that we have got immunity to Shor's algorithm. Maybe Shor may be laughing and working on the version 2. Right? So that is very important, because if not Shor, I may be working on that, or some of you may be working on that. That is very important. We have to work on that and see that really our systems are immune to that, because we are going to invest billions of dollars, assuming that we have overcome Shor's limitations. Right? So some people should really work on that. That's what the challenge was also posed yesterday on the 1 million rupees, I think, right? 10 lakh rupees challenge. So that is very important to work on that. The third thing is, of course, many people spoke about the standardization. It is very important that our products or algorithms adhere to some standards. It is not to discourage the new mechanisms, but it's from the business perspective, we have to adhere to the standards and see that our products will be really obeying some standards or follow the guidelines. And of course, you can be bold and come out with your own algorithms, own mechanisms, but protect them, get the IP protection before you release it into standardization bodies. I'll be very happy to take those cases to the standardization body, because that is my job. Of course, I'll be happy, but don't violate the standards as far as possible. And then the last part is about the applications. Some people spoke about very interesting applications. For example, cameras, how quantum enabled cameras can take the images in spite of fogs and other obstacles. That is very interesting. Although it may not be communication in the true sense, where you transmit some data and receive at the other places, but even camera may be thought of as a form of communication, where you put some signals and get the reflected things back, right? So where the transmitter and receiver could be at the same place or position. So many new applications will really come up. And as I was telling, when quantum teleportation becomes a reality, we will come up with so many zillions of applications, unheard and unthinkable applications, where you don't have to put anything onto the channel. Directly you can replicate the information from one place to the other place. In fact, on the lighter sense, I don't have to carry my bag. I can replicate it to Bangalore. I can go hands-free to the airport. Right? With this concluding remark, I will see you in the next conclave. I'll be very happy to invite you for the next conclave. Probably AK will take care of.
Thank you, Dr. Iyer. With that, we take your leave on behalf of TEC and our collaborators, CDOT, TS, DSI, and IEEE. We thank you all, our distinguished speakers, our esteemed delegates, all the learned audience. Thank you so much, and you may all proceed for high tea now. Thank you. Okay, we have one memento presentation for Dr. Manjunath Iyer. Dr. Iyer, please. Thank you for your closing remarks today and tomorrow, and today and yesterday, sorry. Thank you.